Motorola. Ord RT his data SET. By MC145488/D. Semiconductor. Technical data. MC145488. Advance information. Dual Data Link Controller, DDLC. Serial Control. P or T. IOLFTOM. IEnterFA-CE. MUM. IEnterFAC-EI__________1. Channel 0. Pro TOCOL. C Control LER. CHAN L1. Pro TOC OL. C on TROLLER. Block diagram. Microprocessor. Interfac-E. This document contains information on a new PRODU-CT. Specifications and information herein are subject to C hang without notice. Copyright Motorola in C1989. At Motorola. AD11524. Expanse is a trademark of Second Wave Incorporated. Macintosh is a registered trademark of Apple Computer Incorporated. Microwire is a trademark of National Semiconductor Corp. PAL is a registered trademark of Advanced Micro Devices Incorporated. Motorola reserves the right to make changes without further notice to any products herein to improve reliability, function, or design. Motorola does not assume any liability arising out of the application or use of any product or circuit described herein, neither does it convey any license under its patent rights nor the rights of others. Motorola products are not authorized for use as components in life support devices or systems intended for surgical implant into the body or intended to support or sustain life. Buyer agrees to notify Motorola of any such intended end use, whereupon Motorola shall determine availability and suitability of its product or products for the use intended. Motorola and registered are registered. Trademarks of Motorola, Inc. Motorola Incorporated is an equal employment opportunity/affirmative action employer. Motorola. 2. MC145488. Paragraph. Number. 1.1. 1.2. 1.3. 1.4. 2.1. 2.1.1. 2.1.1.1. 2.1.1.2. 2.1.1.3. 2.1.1.3.1. 2.1.1.3.2. 2.1.1.4. 2.1.2. 2.1.3. 2.2. 2.2.1. 2.2.1.1. 2.2.1.2. 2.2.1.3. 2.2.2. 2.2.3. 2.2.4. 2.3. 2.3.1. 2.3.2. 2.3.2.1. 2.3.2.2. 2.3.2.3. 2.3.3. 2.3.4. 2.4. 2.4.1. 2.4.2. 2.4.3. 2.5. 2.6. 2.7. MC145488. Table of Contents. Title. Section 1. Overview. Introduction. Features. DDLC Overview. HDLC Protocol Overview. Section 2. Block Diagram Description. Transmit Bit Handler. Packet Operation. State Diagram. Abort Character. Flow Control Mechanisms. ISDN-D Channel Contention. Modem Flow Control. Interrupts. Transmit FIFO. Transparent operation. Receive bit handler. Packet operation. State diagram. Non-octet aligned packets. Address recognition, filtering. Receive FIFO. Transparent operation. Interrupts. DMA controller. DMA operation. Buffer descriptors. Transmit buffer descriptors. Receive buffer descriptors. Address expansion. Transmit channel operation. Receive channel operation. Microprocessor interface. System slave mode. System master, DMA, mode. Interrupt operation. Serial interface. Serial control port. Timers. Page. Number. 1 to 1. 1 to 1. 1 to 2. 1 to 2. 2 to 1. 2 to 1. 2 to 2. 2 to 2. 2 to 3. 2 to 3. 2 to 3. 2 to 4. 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 2 to 5. 2 to 5. 2 to 6. 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 2 to 7. 2 to 7. 2 to 7. 2 to 7. 2 to 9. 2 to 9. 2 to 10. 2 to 10. 2 to 11. 2 to 11. 2 to 12. 2 to 12. 2 to 12. 2 to 12. Motorola. 3. Paragraph. Number. 2.7.1. 2.8. Table of contents. Continued. Title. Watchdog timer. Power consumption. Section 3. Register descriptions. Page. Number. 2 to 13. 2 to 13. 3.1 System Control Register. 3 to 1. 3.2 Master Status Register, Interrupt Vector. 3 to 2. 3.3 Interrupt Enable Register. 3 to 3. 3.4 SCP Status / Control Register and TX / RX Register. 3 to 4. 3.5 Timer Register. 3 to 6. 3.6 Serial Interface Control Register. 3 to 6. 3.7 Transmit Control Register. 3 to 8. 3.8 Receive Control Register. 3 to 9. 3.9 Transmit Status Register. 3 to 10. 3.10 Receive Status Register. 3 to 11. 3.11 Address Compare Register. 3 to 13. 3.12 Address Wildcard Bit Register. 3 to 14. 3 Costa Rican Colones and 13 Centimos Error Count Register. 3 to 14. 3.14 DMA Base Address Registers. 3 to 14. 3.15 Transmit Frame Length Register. 3 to 15. 3.16 Receive Buffer Length Register. 3 to 15. 3.17 Receive Frame Length Registers, Read Only. 3 to 15. 3.18 Transmit Byte Count, Read Only. 3 to 16. 4.1. 4.1.1. 4.1.1.1. 4.1.1.2. 4.1.1.3. 4.1.1.4. 4.1.1.5. 4.1.2. 4.1.2.1. 4.1.2.2, 4.1.2.3, 4.1.2.4, 4.1.2.5, 4.2, 4.2.1, 4.2.2, 4.2.3, 4.2.4, 4.2.5, 4.3, Motorola. 4. Section 4. Signal descriptions. MPU interface pins. 4 to 1. 68,000 operation. 4 to 1. Address and data bus. 4 to 2. Control bus. 4 to 2. Bus arbitration. 4 to 3. Interrupt signals. 4 to 3. Miscellaneous signals. 4 to 4. 80,186 operation. 4 to 4. Address and data bus. 4 to 5. Control bus. 4 to 5. Bus arbitration. 4 to 5. Interrupt signals. 4 to 6. Miscellaneous signals. 4 to 6. Serial communication pins. 4 to 7. IDL bus mode. 4 to 7. Time slot mode. 4 to 8. Modem mode, packet operation. 4 to 9. Modem mode, transparent operation. 4 to 10. Serial control port. 4 to 10. Power supply. 4 to 11. MC145488. Paragraph. Number. 5.1. 5.1.1. 5.1.2. 5.1.2.1. 5.1.2.2. 5.1.3. 5.1.3.1. 5.1.3.2. 5.1.3.3. 5.1.3.4. 5.1.4. 5.2. 5.2.1. 5.2.1.1. 5.2.1.2. 5.2.2. 5.2.2.1. 5.2.2.2. 5.2.2.3. 5.2.3. 5.3. 5.3.1. 5.3.1.1. 5.3.1.2. 5.3.1.3. 5.3.1.4. 5.3.1.5. 5.3.2. 5.3.3. 5.3.4. 5.3.5. 5.4. Table of contents. Continued. Title. Section 5. Bus operation. 68,000 system operation. Bus width selection. Host operation. Write cycle. Read cycle. DMA operation. DMA write cycle. DMA read cycle. Bus error recovery. Wait state generator and DAC control. Bus arbitration. 80,186 system operation. Host processor operation. Write cycle. Read cycle. DMA operation. DMA write cycle. DMA read cycle. Wait state generator and ready control. Bus arbitration. Interrupt operation. Interrupt sources. Normal interrupts. Timer interrupts. Bit handler fault interrupts. System fault interrupts. SCP complete interrupt. Interrupt request, IRQ, pin. Interrupt vector. 68,000 interrupt acknowledge cycle. 80,186 interrupt acknowledge cycle. Reset operation. Section 6. Serial interface operation. Page number 5 to 1, 5 to 2, 5 to 2, 5 to 2, 5 to 3, 5 to 3, 5 to 4, 5 to 5, 5 to 5, 5 to 6, 5 to 6, 5 to 7, 5 to 7, 5 to 8, 5 to 8, 5 to 9, 5 to 9, 5 to 9, 5 to 10, 5 to 10, 5 to 11, 5 to 12, 5 to 12, 5 to 13, 5 to 13, 5 to 13, 5 to 13, 5 to 14, 5 to 14, 5 to 14, 5 to 15, 5 to 15, 6.1 Interchip Digital Link, LDLL interface for ISDN applications. 6 to 1. 6.1.1 Functional description. 6 to 1. 6.1.2 Subrate multiplexing, CCID 1.460. 6 to 2. 6.1.3 Transparent operation. 6 to 3. 6.2 Time slot interface. 6 to 4. 6.2.1 Mode selection. 6 to 5. 6.2.2 Long frame operation. 6 to 5. 6.2.3 Short frame operation. 6 to 5. 6.2.4 Subrate multiplexing. 6 to 6. MC145488 Motorola. V. Paragraph. Number. 6.2.5. 6.3. 6.3.1. 6.4. 6.4.1. 6.4.2. 6.4.3. 7.1. 7.1.1. 7.1.2. 7.1.2.1. 7.1.2.2. 7.1.2.3. 7.1.3. 7.1.4. 7.1.5. 7.2. 7.2.1. 7.2.1.1. 7.2.1.2. 7.2.1.3. 7.2.1.4. 7.2.1.5. 7.2.1.5.1. 7.2.1.5.2. 7.2.1.6. 7.2.1.7. 7.2.2. 7.2.2.1. 7.2.2.2. 7.2.2.2.1. 7.2.2.2.2. 7.2.2.2.3. 7.2.2.2.4. 7.2.2.2.5. 7.2.2.2.6. 7.2.2.3. 7.2.2.3.1. 7.2.2.3.2. 7.2.2.4. Motorola. 6. Table of contents. Continued. Page. Title number. Transparent operation. 6 to 6. Modem interface. 6 to 6. Transparent modem operation. 6 to 7. Serial control port, SCP. 6 to 7. Serial control port description. 6 to 8. SCP master mode. 6 to 9. SCP slave mode. 6 to 10. Section 7. Applications. ISD Envoy/Data Terminal Adapter. IDL and SCP interfaces. MPU/DMA interface. Interrupt vectors. DMA bus arbitration. Decoder PALs. User interface, microcomputer keyboard/display controller. Real-time operating system. Summary. ISDN terminal for the Macintosh SE. Terminal card hardware description. The Macintosh SE expansion bus. Data, address, and control buses. Interrupts. PAL device. Serial buses. IDL bus. SCP bus. SID transceiver and line interface blocks. Codec/filter block. Terminal card software. Software functional description. Description of the individual blocks. Transmit procedure. Reception procedure. Data link layer. Physical layer. Hardware interface. Hardware drivers. Implementation issues. Memory buffer management. Flow control and error recovery in the data link layer. Summary. 7 to 1. 7 to 2. 7 to 2. 7 to 3. 7 to 4. 7 to 4. 7 to 5. 7 to 6. 7 to 7. 7 to 7. 7 to 8. 7 to 8. 7 to 8. 7 to 14. 7 to 14. 7 to 14. 7 to 17. 7 to 17. 7 to 18. 7 to 18. 7 to 20. 7 to 20. 7 to 20. 7 to 22. 7 to 22. 7 to 24. 7 to 24. 7 to 25. 7 to 26. 7 to 26. 7 to 26. 7 to 27. 7 to 28. MC145488. Paragraph. Number. Table of contents. Concluded. Title. Section 8. Electrical specifications. Page. Number. 8.1 maximum ratings. 8 to 1. 8.2 thermal characteristics. 8 to 1. 8.3 DC electrical characteristics. 8 to 1. 8.4 power considerations. 8 to 2. 8.5 MPU/DMA timing characteristics, 68,000 model. 8 to 3. 8.6 MCLK timing characteristics. 8 to 7. 8.7 serial interface, modem mode, timing characteristics. 8 to 8. 8.8 serial control port timing characteristics. 8 to 9. 8.9 IDL timing characteristics. 8 to 10. 8.10 serial interface timing characteristics, long and short frame modes. 8 to 10. 8.11 MPU/DMA timing characteristics, 80,186 mode. 8 to 14. Section 9. Mechanical data. 9.1 pin assignment. 9 to 1. 9.2 package dimensions. 9 to 2. MC145488 Motorola. 7. List of illustrations. Figure page. Number title number. 1 to 1 HDLC frame format. 1 to 2. 2 to 1 DDLC block diagram. 2 to 1. 2 to 2 transmitter state diagram. 2 to 2. 2 to 3 receiver state diagram. 2 to 5. 2 to 4 alternate receive buffer operation. 2 to 8. 2 to 5 transmit DMA state diagram. 2 to 9. 2 to 6 receive DMA state diagram. 2 to 11. 2 to 7 timer clock selection. 2 to 13. 3 to 1 register memory map. 3 to 16. 5 to 168,000 host write cycle. 5 to 2. 5 to 268,000 host read cycle. 5 to 3. 5-368,000 DMA write cycle. 5 to 4. 5 to 468,000 DMA read cycle. 5 to 5. 5 to 568,000 DMA write cycle with one programmed wait state and a delayed DAC. 5 to 6. 5 to 668,000 bus arbitration. 5 to 7. 5 to 780,186 host write cycle. 5 to 8. 5 to 880,186 host read cycle. 5 to 8. 5 to 980,186 DMA write cycle. 5 to 10. 5 to 1080,186 DMA read cycle. 5 to 10. 5 to 1180,186 DMA cycle with one programmed wait state and delayed RDY. 5 to 11. 5 to 1280,186 bus arbitration. 5 to 11. 5 to 1368,000 LAC cycle. 5 to 14. 5 to 1480,186 INTA cycle. 5 to 15. 5 to 15 watchdog generated reset. 5 to 15. 6 to 1 typical DL bus application. 6 to 1. 6 to 2 IDL frame timing. 6 to 2. 6 to 3 IDL bus signals. 6 to 2. 6 to 4 IDL subrate multiplexing. 6 to 3. 6 to 5 transparent byte alignment. 6 to 4. 6 to 6 PCM highway application. 6 to 4. 6 to 7 typical PCM bus. 6 to 5. 6 to 8 time slot operation long frame. 6 to 6. 6 to 9 time slot operation short frame. 6 to 6. 6 to 10 DDLC modem application. 6 to 7. 6 to 11 transparent modem operation. 6 to 7. 6 to 12 ISDN terminal application. 6 to 8. Motorola. 8. MC145488. Figure. Number. 6 to 13. 6 to 14. 6 to 15. 7 to 1. 7 to 2. 7 to 3. 7 to 4. 7 to 5. 7 to 6. 7 to 7. 7 to 8. 7 to 9. 7 to 10. 7 to 11. 7 to 12. 7 to 13. 7 to 14. 7 to 15. 7 to 16. 7 to 17. 7 to 18. 7 to 19. 7 to 20. 7 to 21. 8 to 1. 8 to 2. 8 to 3. 8 to 4. 8 to 5. 8 to 6. 8 to 7. 8 to 8. 8 to 9. 8 to 10. 8 to 11. 8 to 12. 8 to 13. 8 to 14. 8 to 15, 8 to 16, MC145488. List of illustrations. Concluded. Page. Title number. SCP module block diagram. 6 to 8. SCP pin functions master mode. 6 to 9. SCP pin function slave mode. 6 to 10. ISDN terminal adapter with voice and data block diagram. 7 to 1. IDL, SCP bus connections. 7 to 2. 128 KB memory map. 7 to 3. Real-time multitasking operating system. 7 to 6. Terminal adapter software/hardware model. 7 to 7. Macintosh SE ISDN terminal card hardware block diagram. 7 to 8. DDLC type def, C language. 7 to 9. DDLC buffer aliaco procedure, C language. 7 to 13. Macintosh SE terminal card, MPU section. 7 to 15. ST read write O procedure, C language. 7 to 17. SCP_transfer O procedure, C language. 7 to 18. Macintosh SE terminal card, S/T transceiver section. 7 to 19. ISDN transmit peer interface and protection. 7 to 19. Macintosh SE terminal card, codec/filter section. 7 to 21. Terminal card software block diagram. 7 to 21. Transmit procedure. 7 to 23. Reception procedure. 7 to 23. Buffer descriptor. 7 to 27. Linked list of descriptors. 7 to 27. Circular queue of descriptors. 7 to 27. Data link headers. Dash. 7 to 28. Test load. 8 to 2. 68,000 MPU write timing. 8 to 4. 68,000 MPU read timing. 8 to 4. 68,000 DMA arbitration and write timing. 8 to 5. 68,000 DMA arbitration and read timing. 8 to 6. MCLK timing diagram. 8 to 7. Serial interface, modem mode, timing diagram. 8 to 8. SCP master mode. 8 to 9. SCP slave mode. 8 to 9. IDL timing. 8 to 11. Time slot mode timing long frame operation. 8 to 12. Time slot mode timing short frame operation. 8 to 13. MPU read timing, 80,186 mode. 8 to 15. MPU write timing, 80,186 mode. 8 to 15. DMA write timing, 80,186 mode. 8 to 16. DMA read timing, 80,186 mode. 8 to 17. Motorola. 9. List of tables. Table page. Number title number. 3 to 1 reset operation results. 3 to 17. 4 to 1 68,000 mode pin functions. 4 to 1. 4 to 2 80,186 mode pin functions. 4 to 4. 4 to 3 serial interface pins. 4 to 7. 4 to 4 MPU interface pin names. 4 to 12. 5 to 1 interrupt priority and vector values. 5 to 12. 6 to 1 time slot byte alignment. 6 to 3. 7 to 1 system decode et pals. 7 to 4. 7 to 2 PAL design equations. 7 to 4. Motorola X. MC145488. 1.1 Introduction. Section 1. Overview. The MC145488 is a 2-channel ISDN LAPD controller with an on-chip direct memory access DMA controller. It is intended for ISDN terminal and switch applications where 1 or 2 channels of data will use HDLC type protocols. The DDLC is ideally suited for use with the MC145474 SID transceiver. The Interchip Digital Link, IDLL, easily connects the chips together, providing a powerful Layer 1/Layer 2 ISDN solution. A serial control port is provided to efficiently control the MCL45474 or other ISDN family devices. The DDLC is compatible with 68,000 and 80,186 bus structures. 1.2 Features. 2 independent full duplex bit-oriented protocol controllers supports HDLC, SDLC, CHIT X.25. CHIT 921 Quetzales, LAPD, and V.120 at basic and primary rates. 4-channel on-chip DMA controller. 64 KB address range with expansion control. Internal programmable wait state generator. 2 buffer descriptors for each receiver channel. Compatible with 68,000 and 80,186 bus structures. Non-multiplex 16 or 8-bit data bus. Bit-level HDLC processing including flag generation/detection, abort generation/detection, zero insertion/deletion, CRC chit generation/checking, residue bit handler, T/SAPI address comparison, 3 address comparisons, wildcard bits for block comparisons, transparent mode for codec compatibility, programmable interrupt vector generator, 2 independent timers configurable as a watchdog timer, flexible serial interface with IDL interface for connection to other ISDN family devices, time slot interface for connection to PBX type backplanes, modem interface for other applications. Supports JIT specification 1.460. Supports DMI specification 3.1 modes 0, 1, 2, and 3. Serial control port for ISDN family device control. Low power CMOS with automatic power down. MC145488 Motorola. 1-to-1. 1.3 DDLC overview. The MC145488 Dual Data Link Controller, DDLC, is a high-performance 2-channel protocol controller. With an on-chip direct memory access controller, DMAC. Each channel has a full duplex transceiver with independent protocol controllers to handle the bit-level tasks of HDLC-type bit-oriented protocols including LAPB and LAPD. Each channel also has dedicated DMA controllers for transmit and receive. A transparent mode is provided which bypasses the protocol circuitry so that serial data may be directly DME'd between the host processor's memory and the serial interface. The DDLC's microprocessor interface is configurable to 68,000 or 80,186 systems and may be used in 8-bit or 16-bit modes. Each channel has a serial data interface which operates up to primary rate speeds in 3 modes, IDL, time slot, and modem. In the IDL, Interchip Digital Link, mode for ISDN applications, the IDL bus is supported. While in the IDLD mode, access control lines to the D channel, through the MC145474 SID transceiver, are included. The time slot mode is used to connect the DDLC to PBX type PCM highway backplanes. Both long frame and short frame timing are supported, as well as asynchronous transmit and receive. In the modem mode, each channel has its own separate transmit and receive clock inputs along with modem control lines, RTS, CTS, and CD. The two channels are independent and may be in different interface modes. A serial control port, SCP, is provided to pass control information to other devices in a system. The SCP is compatible with Motorola Serial Peripheral Interface, SPI, and National Semiconductor's microwire plus star. Two internal timers may be used for general purpose, low-resolution timing of HDLC-type protocols. One of the timers may be configured as a watchdog timer to reset the entire system in the event of a hardware or software failure. Power consumption is an important aspect of ISDN terminal designs, and the DDLC was designed to use the minimum power possible while maintaining maximum functionality. The DDLC keeps power consumption to a minimum with an automatic power down feature that turns off sections of circuitry that are not being used. Only those circuits that are actually used, such as when the CS pin is activated for a register read-write or when the DMA controller performs a bus transaction, does the chip enter the normal power state for the duration of the access and for any time required for internal processing. Two internal loopback functions and special chip and system test modes are available. The loopbacks are controlled by the host for online maintenance. The test modes are activated by bits in the master control register and provide access to the internal state machines. 1.4 HDLC Protocol Overview. HDLC, High-Level Data Link Control, and its descendants, LAPB, Link Access Protocol Balanced, and LAPD, Link Access Protocol for the D-channel, are bit-oriented synchronous protocols which are finding increased usage in data communication systems. LAPB and LAPD share the basic format of HDLC but differ in certain aspects of the software implementations. See Figure 1:1. N bit 16 bits. Information Air. Figure 1:1. Whole frame format. The DDLC in the packet mode transmits and receives data in a format called a frame or packet. All frames start with an opening flag and end with a closing flag. Between the flags, a frame contains an address field, control field, information field, and a cyclic redundancy check field, CRC. Asterisk microwire is a trademark of National Semiconductor. Motorola. 1:2. MC145488. Flag. The flag is the unique binary pattern, 0111110. It provides the frame boundary and a reference for the position of each field of the frame. The DDLC transmitter generates a flag pattern internally and the opening flag and closing flags are appended to a frame automatically. Two successive frames can share one flag as a closing flag of the first frame and the opening flag of the succeeding frame. The receiver searches for a flag on a bit-by-bit basis and recognizes a flag at any time. The receiver establishes frame synchronization with every flag. The flags mark frame boundaries and references for each data field, but they are not transferred to the receive FIFOs or memory address field. The 8 or 16 bits following the opening flag comprise the address field. The address field is used to distinguish between the various devices in a network. Devices receiving frames not addressed to them may discard and ignore the frames. The DDLC has address recognition circuitry included which relieves the host from this task. Control field. The 8 or 16 bits following the address field are the control field. Commands and responses between the devices in a network are exchanged in this field. Information field. This field follows the control field and precedes the CRC field. The information field contains the data to be transferred and may be a null field. Additionally, the information field is not necessarily an integral number of octets in length. The DDLC receives non-octet frames as octets and LSB justifies the extra orphan bits at the end of the field. The number of orphan bits is indicated in a residue register. Cyclic redundancy check field. The 16 bits preceding the closing flag are the CRG field. This field detects bit errors in the address, control, and information fields. Checking is with the standard CHIT. Polynomial x16 x12 x5 plus 1 for both the transmitter and receiver. Both the transmitter and receiver polynomial registers are initialized to all ls when a flag character is detected, then begins calculating the CRC. The transmitter calculates the CRC on all bits of the frame except for the flags and transmits the complement of the resulting remainder as the CRC field. The receiver performs the similar computation on all bits except for the flags and compares the result to FOBs, hex. When the result matches FOBS, the frame is accepted and the buffer is closed. CRC generation and checking are automatically performed by the DDLC. The CRC field is transferred to the buffer in memory. If desired, frames with CRC errors can be discarded automatically. All CRC errors are logged in a counter. For network-level error checking, the transmitter can generate faulty CRCs to simulate transmission errors. Zero insertion and deletion. Zero insertion and deletion, which allows the content of the frame to be transparent, is automatically performed by the DDLC. A binary 0 is inserted by the transmitter after any succession of 5 ls within a frame, between flags. This eliminates the possibility of data imitating a flag character. The receiver deletes all OS that were inserted by the transmitter to regenerate the original data. Abort. The function of prematurely terminating a data frame is called an abort. The transmitter aborts a frame by sending between 7 and 14 consecutive ls. When the receiver detects an abort character, it responds by clearing the FIFO and clearing the buffer in memory. It then begins searching for a new frame. Idle and interframe time fill. For LAPB and other applications, there are 3 states that the data link may be in frame, interframe time fill, and idle. In frame is the period from the beginning of an opening flag and the end of a closing flag. Interframe time fill is the period between frames when continuous flags are transmitted. Idle is an out-of-frame period when continuous ls are on the link. In LAPD, on the D channel, there are only 2 states, in frame and idle. Continuous flags are not transmitted between frames. MC145488 Motorola 1-3 Motorola 1-4 MC145488. Section 2. Block diagram description. This section describes the internal blocks of the DDLC. The blocks include 2 protocol controllers which handle the bit-level aspects of HDLC like packet protocols and 4 FIFOs which buffer the data, a 4-channel DMA controller and a microprocessor interface block which connects the DDLC to the host system. The serial interface block is described in detail in Section 6. Figure 2:1 is a simplified block diagram of the DDLC. While the DDLC has 2 data transceivers, only one is shown for simplicity. Serial bus. Serial control port I timers. Plus. Serial. Interface. T. F plus TX bit. TXF. Handler FIFO. LL-OMA. Controller. RX bit R plus RX. Handler FIFO. +++. Interrupts. Figure 2:1. DDLE block diagram. 1 transceiver shown. 2.1 transmit bit handler. I. MPU. Interface. IMPU bus. T. I. 2 identical bit level protocol transmitters are provided which perform HDLC type framing. This section describes the operation of one transmitter, but it applies to both. 2.1.1 Packet operation. The transmitter is designed to operate with as little intervention from the host processor as possible. 2. Transmit a frame of data. The host merely informs the DDLC of the starting address of the data frame in memory and the length of the frame in bytes. The DDLC then transmits an opening flag and the data LSB first, from memory. When the transmitter detects that the end of the data buffer has been reached, a CRC field and a closing flag are appended. Zeros are automatically inserted after every string of 5 ones in the data to prevent imitation of a flag or abort character. The transmitter generates an abort character if the FIFO underruns. During interframe periods, the DDLC has the capability of transmitting either continuous flags, 7E hex, or continuous marks, FF hex, as selected by the interframe time fill bit. For network-level fault isolation, when the force CRC error bit is set, faulty CRCs are generated, simulating a transmission error. The transmitter also continuously monitors the CTS pin and indicates the current state of the pin with the CTS status bit in the transmit status register. MC145488 Motorola. 2:1. 2.1.1.1 State diagram. Figure 2:2 is the state diagram for the transmitter in packet operation. Idle is entered any time the transmit enable bit is low or when mark idle is selected and no data is ready to transmit. When data is ready or flag idle is selected, the send flag 1 state is entered. At least one flag character will be sent before the send data state is entered. The state machine remains in the send data state until an end of frame, EOF, tag is received through the FIFO from the DMA controller. Send CRC then send flag 2 states are entered. After sending the closing flag, if data for another frame is ready, send data is entered allowing the closing flag to be shared with the following frame's opening flag. If no data is ready, either idle or send flag 1 is entered depending on the setting of the frame time fill bit. A FIFO underrun causes the state machine to enter the abort state where an abort character is sent to clear the link. When the modem control signals are used, if the CTS pin goes inactive for more than 1 bit time, an abort condition is generated and the current state is exited for the abort state. See section 2.1.1.3 for a further discussion of flow control. 2.1.1.2 Abort character. The DDLC transmits an abort character which is compatible with DMI 3.1 modes 2 or 3 for restricted B-channel applications. In restricted access, no more than 7 OS in a row may be transmitted. Because the HDLC protocol format may have any number of OS contiguously in the data field of a frame, DMI modes 2 and 3 invert all data before transmission. The DDLC inverts all Transmitted data bits when the data invert bit of the transmit control register is set to 1. Normally, with the data inverted, the maximum number of OS transmitted is 6, the number of ones, inverted to OS, of Motorola 222. No. Data. Idle. Dash comma equals dash, abort. Data ready dr. Flag idle. Send. Flag 1. 1-1 __ abort dr, no CTS flag sent n. Data ready. Send. Data. Abort. Ab.ort dr-r. No CTS dr, end of data FIFO underrun. Amon. CRC sent no CTS. Send abort dr, flag to no CTS. Abort sent. Figure 2-2. Transmitter state diagram HDLC operation. MC145488. A flag, 0111110, character. However, an HDLC abort character is 7 to 14 contiguous LS, which, when inverted, may be too many OS, so the DDLC transmits an abort character of 0111111. This ensures that the maximum number of OS, inverted from LS, is limited to 7 even if the preceding data was 5 LS. In LAPB operation, the character following the abort character will always be a flag with the first bit a 0. When the DDLC is configured for ISDN D-channel use, an abort character of 11111111 is followed by idle, continuous LS. In certain applications a software-generated abort may be desired. The following is the recommended procedure to generate an abort. 1. Clear the buffer ready bit and set the force abort bit. 2. Reload the DMA pointers to the next frame's buffer, and 3. Set the buffer ready bit. This procedure disables any pending DMA requests, then causes the transmitter to begin an abort sequence. At the same time the state machine clears the FIFO. The user then prepares the next frame for transmission. Simply negating the transmit enable bit will cause an abort sequence, but it is uncontrolled. The host processor does not know when the idle bits were actually transmitted, and if the transmitter is re-enabled before at least 7 LS were transmitted, a valid abort may not be transmitted. When the transmit DMA complete interrupt is enabled, if an abort sequence is generated due to negation of the CTS pin or a FIFO underrun, the buffer ready bit in the transmit control register is reset after the abort has been completely transmitted. The host is then free to prepare a buffer descriptor for the next frame to be transmitted, either a new frame or the aborted one. Control of the buffer ready bit is different if the transmit frame complete interrupt is enabled. This is discussed in section 2.1.1.3.2. 2.1.1.3 Flow Control Mechanisms. The DDLC provides 2 flow control mechanisms, one for basic rate ISDN applications and the other for standard modem applications. The following paragraphs describe the operation of the two schemes. 2.1.1.3.1 ISDN D-channel contention. When the DDLC is operating on the D-channel with the companion MC145484 SIT transceiver, the DREO and DGNT lines must be used to comply with the basic rate D-channel contention algorithm. When the DDLC has a data frame to transmit, it asserts DREO, high. The MCL45474 transceiver monitors the SIT interface for activity on the D-channel and indicates when the channel is free by asserting DGNT, high. While DREO is high, the DDLC samples DGNT on the falling edge of IDL sync. Transmission from the DDLC begins in the IDLD bit time slots when DREO and DGNT are both active. If a D-channel collision is detected on the SIT interface by the MC145488 transceiver, DGNT is negated, low. ISDN D-channel contention rules state that when a collision is detected, the colliding device must immediately stop transmitting and retransmit the frame at a later time when the zero channel is again available. When a collision is indicated, the DDLC automatically aborts the frame in progress and prepares to retransmit the entire frame when the D channel again becomes available. This is done without interrupting the host. The transmit frame complete interrupt must be enabled to allow this operation. When the packet has been successfully transmitted, a transmit frame complete interrupt is generated when the last zero of the closing flag is transmitted. If a software-generated abort is desired while in D-channel operation, transmit DMA complete should be enabled and transmit frame complete should be disabled before the force abort bit is set. This ensures that the aborted frame will not be retransmitted after the abort character is sent. After the force abort bit is cleared by the transmitter, the host is free to prepare a buffer descriptor for the next frame to be transmitted. 2.1.1.3.2 Modem Flow Control. The transmitter indicates to a modem that it has data ready to transmit, with signals similar to D-channel operation. In this mode, request to send, RTS, is directly controlled by the transmit enable, TE, bit. When TE is high, the RTS pin is asserted, low. During interframe periods, either flags or marks, as selected, are transmitted but the RTS pin remains asserted until the user negates. MC145488 Motorola 2 to 3. The TE bit transmission of a frame, if one is ready, actually begins when the modem asserts clear to send, CTS low. If CTS is negated for more than one TXCLK period while a frame is in transmission, the frame is aborted and the DMA pointers are reset so that the frame can be retransmitted without interrupting the host. Section 2.1.1.2 indicates that while the transmit DMA complete interrupt is enabled, the buffer ready bit is reset after the abort character is transmitted. This operation is modified while the transmit frame complete interrupt is enabled, in which case the buffer ready bit remains set after an abort character is sent. When a collision is detected, an abort character is sent immediately followed by automatic retransmission of the colliding frame. 2.1.1.4 Interrupts. There is one interrupt generated by the transmitter state machine. Transmit frame complete indicates that an entire frame and its closing flag have been successfully transmitted. It is issued when the state machine exits the send flag to state. Ordinarily this interrupt is used for basic rate ISDN D-channel operation. Two other interrupts associated with the transmitter are generated by the DMA controller and are discussed in section 2.3.2. 2.1.2. Transmit FIFO. The transmitter has a FIFO which buffers it from the DMA controller. It is 4 characters deep and 9 bits wide. The 9th bit is a tag bit which is attached to the last byte of a frame by the DMA controller. When the host has a message to send, the DMA controller fills the transmit FIFO and attempts to keep it full. A comparator in the controller keeps track of the FIFO occupancy and requests that the DMA controller load a word of data, 16 bits low when the FIFO has 2 empty bytes. In 8-bit operation the DMA controller fetches 1 byte when there are 1 or more bytes available in the FIFO. At 64 kbps, DMA Requests from a transmit FIFO are generated at approximately 250 ps intervals. If the DMA controller does not service a request and the FIFO underruns, an interrupt is queued and the current frame in transmission is aborted. 2.1.3 Transparent operation. The transmitter has the capability of operating with unframed data such as PCM encoded voice or proprietary protocols. Raw data may be transmitted from memory with byte alignment maintained through the FIFO and transmitter. Byte alignment signals must be provided. In the modem mode, the alignment signal is externally generated. In ID LAN time slot operation, it is internally generated but user programmable. See section 6.1.3 for a further discussion. The DDLC transmits data continuously as long as there is data to transmit. To keep a continuous stream of data flowing, the transmit DMA complete interrupt should be enabled. This interrupt occurs at least 16 bit times before the FIFO becomes empty and the state machine enters the idle state. At 64 kbps, 250 ps is available to prepare the next buffer for transmission. Before the FIFO empties and idle characters, either marks or flags, are transmitted. 2.2 Receive bit handler. The receiver provides the complementary functions to the transmitter. This section describes the operation of one receiver, but it applies to both receivers. 2.2.1 Packet operation. The receiver is reset and idle until the receive enable bit is set, at which time it begins searching for a flag character. When a flag is found, the selected address field of the frame, if desired, is checked, and if a match is found, the DDLC passes the frame of data to the allocated buffer in memory. If no address match is found, the DDLC clears the FIFO, resets the DMA pointers and searches for a new frame. Zeros inserted by the transmitter are removed from the data before placing the bytes in memory. When the Motorola 224 MC145488 closing flag is detected, the CRC field is checked, and if found to be correct, the DDLC queues an interrupt, indicating that a good data frame has been received and is in memory. If the CRC is found to be in error, the DDLC resets the buffer pointers to the start of the buffer and searches for a new frame. This in essence clears the buffer and discards the frame in error. In certain instances, frames with CRC errors will be of interest. A control bit is provided so that frames with CRC errors can be passed to memory. The receive on CRC error bit enables this feature, and the CRC error bit indicates that the frame has an error. All CRC errors are logged in the CRC error register. The DDLC rejects undersize frames. If a frame of less than 4 octets between flags is found, it usually means that a bit error occurred, so out of frame is entered. If an abort character is found, the buffer pointers in the DMA controller are reset and the aborted frame is ignored. The FIFO is cleared and the receiver begins searching for a flag. No interrupt is generated. 2.2.1.1 State diagram. Figure 2-3 shows the state diagram of the receiver. When the receiver enable bit is initially set, the state machine is in the out-of-frame state. The pattern detector continuously searches for flags, and when it finds one, the flag state is entered. If the next character is not a flag, the machine enters the in-frame state. Address recognition is sampled on the first or second byte after entering this state. If the address does not match, the out-of-frame state is entered and the receiver searches for a new frame. When a flag is found in the in-frame state, an end of frame is assumed and the CRC checker is sampled and an end of frame tag is generated and passed to the FIFO. Then the flag state is entered. The receiver detects and reacts to aborted frames. If an abort is detected, the state machine enters out of frame. Section 2.3.4 has more discussion of the different end of frame tag signals. No. Flag. Flag. Found. No. Flag. Out of frame. Flag. Found. No. Flag. In frame. Abort. Flag. Found. Abort or address mismatch. Figure 2-3. Receiver state diagram. HDLC operation. 2.2.1.2 non-octet aligned packets. The receiver has the capability of operating in non-octet aligned packet systems. The residue bit count indicating the number of orphan data bits at the end of the information field is placed in the RC bits of the receive status register. These bits are valid until overwritten by another frame. In non-octet aligned systems, the software should check the residue count soon after receiving a receive buffer complete interrupt to ensure that the residue count is not overwritten by the next frame. Orphan bits are LSB justified in memory. Note, the DDLC cannot transmit non-octet aligned frames. MC145488 Motorola 2-5 2.2.1.3 Address recognition, filtering. The receiver can filter received frames by comparing their address fields to user programmable addresses. Two addresses may be programmed with another broadcast, FF hex, hardwired into the receiver. Address filtering may be performed on either the first or second octet following the opening flag of a frame. The ABS bit in the receive control register when high enables filtering on the first octet and when low filters on the second octet. Typically, in ISDN terminal applications, the tel address, second, field will be of interest. In network applications, the SAPI, first, field will be checked. A separate wildcard register allows selected bits of compare address 0 to be ignored during the comparison procedure. This provides a simple way to widen the bandwidth of the address filter, allowing blocks of addresses to be passed to memory. If received frames are rejected by address recognition, the receiver is reset and searches for a new frame. Address recognition may be disabled by clearing the address compare enable bit to 0. 2.2.2 Receive FIFO. The receiver has a FIFO which is similar to the transmitters. It is 4 characters deep and 10 bits wide. 8 bits for data and 2 bits for the tag. Serial bytes are produced by the receiver and converted to parallel. As each byte is formed, it is pushed into the FIFO. A comparator in the controller keeps track of the occupancy of the FIFO and requests that the DMA controller place a word of data, 16 bits, in memory when there are 2 or more bytes in the FIFO. In 8-bit operation, the FIFO requests service when 1 or more bytes of data are ready to be placed in memory. If the FIFO overruns because the DMA controller did not service a request, an interrupt is queued. When a receiver is operating at 64 kbps in the 16-bit mode, DMA requests from that FIFO occur at approximately 250 IS intervals. 2.2.3 Transparent operation. The DDLC provides transparent operation for passing raw octet-aligned serial data to memory via DMA. This feature is useful for storing PCM voice or proprietary protocols in memory. When using the DDLC, to pass PCM voice to memory, maximum buffer size of 4096 bytes should be used. Ordinarily, this will cause an interrupt every 500 milliseconds. When the buffer overrun interrupt is generated, the DMA controller automatically switches to the alternate buffer, if it is available, and begins placing data in it. No data will be lost in the changeover from one buffer to the other. Note that the receive DMA complete interrupt is not generated in transparent operation, because the transparent mode requires that data be in 8-bit quantities. Synchronization procedures for defining octet boundaries are required. In the modem mode, the sync signal is externally generated and input on the CD pin. In IDL and time slot operation, the sync signal is internally generated but user programmable. Once byte alignment is obtained in the receiver, it is maintained through the DMA controller into memory. Section 6.1.3 contains more details regarding transparent operation. 2.2.4 Interrupts. There are two interrupts generated by the receiver. Receive idle indicates that 15 or more consecutive 1s were received. This interrupt is considered normal operation. The current status of receive idle and carrier detect is available in the receive status register, but it must be kept in mind that they can change immediately after being read. The carrier detect pin also generates an interrupt when it changes state. Section 5.3 details all interrupts. 2.3 DMA controller. In order to relieve the host software from critically timed data transfers to or from the protocol controllers, the DOL provides 4 DMA channels, one for each transmitter and receiver. Motorola 226 MC145488 2.3.1 DMA operation. When the DMA controller detects a service request from one of the FIFOs, it prepares the address and data for the transfer, then requests ownership of the system bus from the host. When ownership is granted, the DMA controller assumes control of the bus and transfers data either to or from memory. Transfers are 16 bits or 8 bits depending on the selected bus width. In a 16-bit system, all transfers are word-wide. When the number of bytes in a received frame is odd, the last byte is placed in the most significant byte of the last word. The least significant byte will contain unknown data. The received byte count will contain the correct number of bytes received, including the CRC. When odd-length frames are transmitted, the last word read from memory will have the last byte transmitted in the most significant byte and the least significant byte of that word will be discarded. For Operation Indiana 80186 systems, see Section 5.2. The DMA controller uses a round-robin strategy to service internal DMA requests. A channel that was just serviced will not be polled again until all other channels have been polled and serviced, if needed. The DDLC services one DMA request per bus arbitration cycle. For example, if two channels have requests pending, when the DDLC assumes ownership of the bus, one channel is serviced, then the bus is relinquished. The DDLC re-requests the bus no sooner than 3 MCLK cycles after the bus was relinquished, allowing another bus master to begin a cycle. This type of operation improves system performance and guarantees that the DDLC will be well behaved. The DDLC prepares the data to be transferred on received DMA requests, and calculates the address before requesting the bus. This requires minimum overhead, dead cycles while the host is transferring ownership of the bus. The next bus owner may assume ownership immediately after the DDLC has relinquished the bus. It is impossible to precisely predict what the DDLC bus occupancy will be, but worst case with both. Channels operating full duplex at 64 kbps, aggregate rate of 256 kbps, in a 16-bit 68,000 system with a 12 MHz MCLK, approximately 0.66% of the host bus bandwidth will be consumed by the DDLC. This figure assumes 1-1/2 front-end overhead cycles and no wait states. While the DDLC was designed to operate with both channels at 64 kbps, it is possible to operate at much higher data rates. Bus occupancy increases linearly with data rate. At very high data rates, latency from the bus request to the bus grant and interrupt service latency become the limiting factors. It must also be kept in mind that the DDLC can generate interrupts quickly, especially with a large number of small data packets. 2.3.2 Buffer descriptors. As previously stated, the DDLC has 4 DMA channels. Pointer registers and counters are required so that the DMA controller knows where to place or fetch data in memory. 2.3.2.1 Transmit buffer descriptors. When the host has a frame of data to transmit, it informs the DMA controller where the data resides in memory. A 16-bit register, the transmit base address register, points to the first word of the transmitted frame and provides 64 kbyte address range. The host programs the address of the first word to be transmitted into this register. The length of the data frame must also be given to the DMA controller, so a 12-bit transmit frame length register is used to indicate the length of the frame in bytes. Frames of up to 4096 bytes in length may be transmitted. Note, once a transmit buffer descriptor has been prepared, it must not be disturbed until the transmit DMA complete or transmit frame complete interrupts are generated. Modifying the contents of an active buffer descriptor may result in data being transmitted from unintended areas of memory. 2.3.2.2 Receive buffer descriptors. The receive buffer descriptors have a 16-bit receive buffer base address register, a 12-bit buffer length register, and a 12-bit frame length register. The 16-bit base address register provides 64 kbyte address range and contains the address of the first word of the data buffer which will accept a data frame. The 12-bit buffer length register indicates the length of the MC145488 Motorola 227 memory buffer in bytes. Buffers of up to 4096 bytes may be built. The DMA controller will never place data outside of the boundaries set up by these two registers. The frame length register indicates the number of bytes, including the CRC, received. Each channel has a pair of buffer descriptors. These may be used alternately so that while one buffer is filling, another buffer is ready in waiting. If back-to-back data frames are received, after the first buffer has been closed, the second is immediately ready for the next frame. There must be at least one buffer ready to accept data when the RX enable bit is set. Figure 2-4 describes the activity of the receiver with 4 buffers in memory. Initially, buffer A start address is set to a BOO hex and buffer B is set to a DOO. The length register is set to 200 hex. After the first frame is received, buffer A is set to be 300 hex to prepare for the third frame. After the second frame is received, the fourth buffer is prepared with an address of B500. This process continues for the entire session. In a typical ISDN B-channel system at 64 kbps with frames of 256 bytes in length, interrupts requesting new buffer allocations will occur at approximately 32 milliseconds intervals. ABOOB 300. Receiver buffer. 13. Buffer A start address A-B-O-O hex. Buffer A length 200 hex. Buffer B start address A-D-O-O hex A-D-O-O B 500. Buffer B length 200 hex. Buffer underscore. Buffer A start address AD 300 hex 24. Buffer A length 200 hex. Buffer B start address B 500 hex. Buffer B length 200 hex I. System memory I. Figure 2-4. Alternate receive buffer operation. If a packet is coming in and no buffers are ready, the receive FIFO will overrun, the receiver enable bit is reset, and an interrupt is queued indicating the overrun. If both descriptors are ready, then buffer A will be filled. If a received frame is larger than a buffer, the buffer, A or by overrun interrupt will be queued, but the receiver will continue to receive and the DMA controller will place the data in the alternate buffer, if it is available. If an alternate buffer is not ready, the RxFIFO overrun interrupt will be generated, and the receiver is reset. Two buffer-ready bits, buffer A ready and buffer B ready of the receive control register, are provided which allow the DMA controller to operate on that buffer. DMA activity on a receive channel begins when there is data in the FIFO and a buffer-ready bit is set. As the buffer fills, the byte count increments. When the last byte has been placed in memory and the CRC has been checked OK, the selected buffer-ready bit, buffer A ready or buffer B ready, is cleared, halting future DMA activity on that buffer until it is again prepared by the host. Once a data frame has been completely received, the number of bytes received is indicated in the frame length register. The number in this register is valid only when the received DMA complete bit, buffer A or buffer B, in the receive status register is set to 1. If non-octet aligned frames are received, the number of residue bits, valid bits, in the last byte is indicated in the RC bits of the receive status register. The residue bits in memory will be least significant bit justified. For octet-aligned systems, the residue count should always be 0. Motorola 228. MC145488. Note, as with the transmitter, once a receive buffer descriptor has been prepared, it must not be disturbed until the closing flag has been found and DMA activity on the buffer has stopped. This is indicated by the receive DMA complete, buffer A or B, interrupt. Modifying the contents of an active receive buffer descriptor may result in data being placed into unintended areas of memory. 2.3.2.3 Address expansion. The DDLC provides signals for expansion of the 64 KB address space. The OWN pins are activated with timing identical to the address pins to enable external address circuitry onto the address bus. Using the OWN pins with the R/W pin, the transmit and receive buffers may all be on separate 64 KB pages in memory. Section 7 describes address expansion techniques in more detail. 2.3.3 Transmit channel operation. Figure 2-5 is a simplified state diagram of the DMA controller's operation when a transmit channel requests service. The DMA controller continuously polls the 4 channels for DMA requests. When a transmit request is found, an address pointer into the buffer is prepared and compared to the ending address of the buffer. If the pointer is pointing to the last byte of the buffer, an EOF tag is prepared to inform the transmitter and the DMA complete interrupt is generated. The bus is then requested. When it is granted, a read cycle is performed. Data read from memory is placed into the FIFO in ascending address order. If during the bus cycle a bus error or address error is detected, the buffer ready bit is cleared, halting further DMA requests from that channel. A system error interrupt is then queued. MC145488. Normal. Termination. Poll. Requests. TXDMA. Request. Prepare. Address. Buffer not. Empty. Bus granted. Bus error. Disable. Channel. 1-buffer. Empty. No. TAC. Close. Buffer. Figure 2-5. Transmit DMA state diagram. Motorola. 2-9. An internal counter keeps track of the number of bytes transferred to the FIFO. When its count equals the number in the frame length register, an end of frame tag is generated and loaded into the FIFO, along with the last byte. The buffer ready bit is reset, a transmit DMA complete interrupt is queued, and further DMA activity on that channel is suspended. The host prepares the next frame by setting up another buffer descriptor and setting the buffer ready bit high. 4 interrupts are produced by the transmitter DMA channel. Transmit DMA complete indicates that the last byte of data has been transferred from the buffer into the transmit FIFO. FIFO underrun indicates that DMA requests were not serviced and the FIFO underran. Bus error is generated when the burp pin is activated during a DMA cycle, and address error is generated when either LAC or CS are activated. During a DMA cycle, communication from the DMA controller to the transmitter is through the tag bit, as there is an unknown time delay from the DMA controller's activities to the time when the transmitter actually operates on the data. The EOF tag informs the transmitter to close the frame with a CRC field and flag. Note that if the software reacts to the DMA complete interrupt and prepares the next frame's buffer, the end of the previous frame may still be in the FIFO while the first 2 bytes of the next frame are loaded. When the transmitter finds the situation, after closing the first frame it shares the flag between frames and begins the next frame. This section has only described the internal operation of the DMA controller. For details about DMA from the MPU's point of view, see section 5.1.2. 2.3.4 Receive Channel Operation. Figure 2-6 is a simplified state diagram for operation of the DMA controller when a receive channel requests service. The DMA controller first gets data from the FIFO and arranges it into ascending order for 68,000 or 80,186 operation. While it is preparing the data, it examines the tag bits. If the tag indicates that an error was received, the byte counter is reset, enabling the buffer to be reused. If a normal EOF is found, the buffer ready, A or B, bit is cleared and receive DMA complete interrupt is queued. If no tag is found, a pointer to the next buffer location is prepared. If the pointer indicates that the buffer is full, a buffer overrun interrupt is queued and the alternate buffer is activated, if it is available. Only after the data and address are ready is bus request asserted. A write cycle is then executed when ownership is granted. If a bus error or address error is detected during a bus cycle, a system error interrupt is queued, and the RxN bit is cleared, resetting the receiver. As with the transmitter, all communication between the receiver and DMA blocks is through the tag bits. In the FIFO, because 3 end-of-frame conditions are reported, 2 bits are used. When a CRC error tag is detected, the receive CRC error bit in the receive status register is set. If RCE in the control register is set, and the CRC error log counter is incremented. If RCE is not set, the receive byte counter is reset, enabling the buffer to be reused. When an abort tag is detected, the byte counter is reset, effectively clearing the buffer for reuse. When a normal EOF is found, the buffer ready, B, is cleared, and a receive DMA complete interrupt is queued. When the next frame arrives, the alternate buffer will be used. When transparent mode is used, no tags are generated, so the RxDMA complete interrupt is never generated. The DMA controller generates a buffer overrun interrupt when the buffer actually fills. At 64 kbps, the host has approximately 375 ps before the FIFO overruns, or 250 ps before the alternate buffer is activated. 2.4 Microprocessor interface. The microprocessor block interfaces the internal L6-bit bus to the host's 8 or L6-bit bus. All timing, conversion and buffering is also performed. This block has three modes of operation: system slave, system Motorola 2 to 10, MC145488, Poll RxDMA, requests request, I plus buffer, no buffer, prepare full, alternate, available, buffer I buffer, available, normal, termination, reset, byte, count, ERROTEOF, prepare, data, no TOF, plus, prepare, A address, buffer not, F plus L, request, bus, bus GIANTED, bus, cycle, bus JERR, T, disable, channel, normal close, EOF buffer, no, 2G, no, DAC, figure 2 to 6, DMA receive state diagram, master, and interrupt generator. This section will describe the operation of these three modes. Operation of the DDLC in an 80186 system is described in section 5.2. 2.4.1 System Slave Mode. When the DDLC is in this mode, it appears as fast memory to the host processor. The host can read or write from PR to the registers in the DDLC. This mode is entered when the CS pin is activated. Internal address decoding circuitry is selected and the desired register is connected to the internal bus for access by the host. Section 5.1.1 describes 68,000 operation and Section 5.2.1 describes 80,186 operation. 2.4.2 System Master, DMA, mode. During DMA operation, the DDLC becomes a system master and controls the system bus. When one of the internal FIFOs requests a DMA transfer, the DDLC negotiates with the system host for ownership of the bus. After successful negotiation, one DMA request is serviced, then the bus is relinquished. The DDLC has the capability of reading or writing data from or to memory. If the memory system is slow, the DDLC inserts wait states, user selectable, until the memory is ready to complete the access. The DDLC has the capability of recovering from system faults such as address or bus errors. If one of these faults are detected, the DDLC disables the particular DMA channel which encountered the fault and queues an interrupt indicating the fault. The pointers in the DMA register which had the fault remain where they were when MCL46488 Motorola 2 to 11. The fault was detected, so the host may investigate the problem. A system fault on any channel will not affect the operation of any other channel. Sections 5.1.2 and 5.2.3 describe the operation of the DDLC as a bus master and the bus negotiation procedure. 2.4.3 Interrupt operation. The DDLC has 27 vectored interrupt sources to inform the host of its status. One group of interrupts is normal operation interrupts. These inform the host that a particular task was completed and that new tasks are desired. Another group is bit handler faults, which inform the host that a DDLC channel detected a fault from which it cannot recover without assistance from the host. A third group is the timer and SCP interrupts. The last group of interrupts is the system faults. These include bus errors and address errors. When a DMA channel encounters one of these errors, it stops operation on the affected channel and informs the host that the channel has been disabled. All interrupts are maskable. In the case of system faults, all channels interrupts are enabled or masked as a group. The interrupts are presented to the host as a vector number in an interrupt acknowledge cycle. The interrupts are encoded into 4 bits, so the DDLC vector space consumes 16 out of 256 locations. 4. Applications not using vectored interrupts, the equivalent vector number is accessible in the master status register. Interrupts are queued internally and a priority mechanism is used to ensure that the most important interrupt is serviced first. Interrupt operation of the DDLC is described more fully in section 5.3. All interrupt status bits have a feature where they may be set by the user to generate an immediate interrupt. This is useful for software debugging. 2.5 Serial interface. The serial interface block has a variety of configurations which make it compatible with most common interfaces. Each channel serial interface is independent, so 2 different configurations may be active simultaneously. The serial interface has an IDL mode, a time slot mode, and a general purpose modem mode. The operation of these modes is fully described in section 6. 2.6 Serial control port. A serial control port, similar to the serial peripheral interface, SPI, on Motorola single-chip microprocessors, is provided to communicate with external devices via a serial link. The SCP functions are multiplexed onto other serial pins, so when the SCP is enabled, certain modem control features will be lost. Section 6.4 describes in detail the operation of the SCPO. 2.7 Timers. 2 timers are provided for general-purpose low-resolution protocol uses. The clock to the timer is derived from the master MPU clock, MCLK. The baud rate generator in the SCP block is used to drive the timer divide chain. This clock is then divided by 1024 and applied to an 8-bit down counter. The counter is readable and writable by the host and may be set to any value. The counter counts down toward 0 from the current value. A non-maskable interrupt is generated when the counter underflows from 00 to FF. The timer function and interrupt are enabled by setting the timer enable bit in the timer register to 1. The timer interrupt status bits must be read while set before they may be cleared. See section 5.3.3. As previously stated, the timers are intended for low accuracy uses such as protocol timers. If the host is accessing the timer for a read or write and a countdown pulse arrives, the pulse is ignored. For its intended application, this will not cause any difficulty. Figure 2-7 describes the clock selection choices for the timers. Motorola 2-12, MC145488, SCP clock generator. MCLK plus 1024 plus 16. Prescale select. Figure 2-7. Timer clock selection. 2.7.1 Watchdog timer. Timer 0. Up timer mode. Down watchdog mode. Timer 1. Timer 0 may be configured as a watchdog timer for the entire host system. When the watchdog enable bit is set, an extra divide by 16 is added to the clock input of the counter. When the counter underflows from 00 to FF, the reset pin becomes an output for 16 MCLK cycles and a logic low is output. This provides a system reset to the host. The host can write any value, except FF hex, to the timer register. To set up any timeout. Timeouts of up to 5.6 seconds are available with a 12 MHz MCLK. See section 5.4. For timing information on watchdog generated resets. 2.8 Power consumption. The DOLC is designed utilizing high-performance CMOS technology. As a result, average power consumption is very low. However, because there are wide address and data buses, peak currents may exceed 150 mA for short periods of time, less than 20 ns, while the drivers are charging or discharging the buses. The bit handler sections of the chip are only clocked during active bit times. In the IDL or time slot modes, even though there is a continuous clock running, internal circuitry is active only while the time slots are enabled. The average power consumption is thus proportional to the bit rate, i.e., for an 8-bit time slot. In an IDL system, the bit rate is 64 kbps. The peak bit rate may be 2.56 MHz and during an active time slot, the power consumption will be proportional to the peak bit rate. However, averaged over a 125 J.L.S frame, power consumption will drop to a level proportional to the average bit rate. To further reduce power consumption, sections of the circuitry are not clocked rather than just held in reset during states when they are not needed. For example, while a receiver is searching for a frame, the CRC checker of that receiver is disabled and not clocked. The internal 16-bit bus remains idle until the host requests a read or write cycle or until a DMA cycle is requested. 3 separate VOD/VSS pairs are provided. Each powers a separate section of the chip. Section 4.3 details which pins power which sections. It is expected that the user will utilize good grounding and power decoupling techniques when designing the DDLC into a system. MC145488 Motorola 2-13 Motorola 2-14 MC145488. Section 3 Register descriptions. The DDLC has several user-accessible registers. These registers control the blocks or indicate status. Other registers, used by the DMA section, are used as buffer descriptors and counters. This section provides a description of the registers and the bits in those registers. The address for each register is the hexadecimal offset from the base address of the chip select. The registers may be accessed as 8-bit registers. All status bits, except where noted, may be written with 1 to generate an interrupt. This is useful for system debugging. 3.1 System Control Register. Address 00 hex. This register holds the various bits which control the MPU interface and test functions. When read as a 16-bit register, the most significant byte is 00. This register is cleared to 0000 hex after a reset. OA9. 4. TST to WSRSTL. BW bus width. This read-only bit is a status bit which indicates the data bus width. When this bit is 0, the data bus is 8 bits wide and the upper data byte pins are disabled. When this bit is 1, the data bus is 16 bits wide. 8-bit operation is selected by connecting the D8 pin to VSS. 16-bit operation is selected by writing FFFF to address 6. The mode is then permanently latched. Only hardware reset can clear 16-bit operation. RST master reset. This bit resets the DDLC when set tot. A software reset sequence begins when the write cycle is completed. This bit is reset to 0 after the sequence is completed. Section 5.4 describes the sequence. WS wait. Select these bits. Choose the number of wait states the DMA controller inserts into direct memory access cycles. The bits are encoded as B3 B2 wait states 000, 011, 102, 114. Section 5.1.3.4 describes the operation of the wait state generator. MC145488 Motorola 3 to 1. The DAC enable. When this bit is 0, the DAC signal is ignored so DMA accesses are completed after the programmed wait states have terminated. When this bit is 1, DMA accesses are completed after the programmed wait states have terminated and the DAC pin is asserted. The DAC pin operates normally in the 68,000 host processor mode as an output regardless of the setting of this bit. Section 5.1.3.4 discusses DAC functionality. TST test O test 2. These bits control factory test modes and are not user accessible. 3.2 Master status register, interrupt vector. Address 02 hex. This register contains a code indicating the highest priority interrupt source at the time that this register is read. When an interrupt acknowledge cycle is executed, the contents of the least significant byte are placed on the data bus. When read as a 16-bit register, the upper byte reads 00. After a reset, this register is cleared to 0000 hex. OBA 00 4 User V VEC vector. These bits contain the interrupt source coded as follows. User Motorola 3 to 2 B3 B2 B1 BO 0000 no interrupt 0010 SCP complete 00x1 timer interrupt 01XX bit handler normal operation 10XX bit handler fault 11XX system fault. X indicates that the respective bit may be 0 or 1 as described below. BO this bit is set to 0 when the interrupting source is a receiver and AT when the source is a transmitter. B1 this bit indicates the channel which caused the interrupt. An interrupt from channel A causes the bit to be set to 0 and channel 1 causes the bit to be set to 1. User programmable. These bits are user programmable so the programmer may place the DDLC's vectors anywhere in the vector space. Note, after reset this register reads 00 hex. As such, the DDLC does not generate an uninitialized interrupt of hex, as some 68,000 family peripherals do. MC145488 3.3 Interrupt enable register. Address 04 hex. This register controls the generation of interrupts to the host. If a bit is set, the respective interrupt is enabled. In some cases, a bit controls the interrupts for both channels. In every case, even if an interrupt is disabled, the status bit associated with the disabled interrupt will reflect the current state of the DDLE. If an interrupt is disabled, it will not be encoded into the vector. B. AE. Roko. ROC1. Taka. TOC1. TFCO. TFC1. MC145488. CBA. SCPCCOL COD RIL RIO BOV FUN FOV. 40. TFCL TFCO to CL TOCO ROCL ROCO AEB. Bus error. When this bit is set to 1, bus errors from all 4 channels can generate. Interrupts. When this bit is cleared to 0, all bus error interrupts are disabled. Each DMA channel can generate a separate bus error interrupt which is encoded in the vector number. Address error. When this bit is set to 1, address errors from all 4 channels can generate interrupts. When this bit is cleared to 0, all address error interrupts are disabled. Each DMA channel can generate a separate address error interrupt which is encoded in the vector number. RxCH0 OMA complete. When this bit is set to 1, an interrupt is queued when the DMA controller has transferred a complete data frame to memory from Rx channel O. When this bit is cleared to 0, the interrupt is withheld. This bit should be cleared when transparent operation is used. Use the buffer overrun interrupt to indicate that a buffer has filled. RxCH1 OMA complete. When this bit is set to 1, an interrupt is queued when the DMA controller has transferred a complete data frame to memory from Rx channel 1. When this bit is cleared to 0, the interrupt is withheld. This bit should be cleared when transparent operation is used. Use the buffer overrun interrupt to indicate that a buffer has filled. TXCH OMA complete. When this bit is set to 1, an interrupt is queued when the DMA controller has transferred the last byte of a buffer to the channel 0 TXFIFO. When this bit is cleared to 0, the interrupt is withheld. In transparent operation, this interrupt is not generated. TXCH1 OMA complete. When this bit is set to 1, an interrupt is queued when the DMA controller has transferred the last byte of a buffer to the channel 1 TXFIFO. When this bit is cleared to 0, the interrupt is withheld. TXCH frame complete. When this bit is set to 1, an interrupt is queued when the channel 0 bit handler has transmitted the last 0 of the closing flag of a complete data frame. When this bit is cleared to 0, the interrupt is withheld. This bit when set modifies the operation of the transmitter state machine during abort or collision events. See sections 2.1.1.2 and 2.1.1.3.1 for a further discussion. TXCH1 frame complete. When this bit is set to 1, an interrupt is queued when the channel 1 bit handler has transmitted the last 0 of the closing flag of a complete data frame. When this bit is cleared to 0, the interrupt is withheld. This bit when set modifies the operation of the transmitter state machine during abort or collision events. See sections 2.1.1.2 and 2.1.1.3.1 for further discussion. Motorola 323 FOV Fun BOV Rio RI1 Ku CD1 SCPC RxFIFO overrun. When this bit is set to 1, an interrupt is queued if either channel 0 RxFIFO or channel RxFIFO overruns. The channel which generated the interrupt is encoded in the vector number. When this bit is cleared to 0, an interrupt from either receive channels FIFO is withheld. TXFIFO underrun. When this bit is set to 1, an interrupt is queued if the channel 0 TX FIFO or channel TXFIFO underruns. The channel which generated the interrupt is encoded in the vector number. When this bit is cleared to 0, an interrupt from either transmit channels FIFO is withheld. Rx buffer overrun. When this bit is set to 1, an interrupt is queued if a received data frame is too large for the active data buffer. The channel which generated the interrupt is encoded in the vector number. When this bit is cleared to 0, a buffer overrun interrupt from either received channel is withheld. This bit normally is set when transparent operation is selected. RxCH0 idle. When this bit is set to 1, an interrupt is enabled when the channel 0 receiver detects 15 or more contiguous ones, indicating that the received channel is, or was, idle. When this bit is cleared to 0, the interrupt is withheld. RxCH1 idle. When this bit is set to 1, an interrupt is enabled when the channel receiver detects 15 or more contiguous LS, indicating that the received channel is, or was, idle. When this bit is cleared to 0, the interrupt is withheld. Carrier detect O. When this bit is set to 1, an interrupt is enabled when the channel 0 carrier detect pin changes state. When this bit is cleared to 0, the interrupt is withheld. Carrier detect 1. When this bit is set to 1, an interrupt is enabled when the channel carrier detect pin changes state. When this bit is cleared to 0, the interrupt is withheld. SCP complete. When this bit is set to 1, an interrupt is queued when the SCP module has completed an exchange with an external device. Interrupts may be generated in master or slave mode. 3.4 SCP status /control register and TX/RX register. Address 10 hex. This register contains the SCP TX/RX holding register and 8 status/control bits. After a reset, this register is cleared to 0000 hex. The serial control port may be used only when the SCP enable bit in serial interface control register 0 is set TOT. OA9 IRA81 MCIBRSN1 ENO TX 4 T/R T/RTX/RX register. The host writes this 8-bit register with the data to be transferred over the SCP link to an external device. Data is exchanged with the slave device MSB first. Motorola MC145488 3-4 TX ENO N1 BRS CI S/M IRQ MC145488. Upon completion of the transfer, this register contains the data received from the addressed device. If the host reads this register while a transfer is in progress, do hex is presented to the host. Transmit this bit when set to 1 causes the SCP controller to issue 8 clock pulses and exchange the data in the TXLRX register with the selected slave device's data. This bit is cleared to 0 when the exchange is complete. Note, the host should wait 2 SCP clock periods, as selected by the BR's bits, after this bit is automatically cleared before re-enabling this bit after an SCP transfer. This bit has no function in the slave mode. Enable 0. This bit directly controls the state of the SCP-N pin. When this bit is set to SCP-N is asserted, low. When this bit is cleared to 0, SCP-N is negated, high. SCP-N may be used as a general-purpose output controlled by this bit when the SCP function is not enabled. This bit has no function in the slave mode. Enable 1. This bit directly controls the state of the SCP-N, CH, CD, pin while the SCP enable bit in serial interface control register, 40 hex, is set. While this bit is set to SCP-N is asserted, low. While this bit is cleared to 0, SCPN is negated, high. When the SCP enable bit in serial interface control register is negated, this bit has no function. This bit operates in master and slave mode. Baud rate select these bits. Select the SCP clock frequency by choosing a tap from the master clock input, MCLK, divide chain. The output of this clock selector is also used for the two timers. See section 2.7. The divide ratios are encoded as follows. B11 B10 MCLK divider 00 plus 2 01 plus 4 10 plus 8 11 plus 16. Clock invert. This bit inverts the SCP clock polarity. While this bit is low, transmitted data bits shift on rising clock edges and received bits are sampled on falling edges. When the SCP is idle, the clock is low. While this bit is high, transmitted data bits are shifted on falling edges and received bits are sampled on rising edges. When the SCP is idle, the clock is high. Slave/master control. This bit selects master or slave mode. When this bit is 0, the master mode is selected. When the slave mode is selected, see section 6.4 for a further discussion of SCP modes. SCP interrupt status. This bit indicates the current status of the SCP interrupt. When a transfer is complete, this bit is set. This bit must be reset to 0 by the host only after it was read with the value. It must be reset to 0 by the host to clear this interrupt. Motorola 3 to 5 3.5 timer register. Address 12 channel 0. Address 14 chan I1. These registers contain a timer for each channel. The timer is a simple countdown timer which generates an interrupt when the count reaches FF hex. The clock source for the timers is the SCP clock divided by 1024. This generates maximum interrupt intervals of up to 500 milliseconds with an 8 MHz MCLK. The resolution of the counter varies from 250p.s to 2 milliseconds depending on the prescaler tap. The timers can be read or written at any time. Note, if a countdown pulse occurs while a timer register is being accessed, read or write, the pulse is ignored. Treg 10 WO TIRQ OCBA 9 OO Tyro WO 10 64 Treg Timer register. These bits are the 8-bit counter register. They may be read or written at any time. The contents of this register are unaffected by reset and contain unknown data at power up. Timer enable. When this bit is asserted to 1, the timer is enabled and will generate an interrupt when the counter reaches FF hex. When this bit is cleared to 0, the timer is disabled and cannot generate interrupts. This bit is cleared by reset. Watchdog enable, timer 0 only. This bit enables the watchdog function on timer O. When the watchdog is enabled, an extra +16 is inserted into the prescaler chain. Timeouts up to 8 seconds may be generated with the watchdog. This bit is cleared by reset. Timer interrupt status. This bit indicates that the timer generated an interrupt. This bit may be reset to 0 by the host only after it was read with the value 1, it must be reset to 0 by the host to clear this interrupt. 3.6 Serial Interface Control Register. Address 20 hex channel 0. Address 40 hex channel 1. This register contains the control bits for the serial interface blocks for each transceiver channel and is cleared to 0000 hex after a reset. OA SCPE toll loop TRSP-MOOE. 64. BMSK. BMSK bit mask. These bits select the individual bit positions in an 8-bit IDLB channel or time slot that are active. Each bit in this field corresponds directly to a bit in the time slot. Each bit which is asserted to 1 is disabled and each bit cleared to 0 is enabled. Note: serial transmission is LSB first, so the LSB of this field corresponds to the first bit of the B channel. Motorola MC145488. 3 to 6. Mode: TRSP. Loop. Toll. SCPE. MC145488. Time slot. This register is also used in the time slot or IDL transparent mode. See section 6.1.3 for a further discussion. Serial mode. Select these bits. Select the mode of operation for the serial interface. 4. A detailed description of the operation of these modes, refer to section 6. Note: the transparent mode should be initiated and terminated only while the transmitter and receiver enable bits are negated. See sections 2.1.3, 2.2.3, and 6.1.3 for a further discussion. The mode select bits are encoded as follows: BL0 B9 B8 mode, 000 time slot, 001 IDLB1 channel, 010 IDLB2 channel, 011 IDLD channel, 100 modem, 101 reserved, 110 reserved, 111 reserved. Transparent mode. This bit when asserted to 1 enables the transparent mode for both the transmitter and receiver. All HDLC framing and deframing circuitry is bypassed in the transparent mode. When this bit is cleared to 0, normal operation resumes. Look back. While this bit is asserted to 1, a loop back from the transmitter to receiver is enabled. While in loop back, the receiver input pin is disabled and the output of the transmitter is connected to the receiver. The transmit pin of the affected channel is controlled by the transmit on loop bit, B13. When this bit is cleared to 0, loop back is disabled and normal operation resumes. Note: loop back should be initiated and terminated only while the transmitter and receiver enable bits are negated. Timing of the transmit and receive channels must be identical for correct loop back operation. Transmit on loop. While this bit is asserted to 1, the transmitter pin transmits data normally while in loop back. When this bit is cleared to 0, the transmitter pin is forced to during loop back. SCP enable, channel 0 only. This bit, while asserted to 1, enables the serial control port. The channel 0 RTS, CTS, and CD pins assume the SCP functions. SCP enable, channel 1 only. This bit, while asserted to 1, changes channel CD into a general purpose output controlled by the ENL bit in the SCP control register. This may be independent of SCP operation. Motorola 3 to 7. 3.7 Transmit Control Register. Address 22 hex channel 0. Address 42 hex channel 1. This section describes 2 registers, one for each channel. Each bit performs an identical function for both channels. After reset, this register is cleared to 0000 hex. DBA. 4. DIFA MDFI ITFBRTE. TE transmit enable. This bit when asserted to 1 activates the transmitter. If TE is negated to 0 while a frame is in transmission, the transmitter immediately flushes the FIFO and enters the idle state. the DMA pointers are reset to their initial values and the DMA controller is disabled for that channel. This is equivalent to resetting the transmitter. During the time when TE is 0, the TXD pin is high impedance. This bit directly controls the RTS pin. When TE is high, RTS is low, and vice versa. When ISDN channel operation is selected, the DREQ pin is asserted and negated on a frame-by-frame basis as frames are ready for transmission. BR buffer ready. This bit, when asserted to 1 by the host, indicates that a buffer is ready for transmission and allows the DMA controller to service this channel. The DMA controller fills the transmit FIFO and the transmitter begins outputting data when DGNT, CTS, is asserted. When data in the buffer has been completely transferred to the FIFO, this bit is cleared by the DMA controller and an interrupt is queued. If the host clears this bit while a frame is in transmission, DMA activity on the channel stops. Sometime later, the FIFO will underrun and the frame is aborted. If a bus error or address error is detected during a DMA cycle involving this transmit channel, this bit is cleared by the DMA controller, disabling further DMA activity on this channel. The buffer pointers will remain where they were at the time of the system error. ITF interframe time F8. This bit controls the interframe time fill character to be transmitted. While this bit is set to 1, marks 1s are transmitted during interframe periods. Marks idle is used for LAPD operation. While this bit is 0, the transmitter fills interframe periods with flag characters 7e hex. Flags idle is used in X.25 operation. FCE4 CRC error. While this bit is asserted to a 1, transmitted frames contain forced CRC errors. This feature is useful for system debugging. Normally, this bit is cleared so normal CRCs are transmitted. MD mask drive. This bit controls the drive characteristics of masked off B channel or time slot bits. While this bit is set to 1, masked bits are driven to a logic 1. While cleared to a 0, masked bits are high impedance. This feature allows other devices to share a time slot on an IDL or PCM highway bus. FA force abort. When this bit is asserted to a 1, an abort character is transmitted and the transmitter returns to the idle state after the abort was transmitted. This bit is reset by the transmitter after the abort character is sent. See section 2.1.1.2 for a description of the preferred abort sequence. Motorola MC145488 328. Did data invert. When this bit is asserted to a, all transmitted data is inverted. Zeros become ones and ones become zeros. This feature is useful in DMI mode 2 and 3 operation. When this bit is cleared to a 0, data is transmitted normally. 3.8 Receive control register. Address 24 channel 0. Address 44 chan I1. This section describes 2 registers, one for each channel. Each bit performs an identical function for both channels. These registers are cleared to 0000 hex after a reset. A 4 01 ABS ACE RCE BBR bar receive enable. This bit, when asserted tot, enables the receiver. When the HDLC mode is operating, the flag search state is entered. In transparent mode, the receiver immediately begins accepting data and places it in the FIFO. If a bus error or address error is detected by the DMA controller, this bit is cleared. This is equivalent to a receiver reset. Bar buffer A ready. This set only bit controls DMA activity on buffer A's descriptor. When asserted to 1 by the host, it indicates that buffer A is ready to accept data frames and that DMA activity on this buffer may begin. After a complete frame has been received and placed in memory, this bit is negated to 0 by the DDLC's DMA controller and an interrupt is queued. When the receiver is disabled, this bit is cleared by the receive state machine. BBR buffer B ready. This set only bit controls DMA activity on buffer B's descriptor. When asserted to A by the host, it indicates that buffer B is ready to accept data frames and that DMA activity on this buffer may begin. After a complete frame has been received and placed in memory, this bit is negated to 0 by the DDLC's DMA controller and an interrupt is queued. When the receiver is disabled, this bit is cleared by the receive state machine. RCE MC145488. Note, the A and B buffers may be used in a ping-pong fashion so that while a frame is being received, an alternate buffer is prepared for the next frame. Continuous data in the transparent mode or back-to-back frames in the HDLC mode are easily accommodated. With this technique, once the programmer has set either of these bits, the buffer descriptors associated with these bits should not be disturbed until the RxDMA complete interrupt is generated and all DMA activity on that buffer has stopped. The receiver will place data in whichever buffer, A or B, is ready, and if both are ready, buffer A is filled. When enabling one of these bits after preparing a new buffer descriptor, the alternate bit should be cleared to 0. Because these bits are set only, writing a 0 ensures that the alternate buffer is not accidentally enabled, and if it is already enabled, there will be no change. Receive enable on CRC error. Normally, if a CRC error is detected in a frame, the DDLC discards the frame in error. The receive buffer is cleared and reused for the next data frame. When debugging a system, however, it is useful to examine frames with CRC errors to help locate the source of the errors. This bit, when asserted to, enables data frames to be placed in memory in the presence of CRC errors. The CRC error bit in the receive status register indicates that the received frame had a CRC error. When this bit is negated, Motorola 32920, all received frames with CRC errors are discarded and the buffer descriptor is reused on the next received frame. In all cases, independent of the setting of this bit, when a frame is received with a CRC error, the error is logged in the CRC error log register. ACE address compare enable in the HDLC mode. When this bit is asserted to 1, the address field of a frame is compared against the contents of the address compare registers. The address byte select bit selects which address field is tested. A data frame with an address that matches one of these addresses is passed to memory normally. If the address does not match, the FIFO is cleared, the DMA pointers are reset to their initial values and the receiver enters the flag search state to look for a new frame. Note that the LAPD broadcast address, FF hex, is hardwired into the address compare circuitry so 3 addresses can be tested. If comparison of the address field is not desired, negating this bit to 0 disables address filtering. This bit has no function in the transparent mode. ABS address byte select. This bit selects the octet in the received data frame which is tested by the address compare circuitry. While this bit is the first octet following the opening flag is tested. While this bit is 0, the second octet following the opening flag is tested. While the address compare enable bit is 0, this bit has no significance. Data invert when this bit is asserted to 1, all received data is inverted. Zeros become ones and ones become zeros. When this bit is cleared to 0, data is received normally. 3.9 Transmit status register. Address 26 hex channel 0. Address 46 hex channel 1. This section describes two registers, one for each channel. The two channels operate identically. DBA O 4 Foo TFCC TSBA ETDC. TDC transmit DMA complete when the DMA controller has transferred the last byte of a buffer into the FIFO, it asserts this bit to 1 and an interrupt is queued. If the host wishes to send back-to-back frames, another buffer can be prepared and activated before the FIFO goes empty and the transmitter begins transmitting interframe time fill characters. This bit must be reset to 0 by the host to clear the interrupt from this channel. AE address error. This bit when asserted to by the DMA controller indicates that an address error occurred when the DMA controller had ownership of the host's bus. An address error occurs when the CS pin or LAC pin is asserted while a DMA cycle is in progress. If an address error occurs, DMA activity on this channel is suspended and an interrupt is queued. This bit must be reset to 0 by the host to clear the interrupt from this channel. B bus error. This bit when asserted to by the DMA controller indicates that a bus error occurred when a DMA transaction was active on the respective channel. A bus error occurs. Motorola MC145488. 3 to 10. When the Burp pin is activated while the DMA controller has ownership of the host's bus. When a bus error is detected, the active BR bit is reset and DMA activity on that channel is suspended. This bit must be reset to 0 by the host after it is read to clear the bus error interrupt from this channel. Note, this function is not available in Indiana 80186 mode operation. CTS status. This bit indicates the current status of the CTS, DGNT, pin associated with each channel. The CTS int pin is sampled on every falling edge of the MCLK. This pin when set to a 1 indicates that the pin, CTS or DGNT, depending on the mode is asserted. CTS is an active low signal. DGNT is an active high signal. Note, the state of this bit can change immediately after it is read. TFC transmit frame complete only when a data frame has been successfully transmitted by the HDLC transmitter and the interframe fill state has been entered is this bit asserted to a 1 by the transmitter and an interrupt is queued. If a data frame is aborted by the Layer 1 device, as in an ISDN SID bus D-channel collision, the DDLC will retransmit the aborted frame without the host processor's intervention. This bit must be reset to 0 by the host to clear the interrupt from this channel. See section 2.1.1.3.1 for a further discussion. Foo FIFO underrun. This bit when asserted to 1 by the transmitter indicates that the TX FIFO had an underrun. An interrupt is queued when this bit is set. If an underrun occurs, the frame in transmission is aborted, see section 2.1.1.2. The BR bit is negated suspending DMA activity on that channel. This bit must be reset to 0 by the host to clear the interrupt from this channel. 3.10 Receive status register. Address 28 hex channel 0. Address 48 hex channel 1. This section describes two registers, one for each channel. Each bit performs an identical function for each channel. RAC, RBC, MC145488. OCBA. CoRICE COIRC FORC. 4. BAEBBO BAD RBC RAC. RX buffer a complete. This bit when asserted to 1 by the DMA controller indicates that the receiver has successfully received and placed an entire data frame in memory. An interrupt is queued when this bit is set. This bit must be reset to 0 by the host to clear the interrupt from this channel. This function is not used in transparent operation. RX buffer be complete. This bit when asserted to 1 by the DMA controller indicates that the receiver has successfully received and placed an entire data frame in memory. An interrupt is queued when this bit is set. This bit must be reset to 0 by the host to clear the interrupt from this channel. This function is not used in transparent operation. Motorola 3-11. Bow buffer A overrun if the received data frame exceeds the length of the receive buffer A. The DMA control dottler sets this bit to a 1 indicating that the received frame was too large for the buffer. If buffer B is available, it is activated and the overflow data is placed in that buffer. The bar bit is cleared by the DMA controller and further DMA activity on this buffer is suspended after the overrun is detected. This bit must be reset to 0 by the host to clear the interrupt from this channel. In transparent operation, this bit indicates that the buffer was completely filled. If buffer B is available and data continues, it is activated and further data is placed there. BBO buffer B overrun if the received data frame exceeds the length of the receive buffer B. The DMA controller sets this bit to a 1 indicating that the received frame was too large for the buffer. If buffer A is available, it is activated and the overflow data is placed in that buffer. The BBR bit is cleared by the DMA controller and further DMA activity on this buffer is suspended after the overrun is detected. This bit must be reset to 0 by the host to clear the interrupt from this channel. In transparent operation, this bit indicates that the buffer was completely filled. If buffer A is available and data continues, it is activated and further data is placed there. AE address error. This bit when asserted to 1 by the DMA controller indicates that an address error occurred while the DMA controller had ownership of the host's bus. An address error occurs when the CS pin or LAC pin is activated while a DMA cycle is in progress. If an address error occurs, the DMA controller clears the active buffer ready bar or BBR bit. DMA activity on that buffer is suspended and an interrupt is queued. This bit must be reset to 0 by the host to clear the interrupt from this channel. B bus error. This bit when asserted to 1 by the DMA controller indicates that a bus error occurred while a DMA transaction was active on the respective channel. A bus error occurs when the Burp pin is activated while the DMA controller has ownership of the host's bus. When a bus error is detected, the DMA controller clears the active buffer ready bar or BBR bit and DMA activity on that channel is suspended. This bit must be reset to 0 by the host to clear the interrupt from this channel. Note, this function is not available in 80186 mode operation. RC residue count. These 3 bits indicate the number of residue bits received. These bits have significance only when the RAC or RBC bits are set by the receiver. If both RAC and RBC are at a 1 level at the same time, the frame which had a non-zero residue count cannot be determined. The user must read the residue count soon after the end of frame. Interrupt as receiving another short frame may cause RC to be overwritten. FO. Dirk. Motorola. 3-12. FIFO overrun. This bit, when asserted to a 1, indicates a receiver FIFO overrun occurred, and data was lost. An interrupt is generated when an overrun occurs. The active buffer, ready, bar or BBR, bit is cleared and further DMA activity on this channel is suspended. A FIFO overrun can occur only if no buffer is prepared for the data in the host's memory, or if the DMA controller cannot gain access to the bus. This bit must be reset to 0 by the host to clear the interrupt from this channel. CDIRQ status. This bit, when high, indicates that the CD pin changed state and that an interrupt was queued. The current status of the CD pin is available on bit 15. This interrupt is generated every time the CD pin changes state. The CD pin is not available on either channel 0 or channel 1 when the SCP function is enabled or when the time slot mode is selected. MC145488. CECRC error. This bit when asserted to by the receiver indicates that the received frame had a CRC error. This bit only operates when the RCE bit is set to a 1 by the host and has significance only when RAC or RBC are set. If both RAC and RBC are at the same logic level at the same time, the frame which had a CRC error cannot be determined. RI receive idle. This bit is asserted to T by the receiver when 15 or more consecutive LS are detected, indicating that the channel is, or was, idle. An interrupt is queued when this bit is set. This bit remains set until it is cleared to 0 by the host. If the idle condition remains when this bit is cleared by the host, another interrupt will be generated. The communication channel may change state at any time and may become active immediately after reading this bit. CD status. This bit indicates the current status of the CD pin. When the CD pin is low, this bit is high and vice versa. The CS pin is sampled when this register is read. A maskable interrupt is generated every time the CD pin changes state. The CD pin is not available on either channel 0 or channel when the SCP function is enabled or when the time slot mode is selected. 3.11 Address compare register. Address to a hex channel 0. Address for a hex channel 1. This section refers to two 16-bit registers, one for each channel. BA. Address 1. 4. Address 0. This register contains the two addresses which are compared against incoming data frame address fields. If a true comparison is made, the data frame is passed to the FIFO. Compare address 1 resides in bit positions B8 B15 and compare address 0 resides in bit positions BO B7 of this register. Note that address FF hex is hardwired into the address compare circuitry, effectively providing a third address. See the address byte select bit description in sections 3.8 and 2.2.1.3 for a further discussion of the address compare feature. MC145488 Motorola 3-13 3.12 Address wildcard bit register. Address 2C hex channel 0. Address 4C hex channel 1. BA 4. Wildcard bits. This 8-bit register contains the wildcard, don't, bits for address compare O. Any bit that is set to 1 generates a true result after the comparison. With this feature, blocks of addresses can be compared with only one address specified and certain of the bits ignored. There is a 1-for-1 correspondence between the bits in the address comparison register and the wildcard register. Recall that data bits are received LSB first. 3 Costa Rican colones and 13 centimos error count register. Address 2E hex channel 0. Address 4E hex channel 1. O. OA. 4. Error count. This register contains the current number of CRC errors detected since it was reset. Each counter counts up to 255 and stops if more errors are detected. This register is reset to 0000 hex on reset, hardware or software, or any time it is written by the host. The upper byte always reads 00 hex. 3.14 DMA base address registers. Address 32 hex channel 0 transmit. Address 38 hex channel 0 receive buffer AL. Address 3C hex channel 0 receive buffer B. Address 52 hex channel 1 transmit. Address 58 hex channel 1 receive buffer A. Address 5C hex channel 1 receive buffer B. These 16-bit registers contain the addresses of the start of DMA buffers. For transmitters, the first 2 bytes of a frame to be transmitted reside at this location. For receivers, the first 2 bytes received will be placed in this location. For 16-bit systems, the base addresses must be even addresses, AO equals O. Must be taken by the programmer so that these registers are not disturbed while the buffer ready bit associated with that register is set to 1. If these registers are disturbed while the DMA controller is active, data may be written to unintended areas of memory, on received channels, or read from unintended areas. Motorola 3-14 MC145488 Transmitters. These registers are not disturbed by a reset. The programmer should place valid addresses in these registers before asserting the associated buffer ready bit to prevent DMA activity into unintended areas of memory. 3.15 Transmit frame length register. Address 30 hex channel 0. Address 50 hex channel 1. These 12-bit registers hold the length of the frames to be transmitted in bytes. The host writes this data into the register during the transmit buffer descriptor setup routine. After the length has been written, it should not be disturbed until the transmit complete interrupt is generated. The upper 4 bits always read a hex. These registers are not disturbed by a reset. The programmer must place valid data in these registers before asserting the associated buffer ready bit to prevent DMA activity into unintended areas of memory. 3.16 Receive buffer length register. Address 36 hex channel 0. Address 56 hex channel 1. These 12-bit registers contain the maximum length of the receive buffers for each channel. The DMA controller compares the current byte count to the value in this register before a DMA request is made. And if the byte count is equal to the buffer length, then a buffer overrun is declared and an interrupt is generated. Must be taken by the programmer so that this register is not disturbed while the rebit of the associated channel is set to 1. These registers are not disturbed by a reset. The programmer must place valid data in these registers before asserting the associated buffer ready bit to prevent DMA activity into unintended areas of memory. 3.17 Receive frame length registers, read only. Address 3A hex channel 0 buffer A. Address 3E hex channel 0 buffer B. Address 5A hex channel 1 buffer A. Address 5E hex channel 1 buffer B. These 12-bit read-only registers contain the length in bytes of the received data frames in their associated buffers. These registers are updated on every new byte placed in memory by the DMA controller. When the associated receive buffer, bar or BBR, bit is set and the received DMA complete interrupt is set, this register contains the final length of the frame including the 2 CRE bytes. If the received frame is not an integral number of octets long, the number of residue bits is found in the RX status register. These Registers may be read at any time, but they contain meaningful information only after the RxDMA complete. Interrupt has been generated. The upper 4 bits always read 0 hex. These registers are cleared to 0000. After a reset operation. MC145488 Motorola 3 to 15 3.18 transmit byte count, read only. Address 34 hex channel 0. Address 54 hex channel 1. These 12-bit read-only registers contain the count of bytes transmitted in the current frame. The count is cleared to 0 at the beginning of a frame. These registers are provided for diagnostic purposes. The upper 4 bits always read 0 hex. These registers are cleared to 0000 after a reset operation. Motorola 3 to 16 00 02 04 10 12 14 20 22 24 26 28 2A 2C 2E 30 32 34 36 38 3A 3C 3E 40 42 44 46 48 4A 4C 4E 50 52 54 56 58 SA 5C 5E B15 I BO System Control I Master Status I Interrupt Enable I SCP Register CH0 Timer CH1 Timer Channel 0 Serial Interface Control Channel 0 TX Control Channel 0 RX Control Channel 0 TX Status Channel 0 RX Status Channel 0 Address Compare Channel 0 Address Wildcard Bits M Channel 0 AX CRC Error Count Channel 0 TX Frame Length C Channel 0 TX Base Address I1Z Channel 0 TX Byte Count 1 LU Channel 0 RX Buffer Length Channel 0 RX Buffer A Base Address Channel 0 RX Buffer A Byte Count Channel 0 RX Buffer B Base Address Channel 0 RX Buffer B Byte Count Channel 1 Serial Interface Control Channel 1 TX Control Channel 1 RX Control Channel 1 TX Status Channel 1 RX Status Channel 1 Address Compare Channel 1 Address Wildcard Bits M Channel 1 Costa Rican Colon Aerodr Count : Channel 1 TX Frame Length D Channel 1 TX Base Address Z Channel 1 TX Byte Count CU Channel 1 RX Buffer Length Channel 1 RX Buffer A Base Address Channel 1 RX Buffer A Byte Count Channel 1 RX Buffer B Base Address Channel 1 RX Buffer B Byte Count Figure 3:1 Register Memory Map MC146488 MC146488 Table 3:1 Reset on RLTIN results Register NIMI reset results comments Notes 1. X indicates that the bit is unaffected by reset. After power up, the value is unknown. 2. This table applies to a hardware reset by the RST pin or a software reset by the MRST bit in the master status / control register. Motorola 3 to 17 Motorola 3 to 18 MC145488 Section 4. Signal descriptions. This section describes the input and output signals of the DDLC. Active low signals are indicated by an overbar N, example RST. Many of the signal pins are multiplexed with several functions available depending on the operating mode. Each multiplexed pin is described in its various mode settings separately. Pin numbers referenced in the following discussion refer to PLCC package pins. 4.1 MPU interface pins. This section describes the operation of the MPU interface pins. Since the DDLC has two modes of operation, Motorola 68000 and Intel 80186, both descriptions will be provided. In most cases, the pin names vary depending on the mode. Table 4-4 at the end of this section is a complete cross-reference of pin names and aliases for the various operating modes. For a complete discussion of both 68000 and 80186 functional timing, see Section 5. Parametric specifications are presented in Section 8. 4.1.1 68000 operation. This mode is selected by connecting a pull-up resistor to BGAC. A logic high value is internally latched when the DDLC exits the reset state. Any devices connected to BGAC should not be actively pulling down during reset. Table 4-1 describes 68000 mode pin functions. MC145488. Table 4-1.68000 mode pin functions. Signal mnemonic input/output. Active. Driver type. State. Address bus A1 A15 input/output 3 state. Data bus 00-015 input/output 3 state. Master clock MCLK input. Chip select CS input low. Address strobe as input/output low 3 state star. Upper data strobe UDS input/output low 3 state star. Lower data strobe LOS input/output low 3 state star. Read/write R/W input/output high/low 3 state star. Data transfer acknowledged DAC input/output low 3 state star. Bus request BR output low open drain. Bus grant BG input low. Bus grant acknowledge BGAC input/output low 3 state star. Bus owner 0 own 0 output low 3 state star. Bus owner 1 own 1 output low 3 state star. Interrupt request IRQ output low open drain. Interrupt acknowledge lack input low. Reset list input/output low open drain. Bus error BR input low. Asterisk these pins have an internal pull-up device momentarily activated immediately before going high. IMPT ANS for improved rise time. Motorola 4-1 4.1.1.1 address and data bus. A 1A15 address bus. These bidirectional pins are the address lines. When the DDLC is a bus master, these pins are outputs. They present the address of the memory location to be read or written. When the DDLC is a bus slave, these pins are inputs. Internal registers are accessed by placing the address of the selected register on the bus and then reading or writing the register's contents. When these pins are inputs, only the lower 6 bits are decoded and the upper 9 bits are thus don't do D15 data bus. These bidirectional pins are data lines. They are inputs when the host owns the bus and writes to the DDLC, or when the DDLC owns the bus and reads a memory location. They are outputs when the host owns the bus and reads the DDLC, or when the DDLC owns the bus and writes to memory. During an lack cycle, pins do D7 present the interrupt vector number to the host with timing identical to an odd address read. For operation with the 8-bit 68008 bus, see UDS and LDS pin descriptions below. 4.1.1.2 Control Bus. R/W, read/write. This bidirectional pin controls the direction of data flow on the data pins. High indicates that the bus cycle is a read cycle and low indicates a write cycle. While the host owns the bus, this pin is an input. While the DDLC owns the bus, this pin is an output. At the end of a DMA cycle, this pin is pulled high for 1/2 MCLK cycle before going high impedance. As address strobe. This bidirectional pin is an output while the DDLC owns the bus. It is the address strobe which indicates, while active, that there is a valid address on the bus. During a bus arbitration cycle after BG has been asserted, as is an input which is used along with BGAC to determine if the DDLC has been given ownership of the bus. At the end of a DMA cycle, this pin is pulled high for 1/2 MCLK cycle before going high impedance. UDS and LOS, upper and lower data strobes. These bidirectional pins are outputs when the DDLC owns the bus and inputs while the host owns the bus. These pins are data strobes which indicate that data on the bus is valid. When UDS is low, it indicates that data on the bus in the upper byte, D8 D15, is valid. When LDS is low, it indicates that data on the bus in the lower byte, do D7, is valid. When both UDS and LDS are low, all 16 bits on the data bus are valid and a word transaction is performed. Data is latched into the DDLC on the rising edge of these signals. In the 8-bit bus mode, UDS becomes the AO, address 0, pin and LDS becomes the DS, data strobe, pin. At the end of a DMA cycle, these pins are pulled high for 1/2 MCLK cycle before going high. Impedance. DAC, data transfer acknowledge. This bidirectional pin is an output when the host owns the bus. It indicates that the DDLC has completed the data transfer, either read or write, and the host processor may terminate the access cycle. While the DDLC owns the bus, this pin is an input and is sampled on the rising edge of state 4. If DAC is detected high, inactive, wait states are inserted. The pin is sampled on every rising edge of MCLK while wait states are inserted until a logic low is found, at which time the DDLC terminates its access cycle normally. At the end of a DMA cycle, an active pull-up device is momentarily enabled before going high impedance. Motorola 422 MC145488 4.1.1.3 Bus Arbitration. BR, Bus Request. This active low open drain pin is an output indicating that the DDLC is requesting the bus from the present bus owner. It is negated after the DDLC has asserted BGAC, so the next bus master may begin negotiation for ownership of the bus. In 8-bit 68008 systems, BGAC and BR should be connected together, producing the required BR function. BG, bus grant. This input is sampled on MCLK falling edges by the DDLC after BR has been asserted. While BG is active, it indicates that the bus ownership will be transferred to the DDLC. BGAC, bus grant acknowledge. This bidirectional pin is an active low open drain output while the DDLC is indicating that it has taken ownership of the system bus. Before the DDLC can assume bus ownership, it monitors BGAC and S. After BG has been asserted to a logic low and waits for BGAC and S to be negated, indicating that the present owner has relinquished control of the bus. An internal pull-up device is momentarily activated when this pin is negated to improve rise time. This pin is also used to select 68,000 or 80,186 modes of operation. To select the 68,000 mode, a pull-up resistor is connected from this pin to VDD. The level of this pin is internally latched upon exiting the reset state and remains until the DDLC is again reset, hardware or software. Own 0, bus owner channel 0. This active low output pin indicates that channel 0 of the DDLC has ownership of the bus. It is similar to the BGAC pin, but is intended for use by an external function code generator or address expansion circuit. At the end of a DMA cycle, this pin is pulled high for 112 MCLK cycle before going high impedance. This pin is driven high during DMA cycles associated with channel 1. Own 1, bus owner channel 1. This active low output pin indicates that channel 1 of the DDLC has ownership of the bus. It is similar to the BGAC pin, but is intended for use by an external function code generator or address expansion circuit. At the end of a DMA cycle, this pin is pulled high for 1/2 MCLK cycle before going high impedance. This pin is driven high during DMA cycles associated with channel 0. 4.1.1.4 Interrupt signals. IRQ, interrupt request. This active low open drain output indicates that the DDLC has a pending interrupt to the host processor. It remains low as long as there is at least one pending interrupt. LAC, interrupt acknowledge. This input is similar to the CS pin, except that while it is activated, the interrupt vector number is placed on the data bus in the lower byte, do D7. During the LAC cycle, the CS or address pins are not used. But the timing of the vector fetch is the same as a normal odd address read. If IRQ is high, no interrupt is pending, while LAC is asserted, or if LAC and CS are active at the same time, LAC is ignored. MC145488 Motorola 4-3 4.1.1.5 Miscellaneous signals. MCLK, MPU clock. This input is the master clock for the DDLC. It operates from DC to 12.5 MHz. All timing states are derived from this clock. Normally, the source of this signal is the microprocessor's master system clock. The DDLC expects a clock signal of nominal 50% duty cycle. All other clock inputs to the DDLC may be asynchronous to this clock. Burp, bus error. This input is used to pass the status of the MPU bus to the DDLC while the DDLC owns the bus. It is sampled on every falling edge of MCLK after bus state 2 until DAC is active. If a bus error is detected while the DDLC owns the bus, the DMA channel that was active when the error was found is disabled, and an interrupt is queued. RST, reset. This bidirectional active low pin is used to reset all internal state machines and selected registers to known states and values. All bus interface pins go high impedance while the reset line is active. While the watchdog timer is enabled, if the timer underflows to FF hex, this pin becomes an open drain output and goes low for 16 MCLK cycles. This is intended to reset the entire host system. CS, chip select. This input, while at a logic low, indicates that the base address of the DDLC has been selected and the internal address decode logic selects a register for a read or write access cycle. If this pin is detected active while the DDLC owns the bus, an address error is assumed. 4.1.280,186 Operation. This mode is selected by connecting BGAC, pin 41, to VSS. The logic level of this pin is internally latched when the DDLC exits the reset state. Table 4-2 describes the pin functions in the 80,186 mode. Motorola 4 to 4. Table 4 to 2. 80,186 mode pin functions. Signal name mnemonic input/output. Active. Driver type. State. Address bus AIAI5 input/output 3 state. Data bus do div5 input/output 3 state. Master clock MCLK input. Chip select CS input low. Right strobe WR input/output low 3 state star. Address 0AO input/output 3 state star. High byte enable BHE input/output low 3 state star. Read/write R/W input/output high/low 3 state star. Ready ROI input low. Hold request HREQ output low open drain. Hold acknowledge hack input low. 80,186 select 186 input low. Bus owner 0 own 0 output low 3 state star. Bus owner I own 1 output low 3 state star. Interrupt request IRQ output low open drain. I interrupt acknowledge lack input low. Reset RST input/output low open drain. Read strobe RD input/output low 3 state star. Asterisk these pins have an internal pull-up device momentarily activated immediately before going high. Impt ANS for improved rise time. MC145488. 4.1.2.1 address and data bus. AOA15 address bus. These bidirectional pins are the address lines. While the DDLC is a bus master, these pins are outputs. They present the address of the memory location to be read or written. While the DDLC is a bus slave. These pins are inputs. The internal registers are accessed by placing the address of the selected register on the bus and then reading or writing the register's contents. While these pins are inputs, only the lower 7 bits are decoded and the upper 9 bits are thus don't. Do D15 data bus. These bidirectional pins are the data lines. They are inputs while the host owns the bus and writes to the DDLC, or while the DDLC owns the bus and reads a memory location. They are outputs while the host owns the bus and reads the DDLC, or while the DDLC owns the bus and writes to memory. During an LAC cycle, pins 00-07 present the interrupt vector number to the host. 4.1.2.2 Control bus. RD, read strobe. This bidirectional active low pin indicates that the address on the bus is valid and the bus owner will input data on the rising edge of the signal. This pin is an input while the DDLC is in the host processor mode, and an output while in the DMA mode. During DMA operation, an internal pull-up device is momentarily activated when this pin is negated to improve rise time. WR, write strobe. This bidirectional active low pin indicates that the address and data on the bus is valid. The addressed device should latch the data on the rising edge of the signal, while the DDLC is in the host processor mode. This pin is an input, while in the DMA mode, this pin is an output. During DMA operation, an internal pull-up device is momentarily activated when this pin is negated to improve rise time. R/W, read/write control. This 3-state output pin is intended to control the direction of external bus transceivers. The DDLC is performing a memory read while this pin is high and a memory write while this pin is low. This pin has an internal pull-up device activated for 1/2 MCLK cycle before going high impedance at the end of a DMA access. While the DDLC is not the bus owner, this pin is high impedance. BHE, high byte enable. This bidirectional active low pin indicates that the data on 08-015 pins is valid. This pin is an input while the DDLC is in the host processor mode and an output in the DMA mode and is used only for 16-bit Operation. During DMA operation, an internal pull-up device is momentarily activated while this pin is negated to improve rise time. RDY, ready. This active low pin is an input in the DMA mode. Memory signals that it is ready to complete a DMA cycle by asserting this pin. This pin is not used in the host processor mode. 4.1.2.3 Bus arbitration. HREQ, hold request. This active low output pin indicates that the DDLC is requesting ownership of the bus. It remains asserted. For as long as the DDLC owns the bus, then it is negated. MC145488 Motorola. 4-5. Hack, hold acknowledge. This active low input is used to determine when the DDLC has been granted bus ownership. The DMA controller samples this pin while HREQ is asserted, and when found asserted for 2 sample periods, the DMA cycle begins. Own 0, bus owner channel 0. This active low output pin indicates that channel 0 of the DDLC has ownership of the bus. It is intended for use by an external function code generator and address expansion circuitry and remains asserted as long as the DDLC owns the bus. An internal pull-up device is momentarily activated when this pin is negated to improve rise time. This pin is driven high when Own 1 is active. Own 1, bus owner channel 1. This active low output pin indicates that channel 1 of the DDLC has ownership of the bus. It is intended for use by an external function code generator and address expansion circuitry and remains asserted as long as the DDLC owns the bus. An internal pull-up device is momentarily activated when this pin is negated to improve rise time. This pin is driven high when Own 0 is active. 4.1.2.4 Interrupt signals. IRQ, interrupt request. This active low open drain output indicates that the DDLC has a pending interrupt to the host processor. It remains low as long as there is at least one pending interrupt. LAC, interrupt acknowledge. This input is similar to the CS pin, except that when it is activated, the interrupt vector number is placed on the data bus in the lower byte, 00-07. During the LAC cycle, the CS or address pins are not used. But the timing of the vector fetch is the same as a normal odd address read. If IRQ is high, no interrupt is pending when LAC is asserted, or if LAC and CS are active at the same time, LAC is ignored. 4.1.2.5 Miscellaneous signals. MCLK, master clock. This input is the master clock for the DDLC. It operates from DC to 12.5 MHz. All timing states are derived from this clock. Normally, the source of this signal is the microprocessor's master system clock. The DDLC expects a clock signal of nominal 50% duty cycle. All other clock inputs to the DDLC may be asynchronous to this clock. RST, reset. This bidirectional active low pin is used to reset all internal state machines and selected registers to known states and values. All bus interface pins go high impedance while the reset line is active. While the watchdog timer is enabled, this pin becomes an open drain output if the timer underflows and goes low. For 16 MCLK cycles. This is intended to reset the entire host system. CS, chip select. This input, while at a logic low, indicates that the base address of the DDLC has been selected and the internal address decode logic selects a register for a read or write access cycle. If this pin is detected active while the DDLC owns the bus, an address error is assumed. Motorola. 4-6. MC145488. 4.2 Serial Communication Pins. Table 4-3 describes the various names of the serial communication pins. The pin number is in the left column and the several operational modes are in the top row. Some pins, primarily the modem control pins, change function as the operating modes are changed. While the SCP is enabled, modem control pins on channel 0 assume SCP functions. The SCP can be selected independently of any other mode, except for the transparent modem mode where the byte sync pins become SCP functions. When the SCP is not activated, SCP-N0 may be used as a general purpose output, GPO. Table 4-3. Serial Interface Pins. PLCC. IDLB mode, IDLD mode, time slot mode, packet modem. Transparent. SCP enabled. Pin modem. Channel 1. 44 IDL sync 1, I, IDL sync, I, RxCLK1, I, RxCLK1, I, RxCLK1, I, note, I. 46 IDLCLK1, I, IDLCLK1, I, TXCLK1, I, TXCLK1, I, TXCLK1, I, note, I. 46 CFS1, I, DGNT1, I, TXEN1, I, CFS1, I, TXBSYNC1, I, note, I. 47 RTS1, 0, DREO1, 0, RISE1, 0, RTS1, 0, RTS1, 0, note, 0. 4B IDLRX1, I, IDLRX1, I, RXD1, I, RXD1, I, RXD1, I, note, I. 49 IDLTX1, 0, IDLTX1, 0, TXD1, 0, TXD1, 0, TXD1, 0, note, 0. 50 CD1, I, CD1, I, RXN1, I, CD1, I, RXBSYNC1, I, SCPN1, 0. 53 GPO, 0, GPO, 0, GPO, 0, GPO, 0, GPO, 0, SCPN0, IO. Channel 0. 54 CDO, I, CDO, I, RXN0, I, CDO, I, RXBSYNC0, I, SCPTXD, 0. 55 IDLTX0, 0, IDLTX0, 0, TXDO, 0, TXD0, 0, TXD0, 0, note, 0. 56 IDLRX0, I, IDLRX0, I, RXD0, I, RXD0, I, RXDO, I, note, I. 57 RTSO, 0, TRIO, 0, RTSO, 0, ARISE 0, 0, ARISE 0, 0, SCPCLK, IO. 68 CFS0, I, NTO, I, TXN0, I, CTS0, I, TXBSYNC0, I, SCPRXD, I. 59 IDLCLK0, I, IDLCLK0, I, TXCLK0, I, TXCLK0, I, TXCLK0, I, note, I. 60 IDL sync 0, I, IDL sync 0, I, RXCLK0, I, RXCLK0, I, RXCLK0, I, note, I. Note, functionality of this pin is not affected by SCP enable. I, indicates input, 0, indicates output. 4.2.1 IDL bus mode. In the IDL mode, each channel has 6 pins allocated to serial communication with an external data transceiver, typically the MC145488 SIT transceiver. Both channels' interfaces operate identically and are described together. Operation in the packet and transparent modes is identical from an interface point of view. IDL Sync 0, IDL Frame Synchronization Channel 0. IDL Sync 1, IDL Frame Synchronization Channel 1. This input synchronizes the operation of the serial interface circuitry to the IDL bus. A pulse 1 IDL clock period wide is presented to this pin every 125 ps. The synchronization pulse is rising edge aligned with the IDL CLK signal. IDL CLK 0, IDL clock channel 0. IDL CLK 1, IDL clock channel 1. This input is a clock signal typically at 1.544, 2.048, or 2.56 MHz, although any frequency between 1.5 and 4.5 MHz will operate properly. This signal is expected to be nominally 50% duty cycle. It normally is asynchronous to the MCLK signal. MC145488 Motorola 427 IDL RX0, LDL Receive Data Channel 0. IDL RX1, LDL Receive Data Channel 1. Data from the IDL bus is input on this pin. Data bits are presented to this pin on rising edges of the IDL CLK and latched into the DDLC on falling edges. This pin ignores all bit times other than the ones it is programmed to receive. IDL TX0, LDL Transmit Data Channel 0. IDL TX1, LDL Transmit Data Channel 1. Data is output onto the IDL bus from this pin. Data bits are presented on the rising edges of the IDL CLK. Data bits are presented only in the selected time slots in the IDL frame. At all other times this pin is high impedance. When the TE bit is 0, this pin is always high impedance. DREO 0, D channel request channel 0. DREO 1, D channel request channel 1. In the IDL D channel mode, this active high output indicates to the layer 1 transceiver that the DDLC has a frame of data to transmit on the D channel. When the frame has been transmitted, the DDLC negates DREQ to a logic low. If a frame in transmission is aborted by the layer 1 device, the DDLC negates DREQ to a logic low and recycles the frame for retransmission. When the frame is again ready for transmission, DREQ is set to a logic 1. In the IDL B channel mode, this pin assumes the functionality of RTS. See section 4.2.3. DGNT 0, D channel grant channel 0. DGNT 1, D channel grant channel 1. In the IDL D channel mode, this input indicates to the DDLC that the layer 1 transceiver is granting permission for the DDLC to transmit on the D channel. The first bit of the data frame is transmitted during the IDL frame immediately following the assertion of DGNT. If DGNT is found negated while DREQ is asserted, the frame in transmission is aborted and the DMA pointers are reset to prepare for retransmission. In the IDL B channel mode, this pin assumes the functionality of CTS. See section 4.2.3. 4.2.2 Time Slot Mode. The time slot mode is compatible with most PBX type PCM highways. The two channels are independent. Additionally, the transmitter and receiver of each channel may be clocked from a different source. There is no frequency or phase relationship required between transmit and receive clocks. The two channels are identical in operation, so pins of like function are described together. Operation in the packet and transparent modes is identical from an interface point of view. TXCLK0, transmit clock channel 0. TXCLK1, transmit clock channel 1. This signal is the clock for the transmitted data. Data bits are shifted on rising clock edges. This signal must be a continuous clock with a nominal 50% duty cycle. TXN0, transmit enable channel 0. TXN1, transmit enable channel 1. This signal is an active high enable which synchronizes the transmitter to the 8-bit times of a time slot. The enable may be of two different types, short frame and long frame. In short frame operation, the enable is a positive pulse, 1 TXCLK period wide, which immediately precedes the 8-bit time slot. The edges of the pulse are aligned with the rising clock edge. In long frame operation, the enable is a positive pulse, which is 8-bit times wide. The 8 data bits of a time slot are transmitted while the enable is high. Rising and falling edges of the enable are aligned to rising edges of the clock. The DDLC automatically. Motorola 428. MC145488. Senses either short or long frame operation and adjusts its timing for the next 8-bit time slot. See Section 6.2 for a further discussion. TXD0, transmit data channel 0. TXD1, transmit data channel 1. This signal is the transmitted data. Data is presented on the 8 bits of a time slot on rising clock edges. During periods outside of the time slot or when the TE bit is 0, the signal is high impedance. RxCLK0, receive clock channel 0. RxCLK1, receive clock channel 1. This signal is the clock for the received data. Data bits are sampled on falling clock edges. This signal must be a continuous clock with a nominal 50% duty cycle. RxN0, receive enable channel 0. RxN1, receive enable channel 1. This signal is an active high enable which synchronizes the receiver to the 8-bit times of a time slot. Like TX enable, the signal may be of two different types, short frame and long frame. Operation is essentially similar to TX enable. RxD0, receive data channel 0. RxD1, receive data channel 1. Received data is applied to this pin. This pin is sampled on falling edges of the RxCLK during the time slot. During all other periods, this pin is ignored. 4.2.3 Modem mode, packet operation. The modem mode is a general-purpose interface which is compatible with most modems. Logic levels are inverted from the IDL and time slot modes because inverting transceivers, such as EIA232 devices, are normally used. Operation in the transparent mode is different from packet mode and is described in the next section. As with the time slot mode, transmit and receive are independent and have no mutual clocking. Requirements: TXCLK0, transmit clock channel 0. TXCLK1, transmit clock channel 1. This signal is the clock for the transmitter. The transmitter emits a new data bit on every falling clock edge while RTS and CTS are both at a logic low. This signal may be any frequency from 0 Hz to MCLK/2. TXD0, transmit data channel 0. TXD1, transmit data channel 1. This signal is the transmitted data output. Data is output on every falling clock edge while both RTS and CTS are both at a logic low. While either RTS or CTS are at a logic high, this pin outputs a logic high. RxCLK0, receive clock channel 0. RxCLK1, receive clock channel 1. This signal is the clock for the receiver and may be any frequency from 0 Hz to MCLK/2. RxD0, receive data channel 0. RxD1, receive data channel 1. This is the data input for the receiver. It samples this pin on every rising clock edge while the receiver is enabled. MC145488 Motorola 4 to 9. RTS0, request to send channel 0. RTS1, request to send channel 1. This output, while at a logic low, indicates that the transmitter has been enabled by setting the TE bit. Once the transmitter is enabled, this signal remains low until the transmitter is disabled by the TE bit. Transmission begins when both RTS and CTS are low and when data is ready. CTS 0, clear to send channel 0. CTS 1, clear to send channel 1. The transmitter transmits packet data while the signal is low. If this signal goes high for more than 1 bit time, the packet in transmission is aborted and retransmitted in its entirety when CTS again goes low. CD0, carrier detect channel 0. CD1, carrier detect channel 1. This input is a general purpose input. For modem applications, this input is used to indicate when the carrier is active. This pin changes function while the SCP is enabled or while transparent operation is selected. See sections 4.2.4 and 4.2.5 for a further description. 4.2.4 Modem mode, transparent operation. When transparent operation is selected, 5 of the 7 serial interface pins retain their packet operation functionality. CTS and CD change operation to enable a byte synchronization signal to the transmitter and receiver respectively. TXBSYNC0, transmit byte sync channel 0. TXBSYNC1, transmit byte sync channel 1. This input is used to pass byte synchronization information to the transmitter. This pin is sampled on rising TXCLK edges and when found low for one sample, 1-1/2 TXCLK edges, on a falling edge, later the first bit of a byte is transmitted. Synchronization is maintained in the absence of subsequent sync signals. If another sync signal is detected, the transmitter resynchronizes to that signal regardless of its alignment to previous sync signals. See section 6.3 for further details. RxBSYNC0, receive byte sync channel 0. RxBSYNC1, receive byte sync channel 1. This input is used to pass byte synchronization information to the receiver. This pin is sampled on rising RxCLK edges and when found low for one sample, 1-1/2 RxCLK edges later, on a rising edge, a byte boundary is defined. RxBSYNC actually resets a module 0-8 counter in the DDLC so synchronization is maintained in the absence of subsequent sync signals. If sync pulses occur more often than every 8 RxCLKs, the internal counter will never generate a load signal to the FIFO and data will never be placed in memory. See section 6.3 for further details. 4.2.5 Serial Control Port. When the Serial Control Port, SCP, is enabled, SCPE high in the channel 0 Serial Interface Control Register. Some serial interface pins change functionality to the SCP mode. When the SCP is enabled, SCP functions override any other selected function. See section 6.4 for a further discussion. SCP N0, SCP enable 0, master mode. Slave select, slave mode. In the SCP master mode, this pin is an open drain output. It is normally high except when an SCP transmission is in progress when this pin is programmed to a logic low for the duration of the 8-bit SCP. Exchange. This pin is controlled by the ENO bit in the SCP status/control register. When ENO is high, Motorola 4 to 10, MC145488. SCP-N0 is low. When ENO is low, SCP-N0 is high. This pin may be used as a general-purpose output, as it is not multiplexed with any other function and always available. In the SCP slave mode, this pin is an input which indicates that the DDLC has been selected for a transfer. The external SCP master must not enable this pin while the SCP CLK is in the active state, 1 while CI is 0 and 0 while CI is 1. An interrupt is generated on the rising edge of the signal. SCP-N1, SCP-Enable1. This active low output pin is an enable signal for the SCPO. This pin is normally high except when an SCP transmission is in progress, when this pin goes to a logic low for the duration of the A-bit SCP exchange. This pin is controlled by the ENO bit in the SCP status/control register. When N1 is high, SCP-N1 is low. When N1 is low, SCP-N1 is high. This pin is not affected by SCP master or slave operation. SCP-CLK, SCP clock. In the master mode, this pin is an output which is the clock for the SCPO. It is derived from the MCLK pin. And the baud rate is selected by the SCP baud rate select bits in the SCP status/control register. The polarity of the signal is selectable by the CI bit, so data bits may be input or output on either but opposite edges. When the TX bit is set, a burst of 8 clock pulses is generated. In the slave mode, this pin is the clock input to the SCPO. Any frequency between 0 Hz and MCLK is acceptable for proper operation. This clock may be continuous or gated. SCP-RxD, SCP receive data. This input latches new SCP data on edges of the SCP CLK as selected by the CI bit in the SCP status/control register. SCP-TXD, SCP transmit data. This output presents new data bits on SCP CLK edges as selected by the CI bit of the SCP status/control register. 4.3 Power supply. VDD, the most positive power supply pin, normally plus 5V with respect to VSS. There are 3 VDD pins on the DDLC. VSS, the most negative power supply pin, normally 0V. There are 3 VSS pins on the DDLC. Pins 2 and 35 are VDD and VSS respectively for the DMA and MPU sections of the chip. Pins 9 and 21 are VDD and VSS respectively for the pin drivers which can sync and source high peak currents. Pin 52 is VDD and pin 51 is VSS for the serial interface and bit handler sections. Powering the separate sections of the chip in this manner helps minimize noise problems arising from asynchronous clocking schemes. Recall that normally the serial sections are asynchronous from the MPU/DMA sections. Section 9 shows the pin assignments for the MC145488. MC145488 Motorola 4 to 11. Motorola 4 to 12. Table 4 to 4. MPU interface pin names. PLCC 68,000 mode, 80,186 mode. Pin I 61 address 15 address 15. 62 address 14 address 14. 63 address 13 address 13. 64 address 12 address 12. 65 address 11 address 11. 66 address 10 address 10. FF7 address 9 address 9. 68 address 8 address 8. 1 address 7 address 7. 3 address 6 address 6. 4 address 5 address 5. 5 address 4 address 4. 6 address 3 address 3. 7 address 2 address 2. 8 address 1 address 1. 10 data 0 data 0. 11 data 1 data 1. 12 data 2 data 2. 13 data 3 data 3. 14 data 4 data 4. 15 data 5 data 5. 16 data 6 data 6. 17 data 7 data 7. 18 data 8 data 8. 19 data 9 data 9. 20 data 10 data 10. 22 data 11 data 11. 23 data 12 data 12. 24 data 13 data 13. 25 data 14 data 14. 26 data 15 data 15. 27 master clock master clock. 28 chip select chip select. 29 read/write read/write. 30 address strobe write strobe. 31 lower data strobe high byte enable. 32 upper data strobe address 0. 33 reset reset. 34 interrupt acknowledge interrupt acknowledge. 36 interrupt request interrupt request. 37 data transfer acknowledge ready. 38 bus error read strobe. 39 bus request hold request. 40 bus grant hold acknowledge. 41 bus grant acknowledge 80,186 select. 42 owner 0 owner 0. 43 owner 1 owner 1. MC145488. Section 5. Bus operation. This section describes the operation of the DDLC microprocessor interface in the Motorola 68000 environment and the Intel 80186 environment during host processor operation, DMA operation, bus arbitration, and interrupt operation. Functional timing diagrams are included to clarify the timing of the various operations, but are not intended to be parametric definitions. For detailed timing parameters, see seconds. Section 8. In the discussions that follow, the words assert and negate are used extensively. They indicate the logical value of the signal regardless of whether the voltage level on the pin is high or low. 5.168,000 System operation. Operation in the Motorola 68000 environment is chosen by providing a pull-up resistor from the BGAC pin to VDD. When the DDLC exits the reset state, either hardware or software, the level on the BGAC pin is internally latched. This requires that any other BGAC pins in the system be high impedance or at a logic high during reset. The following sections describe the operation of the DDLC in the 68000 mode. The DDLC can operate in either a 16-bit or an 8-bit system. All DDLC MPU interface circuitry timing is derived from the MCLK pin. Normally this pin will be connected to the host's master clock, but it may operate asynchronously to the host if all bus timing requirements are satisfied. In the timing diagrams that follow, MCLK is assumed to be identical to the host's clock. A few words are needed to describe the 68000 memory architecture. All memory may be thought of as 16-bit wide word locations which reside only on even addresses. However, the 68000 does have the capability of accessing bytes. Most significant bytes are located on even byte addresses and least significant bytes are located on odd byte addresses. For example, if the base address of the DDLC is placed at A100 hex, the system control register will be located at address A100, the master status register will be located at A102, and so on. The interrupt number, bits B7, of the master status register is actually located at address A103. This address is not directly accessible by the 68,000 since there is no AO address line to indicate even or odd addresses. Two data strobe pins are provided to solve this dilemma. Upper data strobe, UDS, indicates when asserted that the most significant byte on the 16-bit data bus is active, and lower data strobe, LDS, indicates when asserted that the least significant byte on the bus is active. If the interrupt vector is read in a byte-wide operation, only the LDS pin would be asserted, indicating that the least significant, odd, byte is valid. This is effectively address A103. For word-wide, 16 bits, operations, both UDS and LDS are asserted, indicating that the entire 16-bit word is active. For 8-bit 68008 systems, the memory architecture is composed of 8-bit locations. Even and odd addresses are used, so an AO pin is provided to access every byte. When the DDLC is used in the 68008 mode, the UDS pin becomes the least significant address pin, AO, and LDS becomes the data strobe, DS. The DDLC's internal 16-bit bus is converted to an external 8-bit bus which is active on pins D7. Pins D8, D15 become deactivated. MC145488 Motorola 5:1 5.1.1 bus width selection. The DDLC is in the 8-bit mode after reset. To remain in 8-bit mode, it is recommended that 08 of the data bus be connected to VSS 16-bit operation is selected by writing FFFF to address 6. Address 6 is a dummy register which is used to qualify 16-bit operation. Once the 16-bit mode is selected, it is internally latched until the DDLC is reset by pulling the RST pin low. The software reset does not clear 16-bit operation. 5.1.2 Host operation. The DDLC is in the host processor mode when it is a memory mapped slave peripheral to the bus master. Anytime the DDLC is not a bus master, actually performing a DMA access, the CS and LAC pins are continually sampled. A read or write cycle begins immediately when either of these pins are detected in the asserted state. The DDLC either accepts or presents data from or to the bus, depending on the level of the R/W pin. All internal registers are accessible to the host as decoded by address pins A1 A6. Operation of the LAC pin is similar to a read cycle and is described in section 5.3.4. 5.1.2.1 Write cycle. During a host processor write cycle, the DDLC accepts data from the host and places it into the selected register. All internal registers are writable with the exception of the frame length registers which are read-only. Figure 5:1 illustrates the timing relationships between the various bus interface pins in a typical 68,000 write cycle. Timing is identical for even byte, odd byte, or word operations, so the UDS and LOS pins are shown together. If an unoccupied internal address is selected, the DDLC will not indicate an error condition and the written data will be lost. While in the MPU mode of operation, the DDLC samples CS on falling edges of the MCLK. A write cycle begins on the MCLK edge on which CS is first detected low with R/W low. On the next rising MCLK edge, the address is latched and DAC is asserted. Then data is allowed to enter the internal bus. When the data strobes, UDS and / or LOS, are asserted, the latch of the selected register is opened and the data enters the register. The register's latch is closed off and the data is retained when the data strobes are negated. When CS is negated, DAC is negated and the cycle is complete. DAC is an open drain. Motorola 522 MCLK CS AIA6 UDS LOS DO 015 DAC Relay So S2 S4 S6 // X valid X / X valid C output // J / R figure 5:1 68,000 host write cycle MC145488 So S2 S4 S6 MCLK CS / AIA6 X valid X UOS LOS // 00-015 DAC output / RIW figure 5:2 68,000 host read cycle output in the MPU mode. When it is negated, a pull-up device is momentarily connected to provide a fast rise time. CS must return to a negated state for at least one MCLK cycle before another DDLC access cycle may begin. 5.1.2.2 Read cycle. During a host processor read cycle, the DDLC places data from the selected internal register onto the data bus. All internal registers of the DDLC are readable. Figure 5:2 describes the timing of a typical 68,000 read cycle. Timing is identical for even byte, odd byte, or word operations. If the host selects an unoccupied internal register, the DDLC will not indicate an error and will place unknown data on the bus. In the 16-bit mode, the DDLC always presents 16 bits to the bus regardless of which data strobe pin, UDS or LOS, was asserted during the cycle. A read cycle begins when CS and the data strobes are asserted and R/W is high. The DDLC decodes a 1A6 and selects a register and outputs the data on the rising MCLK edge after CS was detected. Asserted, DAC is asserted. DAC is negated after the rising edge of CS and the cycle is complete. In some systems, the data strobes will be delayed from CS. When this occurs, the data will be placed on the bus when the data strobes are asserted. 5.1.3 DMA operation. In the DMA mode, the DDLC operates as a system bus master. When the internal FIFOs need data or have data to place in memory, the DDLC's DMA controller requests ownership of the system bus. When ownership is granted, the DDLC takes control of the bus and executes a memory cycle. The DDLC services one DMA request, then relinquishes the bus. If another DMA request is pending internally, the DDLC will not re-request the bus for at least 3 MCLK cycles after the bus has been relinquished from the previous access. The internal address generators can operate on address ranges of up to 64 KB. 2 pins, OWN0 and OWN1 are provided to indicate which communication channel is the bus owner. These signals may be used to control an external device, such as an address page register onto the address bus, so each channel may operate on a different memory page. While a DMA cycle is in progress, only one OWN pin will be asserted. The other will be driven to a logic high. For the duration of the DMA cycle. For systems that MC145488 Motorola 523 need them, function codes may also be enabled with the OWN pins. Section 7 describes applications for these pins. Note, in 16-bit systems, the DDLC does not check for odd word boundaries or generate odd word addresses. The system designer must ensure that the DDLC is not supplied with odd pointers in 16-bit systems. For 8-bit systems, odd byte addresses are proper and the AO address pin selects even or odd bytes. For both 16-bit and 8-bit systems, it is suggested that the programmer use only even addresses for transmit and receive buffers and even lengths for receive buffers. This will maintain software compatibility between the two systems. In the following descriptions, MCLK cycles are used as a reference. All internal timing is generated from the MCLK. The MCLK used by the DDLC is not necessarily synchronous to the host's clock. Correct operation of the DDLC in a system is maintained if the proper synchronization times are met for input pins. 5.1.3.1 DMA write cycle. A DMA write cycle is performed when a receiver FIFO has data to be placed in a buffer in memory. Figure 5.2.3 describes the timing of a DDLC write cycle. Bus arbitration is assumed to have been completed before the cycle begins. 80, 81, 82, 83, S4, 85. MCLK as \r LAI5 U08 L08 /r 00-015 OTAC input /TI RNI /F own // Figure 5.2.3 68,000 DMA write cycle. A DMA write cycle is 3 MCLK periods long with the R/W level and address presented to the bus 1/2 clock early. At the beginning of so, data is presented to the bus and address strobe is asserted. On the next MCLK edge, the data strobes are asserted. In the 16-bit mode, the DDLC always makes 16-bit data transactions, so both strobes are asserted at the same time. DAC is sampled on the rising edge of 54, and if found asserted, the cycle is completed with as and the data strobes negated on the falling edge of 54. The address and R/W forced to high impedance on the rising edge of 55. All control bus pins have an internal active pull-up to provide a fast rise time before going high impedance. If DAC is inactive on the rising edge of 54, a wait state is inserted and DAC is resampled at the end of the wait state. This process continues until DAC is found active or until a bus error is found. Operation with the internal wait state generator is described in section 5.1.3.4. Motorola 5-4 MC145488. In 16-bit operation, all write transactions are 16 bits wide. For this reason, memory buffers should be an even number of bytes long. If a received frame is an odd number of bytes long, the last received byte will be written to memory in a 16-bit transaction. The data in the lower byte, higher byte address, in this case, will be unknown data. The received byte count will, however, indicate the correct number of bytes received. In the frame 5.1.3.2 DMA read cycle. The DDLC performs a DMA read cycle when a transmit FIFO needs data to transmit. Figure 5-4 describes the timing of a DDLC read cycle. Bus arbitration is assumed to be completed before the cycle begins. So SI, S2, S3, S4, S5. MCLK \O_J LAI5 los. \o underscore, j. 00-015-0. Input, \t, \riw, \__ Figure 5-4. 68,000 DMA read cycle. A DMA read cycle begins when the address is driven onto the bus and the R/W pin is driven high. 1. Half MCLK later, at the beginning of so, the address and data strobes are driven low. DAC is sampled on the rising edge of 54, and if found asserted the address and data strobes are negated on the falling edge of 54 and the data is latched into the FIFO. 1/2 MCLK later, the address pins and R/W pin go high impedance. If DAC is inactive on the rising edge of 54, a wait state is inserted and DAC is resampled at the end of the wait state. This process continues until DAC is found active or a bus error is found. Operation with the internal wait state generator is described in section 5.1.3.4. As with DMA write cycles, all DMA read transactions in the 16-bit mode are 16 bits wide. If only 8 bits of data are needed, for an odd byte length frame, the extra byte that was read is discarded. 5.1.3.3 Bus Error Recovery. The DDLC provides a bus error pin for systems that detect bus errors. The Burp pin is sampled at the same time as DAC, and if Burp is found to be asserted, the DDLC resamples Burp 1/2 clock period later to qualify it. If Burp is found to still be asserted, the DDLC terminates the DMA cycle and queues an interrupt. For DMA write cycles, associated with the receiver, the receiver's RxN bit is cleared to reset the receiver. For DMA read cycles, associated with the transmitter, the transmitter's BR bit is cleared to disable further DMA requests from that channel. The transmitter is still enabled and will enter the idle state after transmitting an abort character. MC145488 Motorola 5-5. The DDLC also responds to address errors which are defined as the assertion of CS or lack while the DDLC is in a DMA cycle. The CS and lack pins are sampled at the same time as Burp and if found asserted, an address error is declared and an interrupt is queued. 5.1.3.4 Wait State Generator and DAC Control. The DDLC provides a programmable internal wait state generator for systems that have slow memory. The wait state generator inserts wait states before S4 which are essentially equivalent to repeated S2, S3 states. 4 wait state selections are available including 0, 1, 2, or 4 wait states. Additionally, DAC may be enabled to operate with the wait state generator, so DAC is sampled after the wait states have been executed. The cycle then terminates only after DAC is asserted. The DAC pin may be internally disabled so the DMA cycle will terminate after the wait states have executed regardless of the state of DAC. Figure 5-5 describes the operation of the wait state generator or with one programmed wait state and a delayed DAC signal. SP indicates programmed wait states and SW indicates wait states generated because of the delayed DAC signal. The downward pointing arrows indicate the sampling points for DAC. 80, 81, 82, 83, 8P, 8P, 84, 8WS4, 85. MCLK as \, LAI5, IIIIS, L08, \, do_diff5, black, input, T\1, RM, \I, figure 5-5, 68,000 DMA write cycle with one programmed wait state. And a delayed DAC. 5.1.4 Bus arbitration. An internal DMA scheduler continuously polls the 4 data channels for service requests. When a request is found, the scheduler prepares the data and address for the DMA access and requests the system bus from the current bus owner. Once the DDLC has ownership of the bus, it services one internal request, then relinquishes ownership of the bus. Figure 5-6 describes the operation of the 68,000 arbitration mechanism. 68,008 bus arbitration is slightly different in that only 2 pins are used for bus arbitration, BR and BG. When using the DDLC in a 68,008 system, the BGAC and BR pins should be connected together to provide the proper BR signal to the processor. The signal edges overlap so the combined signal will be glitch-free. Bus arbitration begins when the BR pin is asserted, indicating that the DDLC is requesting the bus. The DDLC then samples for BG to be asserted, GAC to be negated, and S to be negated on successive. Motorola 5.2.6 MC145488 MCLK edges. The upward pointing arrows indicate the sampling points of the 3 signals. When the signals are at the proper levels for 2 successive samples, the DDLC immediately assumes ownership of the bus and asserts BGAC, own 0, or own 1, sets the level of R/W and places the address on the bus. On the next rising edge, the cycle begins with the assertion of address strobe. At the end of the DMA cycle, the DDLC negates BGAC and the own pins. The DDLC will not re-request the bus for at least 3 MCLK cycles after relinquishing the bus, even if another internal DMA request is pending. This ensures that another DMA requesting device has access to the bus and that the DDLC will not be a bus hog. 5.280,186 System operation. The DDLC also can operate as an 80186/88 peripheral. This mode is entered by connecting the BGAC pin to VSS. The level of this pin is latched when the DDLC exits the reset state. The DDLC fully supports the 80186/88 bus structure, except that the address and data buses are not multiplexed. The DDLC is designed so that it will reside on the demultiplexed global bus of an Intel system. 5.2.1 Host processor operation. In this mode, the DDLC is a peripheral device to the 80,186 host processor. Internal registers may reside in either the I/O space or the memory space, depending on how the CS pin is decoded by external circuitry. The DDLC is in this mode of operation when either the CS or LAC pins are activated. Operation of the LAC pin is described in section 5.3.5. The ROI pin is an input and is thus not used in the host processor mode. The DDLC, however, appears to be fast memory and does not require wait states to be inserted by the host. The DDLC operates in an 8-bit or 16-bit mode. In the 8-bit mode, the BHE pin is unused, and the AO pin directs the data to the even or odd bytes of the internal registers. In the 16-bit mode, the registers are accessed on even addresses. Both AO and BHE are active low during a 16-bit access. Selection of 8-bit operation is described in section 5.1. MC145488 Motorola 5.2.7 5.2.1.1 Write cycle. During a write cycle, the DDLC accepts data from the data bus and places it into the selected register. Figure 5.2.7 describes the timing relationships of the various bus interface pins. as. With the 68,000 mode, data written to an unoccupied internal address is lost without indication. T1, T2, T3, T4. MCLK. CS. \/ BHE. XX. AOA6. XX. WR. \/ 00-015. XX. Figure 5 to 7.80186 host write cycle. A write cycle begins when the CS pin is activated and the address is on the bus. The WR pin is activated by the host and the internal circuitry selects the proper register for a write access. The data and address must be stable before WR is asserted, as this pin directly controls the latch function of the internal registers. Data is latched into the DDLC on the rising edge of WR. For byte accesses, the AO and BHE pins direct the DDLC's address decoder to the proper byte of the selected register. 5.2.1.2 Read cycle. During a host read cycle, the DDLC takes data from an addressed internal register and places it on the bus. Figure 5 to 8 describes the timing of a read cycle. If an unoccupied internal address is read, the DDLC will place unknown data on the bus. Motorola. 5 to 8. MCLK. CS. BHE. Add as. IW. 00-015. T1, T2, T3, T4. \/ XX. XX. \/ Figure 5 to 8. 80,186 host read cycle. MC145488. A read cycle begins when the CS pin is asserted. Data is available after CS is detected asserted. The RD pin directly controls the output drivers of the data pins, and when it is asserted, the data is placed on the bus. For byte accesses in a 16-bit system, the AO and BHE pins direct the DDLC's address decoder to the proper byte of the selected register. 5.2.2 DMA operation. In the DMA mode of operation, the DDLC is the system bus master. When an internal transmitter or receiver needs service, it generates an internal DMA request. The DMA controller calculates the address to be placed on the address bus and prepares the data to be placed on the data bus, if the request was from a receiver. Then the DDLC requests the system bus by asserting HREQ. When the system bus has been given to the DDLC, hack asserted, the internal DMA request is serviced with a single bus cycle. Then the bus is relinquished. There is one MCLK cycle between the time hack is asserted and the time the bus cycle begins. When the bus is relinquished, the next bus master should wait at least 1/2 MCLK cycle for the bus to settle before beginning its cycle. Note, in 16-bit systems, the DDLC does not have the capability of operating with odd address word boundaries. All word, 16-bit, accesses must be on even addresses. For 8-bit systems, either even or odd addresses are proper, but the programmer should start all buffers on even addresses to maintain compatibility with 16-bit systems. In 16-bit systems, the DDLC will always read or write 16-bit words from or to memory. In the case of a transmitted frame with an odd number of bytes, only the least significant valid byte of the last word read from the memory buffer will be used, and the most significant invalid byte will be discarded. For received odd byte length frames, the last received byte will be transferred to memory with a 16-bit write, and the least significant byte will contain the last received byte. The most significant byte will be unknown data. The receive byte count register always contains the correct number of bytes received. The DDLC automatically aligns the data, depending on whether the 68,000 or 80,186 mode is selected, so that succeeding received data bytes are placed in ascending order in memory. Transmitted bytes are retrieved from memory in ascending order and are internally rearranged so that they are transmitted in the correct order. 5.2.2.1 DMA write cycle. When the DDLC is the bus owner, a DMA write cycle may be performed to transfer data received from the serial bit handler to a memory buffer. Figure 5 to 9 describes the timing relationships of the various signals during a DMA write cycle in the 80,186 mode. The timing diagram assumes that bus arbitration was completed before the cycle started. A write cycle begins with the DDLC placing the address on the bus and asserting the own pin at the beginning of T1. On the rising edge during T1, the data is placed on the bus. At the beginning of T2, WR is asserted. The RDY pin is sampled on the rising edge of MCLK during T3 and if found asserted, the cycle is terminated with WR negated at the beginning of T4. On the next rising MCLK edge, the address and data are removed. Since the DDLC performs one transaction per bus request, all address, control, and data lines go high impedance at the end of the cycle. The DDLC has separate pins for address and data, so no demultiplexing control signals are required. R/W is provided to control the direction of a system bus transceiver. Note that one of the two own pins is asserted during every DMA cycle, so the own pins may be used to enable or disable other devices on the bus. The inactive own pin is driven to a logic high state while a DMA cycle is active. 5.2.2.2 DMA read cycle. A DMA read cycle is performed when a transmitter needs data. Timing is similar to a write cycle and is described in figure 5 to 10. MC145488 Motorola. 5 to 9. T1I, T2I, T3I, T4I, IT1I, T2I, T3I, T4I. MCLK, MCLK. AOA15. AOA15. RIW. RIW. Backslash, backslash. She. Backslash FL. RI. Backslash, backslash. 00-015. RDY. Input, backslash backslash TLZT. ROY. Input. Backslash backslash asterisk slash 11. Own. Backslash, backslash. Own. Backslash, backslash. Figure 5 to 9. 80,186 DMA write cycle figure 5 to 10. 80,186 DMA read cycle. A read cycle begins with the DDLC placing the address on the bus at the beginning of T1. At the beginning of T2, RD is asserted. On the rising MCLK edge during T3, RDY is sampled and if found asserted, the cycle completes with RD being negated at the beginning of T4. Data is latched into the DDLC on the rising edge of RD. On the rising MCLK edge during T4, the address is removed from the bus and all address, control, and data lines go to the high impedance state. The operation of the RDY pin is described in section 5.2.2.3. 5.2.2.3 Wait state generator and ready control. The DDLC provides a programmable internal wait state generator for systems that have slow memory. The wait state generator inserts wait States before the rising MCLK edge during T3 which are essentially equivalent to repeating the second half of T2 and the first half of T3. 4 wait state selections are available including 0, 1, 2, or 4 wait states. Additionally, the RDY pin may be enabled with the wait state generator so RDY will be sampled after the wait states have been executed and the cycle will terminate when RDY is found to be asserted. RDY can be internally enabled in which case the DMA cycle will terminate after the wait states have been run regardless of the state of RDY. Figure 5-11 describes the operation of the wait state generator with one programmed wait state and a delayed RDY signal in a read cycle. TP indicates the programmed wait state. T3 is repeated because when RDY was sampled the first time, it was not asserted. The downward pointing arrows indicate the sampling points for RDY. Operation in a write cycle is similar. 5.2.3 Bus arbitration. In the 80186 mode of operation, the DDLC uses a hold request/hold acknowledge bus arbitration protocol. When the DDLC has an internal DMA request, HREQ is activated. Hack is activated by the bus arbiter. When the DDLC has been granted ownership of the bus, the DDLC assumes ownership when hack is active and holds HREQ active until the DMA transaction has been completed. Figure 5-12 describes the operation of the bus arbitration pins on the DDLC. The own pins indicate that the DDLC is the bus owner and is activated after hack has been found asserted for 2 sample periods. The downward pointing arrows indicate the sample points for hack. Motorola 5-10 MC145488 11 IT2 IT3 IT4I MCLK AOAI5 BHE dash /F /00-015 ROI input /T 1/1 own // Figure 5-11.80186 DMA cycle with 1 programmed wait state and delayed RDY. ITL IT2 IT3 IT4I HREO I R5 /TTI7T IJH other busmaster /11 I DMA I service other busmaster. Figure 5-12.80186 mode bus arbitration. A bus arbitration cycle begins when an internal DMA request is generated by a transmitter or receiver. HREO is asserted low and the DDLC samples hack on falling MCLK edges. The DDLC assumes ownership of the bus after hack has been found asserted for 2 sample periods. The own pin is asserted low at the beginning of T1. After the DMA activity has been completed, HREO and own are negated on the rising MCLK edge during T4. Sometime later, hack is negated by the bus arbiter and the next bus master may negotiate for the bus. 5.3 Interrupt operation. The DDLC communicates with the host through status and control bits. When a particular status bit changes state, sometimes the host needs to service the status change quickly, so interrupts are typically used. The DDLC has a variety of interrupts which may be used by the host to get fast service on certain status changes. All interrupt generating status bits may be set by the user. This generates an immediate interrupt if the associated interrupt enable bit is set. This feature is useful for software debugging. MC145488 Motorola. 5 to 11. 5.3.1 Interrupt sources. There are two interrupt sources in the DDLC. As discussed in section 2.4.3, the interrupts are grouped into several categories. Normal operation interrupts are generated when the DDLC has completed a task and is informing the host of the completion, or when a change has been detected in the state of the physical link. An example of this category is RxDMA complete. Bit handler interrupts are fault conditions in the reception or transmission of frames from which the DDLC cannot recover on its own. An example is a transmit FIFO underrun. System interrupts are detected faults of the microprocessor bus, an example of which is bus error. Timer interrupts are generated when either timer counts down from 00 to FFA. Complete list of the interrupt sources is described below in Table 5 to 1. Table 5 to 1. Interrupt priority and vector values. Priority interrupt name vector, priority interrupt name vector. 1 RxCH0 bus error XC15 RxCH0 FIFO overrun X8. 2 RxCH1 bus error XE16 TXCH1 FIFO overrun XA. 3 TXCH0 bus error XD17 TXCH0 FIFO overrun X9. 4 TXCH1 bus error XF18 TXCH1 FIFO overrun XB. 5 RxCH0 address error XC19 RxCH0 buffer overrun X8. 6 RxCH1 address error XE20 RxCH1 buffer overrun XA. 7 TXCH0 address error XD21 RxCH0 idle X4. 8 TXCH1 address error XF22 RxCH1 idle X6. 9 RxCH0 DMA complete X423 CH0 CD changed state X4. 10 RxCH1 DMA complete X624 CH1 CD changed state X6. 11 TXCH0 DMA complete X525 SCP complete X2. 12 TXCH1 DMA complete X726 timer 1 X3. 13 TXCH0 frame complete X527 timer 0 XL. 14 TXCH1 frame complete X7. Note, X indicates user programmable bits. 5.3.1.1 Normal interrupts. These interrupts are generated in response to changes in the link state. A discussion of each follows. Receive DMA complete. Each channel has a receive DMA complete interrupt. This is generated when the receiver has detected a frame's closing flag and the DMA controller has finished placing the last data byte in memory. The DDLC is informing the host that a complete frame was received and is in memory at the locations described in the buffer descriptor. This interrupt is not generated in the transparent mode, as flag detection is not used. Transmit DMA complete. This is an early interrupt which indicates that the DMA controller has transferred the last byte of data from memory to the FIFO. This interrupt is used when the host wishes to send back-to-back frames. At 64 kbps, the host has several hundred microseconds from the time this interrupt is generated until the FIFO empties and the transmitter closes the frame with a CRC field and flag to prepare the next frame's buffer descriptor. Transmit frame complete for ISDN SIT interface D-channel applications, where back-to-back frames are illegal. Transmit frame complete is used. This interrupt indicates that the closing flag of a frame was successfully transmitted. On the D channel, where collisions may be found, the host needs to know when a frame was actually transmitted. If the DMA complete interrupt was enabled and a collision occurred while the last byte of data was being transmitted, the interrupt would have occurred before the collision. and the host may have already prepared the next frame for transmission. When the DDLC prepared to retransmit the frame that collided, the wrong frame would be sent. This interrupt is not generated in the transparent mode. Receive idle indicates that the generating channel's receiver detected at least 15 contiguous ones and that the link has gone into the idle state. This interrupt is used only in LAPB where interframe. Motorola 5-12 MC145488 periods are filled with flags. In this case idle is distinct from interframe periods. In LAPD, where interframe periods are filled with 1s, there is no distinction between interframe and idle periods. In LAPD applications, this interrupt should be masked. Carrier detect changed state. This interrupt is generated when the carrier detect pin changes state. The interrupt status bit is bit 12 of the receive status register. The current state of the CD pin is available on bit 15 of the same register. When the SCP is disabled and the serial interface is not in the time slot mode, the CD pin is available for general purpose input. 5.3.1.2 Timer interrupts. There are two timers in the DDLC. The timers are low-resolution devices intended for long-term timeouts for HDLC-type protocols. The source of the clock to the timers is the SCP prescaler, which is then further divided by 1024. The host can preset the value in the counter at any time and the counter will begin counting down toward 0 from that value. When a timer register counts down past 0, an interrupt is queued. The timer interrupt status bits operate identically to the other interrupt generating bits. The status bit must be read while it is set before it may be cleared. Note, the timer will ignore a count pulse if the pulse occurs while the register is being accessed by the host for a read or write operation. 5.3.1.3 Bit handler fault interrupts. These interrupts are generated when the transmit or receive state machines detect errors that cannot be serviced without host intervention. Receive FIFO overrun. This indicates that the DMA controller did not service the FIFO's request for data and data was lost. When this interrupt is generated, future DMA activity on the interrupting channel is suspended until the host re-enables the suspended channel. Transmit FIFO underrun. This indicates that the DMA controller did not service the FIFO's request for service. The frame in transmission is aborted and the transmitter enters the idle state. FIFO interrupts indicate that the system is having hardware or software malfunctions or that the system is approaching its throughput limit. Receive buffer overrun. The receive buffer overrun interrupt indicates that the received frame was too large for the allocated buffer in memory and usually indicates that a closing flag was corrupted in transmission. When this interrupt is generated, DMA activity on that buffer is suspended and if the alternate buffer is available, data will continue to be received and will be placed in the alternate buffer. This interrupt is used in the transparent mode to indicate that a block of data was received. 5.3.1.4 System fault interrupts. The interrupts for all four channels are enabled or masked together as either bus or address errors. A bus error is defined as the activation of the burp pin while a DMA cycle is in progress. The timing of sampling of the burp pin is the same as for the DAC pin. External circuitry determines which system faults allow the burp pin to be asserted. If burp is found to be asserted in a DMA cycle, the DMA channel that was active when the fault occurred is disabled. Address errors are defined to be activation of the LAC or CS pins while a DMA cycle is in progress. This implies that the DMA controller is pointing to a register inside the DDLC. When an address error is detected, the DMA channel that was active when the fault occurred is disabled. For transmitters, this means that DMA activity stops, the transmitter generates an abort character, then enters the idle state. Receivers are reset by clearing the RxN bit. 5.3.1.5 SCP complete interrupt. This interrupt is generated when an SCP transfer is complete. It operates similarly in master and slave modes. In master mode, the interrupt is generated after the 8th bit has been transmitted. In slave mode, the rising edge of slave select generates the interrupt. MC145488 Motorola 5-13 5.3.2 Interrupt Request, IRQ, pin. The IRQ pin is an active low, open drain pin which indicates that there is a pending interrupt from one of the DDLC sources. IRQ is the logical NOR of all enabled interrupt sources. As long as there is at least one pending interrupt, IRQ remains low. When the host processor requests the interrupt vector with either an LAC cycle or by reading the master status register, the highest priority interrupt pending at that instant, CS or LAC are asserted, will be encoded into bits BO-B3. The IRQ pin will remain asserted until all interrupting sources have been cleared. It is the host's responsibility, in the interrupt service routine, to clear the status bit which caused the interrupt, or the same interrupt will immediately cause another interrupt. 5.3.3 Interrupt Vector. The 27 interrupts are encoded into 4 bits of an 8-bit vector. The most significant bits of the vector are user programmable, so the block of vectors may be placed anywhere in the vector map. When the vector is read either with an LAC or a read cycle, the highest pending interrupt will be encoded and latched at the instant that the internal read enable signal is decoded. Every time the vector is read, the highest pending interrupt is encoded. After reset, the interrupt vector register reads 00 hex. This is different from other 68,000 peripherals which generate vector number of hex, uninitialized interrupt. The programmer is expected to initialize the interrupt vector map before enabling any of the DDLC interrupts. When an interrupt generating status bit is set, the bit must be cleared before that particular interrupt is cleared. A status bit may only be cleared if it was set when it was read. Stated another way, a status bit must be read in the set state before it may be cleared by writing a 0 into that bit position of the status register. This rule eliminates the possibility that an interrupt generating status bit can be accidentally cleared and thus lost. If a status bit is written with a 0 before it is read while it is the write operation for that bit will be ignored. 5.3.468,000 Interrupt Acknowledge Cycle. An interrupt acknowledge cycle has timing identical to a read cycle. However, the vector number is placed only on the lower byte of the data bus, pins 2D7L. The LDS pin indicates that data is valid on the lower byte. The LAC pin and CS are mutually exclusive and should not be asserted at the same time. If they are asserted simultaneously, the CS pin has precedence. Figure 5-13 describes an LAC cycle in a 68,000 system. Motorola 5-14 MCLK LAC LOS 00-07 OTAC RIW So 8284 S6 // output /I Figure 5-13 68,000 LAC cycle MC145488 An interrupt acknowledge cycle is virtually identical to a read cycle except that it begins when lack is asserted. The OOLC presents the interrupt vector number to the data bus on pins 00-07 and asserts attack on the next rising MCLK edge after the lack pin was detected low. The cycle is completed when loss and lack are negated. 5.3.5 interrupt acknowledge cycle. The 80186 interrupt acknowledge cycle is similar to a read cycle except that the INTA signal is issued 1 clock earlier than the RO strobe. Because the OOLC responds to the INTA pin identically to the RO pin, the data will be placed on the bus 1 MCLK edge after the INTA pin was detected asserted. Figure 5-14 describes one INTA cycle. The 80186 actually performs two cycles separated by two wait states. The OOLC will respond to each cycle identically. T113 MCLK INTA \\\\/00-07-4 _______ J dash. Figure 5-14.80186 INTA cycle. The OOLC monitors the INTA pin continuously and when it is found asserted, with IRQ asserted, presence the interrupt vector on the next MCLK edge. 5.4 Reset operation. The OOLC may be reset by a hardware signal, or by software. Additionally, with the watchdog timer activated, the OOLC may reset the entire host system if the timer underflows. Table 3-1 describes the state of all register bits after a reset operation, either hardware or software. A software reset takes 2 MCLK cycles to complete. Figure 5-15 describes the timing of a watchdog timer generated reset. Reset becomes an output and is held low for 16 MCLK cycles, then it is released. MCLK MC145488 16 dash. Figure 5-15 Watchdog generated reset. Motorola 5-15 Motorola 5-16 MC145488 Section 6 Serial Interface Operation. The serial interface has several modes of operation. The following sections describe the operation of each mode. Functional timing diagrams are included to clarify the operation. For detailed parametric specifications, see Section 8. The DDLC's two channels each have three modes of operation for their serial interfaces: IDL, time slot, and modem. In the IDL mode, the DDLC is compatible with Motorola's ISDN family. When IDL D-channel operation is selected, D-channel access control pins, DREQ and DGNT, are also provided. The time slot mode provides compatibility with typical PBX backplane timings. Both long frame and short frame synchronization is supported. In the modem mode, each channel supports a standard 7-pin synchronization. Modem interface including 3 modem control signals. See Table 4-4 for a description of the serial interface pin functions. The two DDLC channels are identical but independent. The following discussions describe one channel, but they apply to both. 6.1 Interchip Digital Link, LOT, interface for ISDN applications. The IDL interface is used to interconnect various devices on ISDN board-level systems. See Figure 6-1. The IDL distributes several channels of information from the ISDN Basic Access Interface, SID bus, that have been processed by the MC145474 SIT transceiver to the various devices on the bus using a time slot. Technique. Full duplex data is transferred in 20-bit frames every 125 ps, providing 160 kbps full duplex. Bandwidth. Figure 6-2 describes the operation of the IDL frames. A continuous clock at 2.56 MHz, or other standard frequency, shifts the data for both transmit and receive. ISDN. SRR bus. MC145474. SRR. Transceiver. I. Codec. Filter. IDL-BUS. II. MC145488. DDLC. Figure 6-1. Typical DL bus application. 6.1.1 Functional description. I. Other. IDL. eVice, S. 264 kbps B channels and 116 kbps D channel along with two 8 kbps auxiliary channels are passed over the IDL interface. The DDLC is an IDL slave which is clocked by the bus master, typically the MC145474 SIT transceiver. Figure 6-3 indicates the relationship of the four IDL signals. IDL sync is an input which accepts a positive 1 clock period wide pulse. The 20 clock periods following the pulse contain the IDL frame. Sync occurs every 125 ps so that 8,000 frames per second are exchanged between the bus master and the slaves. IDL-CLK is an input which receives a square wave at 2.56 MHz from the IDL bus master. For ISDN terminal applications, the MC145474 SIT transceiver is the IDL bus. MC145488 Motorola 6-1 1-01 1-125.I 10L sync 11JL .-s- bit fields B1 2 B2 2 B1 2 B2 1011 111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111 1. 10LTXDRRX. 10LCLK. Figure 6-2. IDL frame timing. 10L sync. JL. 10LCLK. 10LTX-1B1/01. A. I. B2. 101M. 10LRX. I. B1. 1. 0. 1AI. B2. 10H. Figure 6-3. IDL bus signals. Master which provides this clock. In other applications, frequencies such as 1.536 or 2.048 MHz may be used. IDL-TX is an output which is active only on assigned bits in the frames. For all other bit times, it is high impedance. IDL-RX is the data input which samples bits only on assigned time slot bit times. The 20-bit frames are composed of 5-bit fields. The first 8 bits contain data on the 64 kbps B1 channel. The 9th bit contains 1 bit of the D channel. The 10th bit is an auxiliary bit which is not used by the DDLC. Bits 11 to 18 contain the 64 kbps B2 channel. The 19th bit is the 2nd bit of the D channel and the 20th bit is another auxiliary bit which is not used by the DDLC. When the DDLC operates on the D channel, it uses bit 9 and bit 19 of the IDL frame. The two bits cannot be separated. The D channel is a 16 kbps channel which is used for communication between an ISDN terminal and the network. When the DDLC is configured for use with the IDL D channel, it directly supports the D channel. Contention algorithm of the MC145488 SIT transceiver. Each channel may operate on either of the B channels or the D channel. With both channels configured in the IDL mode, the DDLC has the capability of handling data on either B channel and the D channel or on both B channels simultaneously. If the two channels operate on the same IDL frame, must be taken so that the transmitters are not programmed to output data in the same bit times. 6.1.2 Subrate multiplexing, CHIT 1.460. Normally, all 8 bits of an ISDN B channel are grouped into one 64 kbps bearer channel. However, a B channel may be thought of as composed of 8 kbps channels. CHIT specification 1.460 outlines a technique where the individual bits in a B channel are accessed and treated as individual channels. The DDLC meets the requirements of 1.460 as it can access individual bits in the B channels for multiplexer or other non-ISDN applications. A bit mask register is provided for each channel which selects the individual bits in the 8-bit field which are active. The B channel bit mask registers are programmed with OS in the Motorola 622 MC145488 positions where the bits are active and ones where the bits are ignored. Note that the least significant bit is transmitted first, so the LSB of the mask register corresponds to the first bit transmitted in an IDL frame. For example, if bits 2 and 3 are to be active in a particular application, the coding in the bit mask register would be 11110011, F3 hex. The receiver will ignore all bits in bit positions other than B2 and B3 and the transmitter will transmit only on these 2-bit positions. On all other positions, it will be high impedance or ones depending on the setting of the mask drive bit in the transmit control register. When high impedance is selected, other devices on the IDL bus may transmit during the inactive bit times. 4. Applications without other devices sharing a B channel, ones may be transmitted, eliminating the need for a pull-up resistor on the bus. The bit mask feature is usable on IDL B channels. In D-channel operation, the bit mask is disabled. Figure 6-4 depicts subrate multiplexing where B2 and B3 of the B1 channel are active. Other devices on the IDL bus may transmit on the first 2 and last 4 bits of the B1 channel or the B2 or D channels. IDL sync -fl ________________________ IDLCLK BLB2 T IDLTX IDLRX active bits. Figure 6-4 IDL subrate multiplexing 6.1.3 Transparent operation. The DDLE provides a method to pass unformatted, unframed data between the serial interface and memory. Internal synchronization signals are generated which delineate byte boundaries. Received data is organized into bytes and passed to memory through the DMA controller. Bytes from memory are transmitted upon command by the internal sync signal. The user has control of the byte orientation within an 8-bit time slot. Transparent operation is not supported with D-channel operation. A bit pattern is programmed into the bit mask register which corresponds to the byte alignment desired. Other alignments are possible by moving the position of the 0 in the bit mask register. Table 6:1 describes the possible bit patterns and their consequent alignments. Transmit and receive use the same mask register, so their byte alignments are the same. Table 6:1 Time slot byte alignment. MSB Lab 0111111 hex aligned to time slot boundary, BO. 1011 1111 BF hex aligned to BL. 1101 1111 of hex aligned to B2. 1110 1111 F hex aligned to B3. 0.11110111 F7 hex aligned to B4. 1111 1011 FB hex aligned to B5. 1111 1101 FO hex aligned to B6. 1111 1110 Fe hex aligned to B7. MC145488 Motorola 6-3. Figure 6-5 depicts the case where 7F hex is loaded into the bit mask register. Data bytes are aligned such that the 7th bit in a time slot is shifted into the BO position of the data bytes stored in memory. All other received bits follow sequentially. As figure 6-5 shows, the internal sync signal is actually offset by January 2nd bit time to eliminate internal edge skew. The user does not see this offset in the IDL or time slot modes, however, in the modem mode this is important. Section 6.3.1 describes this more fully. Serial clock, bit mask, register, internal sync, data, bits, time slot. Figure 6-5. Transparent byte alignment. 6.2 Time slot interface. A PBX PCM highway time slot interface may be enabled for network applications. Time slots of 8 bits. Each are enabled so the DDLC shares a bus with other devices. The transmitter transmits up to 8 bits in a time slot, then goes high impedance. The receiver samples bits only in its assigned time slot and ignores all other bits. Subrate multiplexing may be used in time slot operation in a similar manner as the IDL mode. Figure 6-6 describes a typical PCM bus application. TLMESLOT assigner. II. PCM highway. III. Device. DDLC. 01NLN. Figure 6-6. PCM highway application. Two separate continuous clocks, not shown, at 1.536 MHz, clock the transmitters and receivers on the bus. Individual devices are activated for their assigned 8-bit time slot. Figure 6-7 shows a device active on time slot 2. The other 23 devices are active on the PCM highway in their assigned time slots. External circuits called time slot assigners, TSACs, count time slots using the frame sync to keep track of frame boundaries. They output enable signals to the devices on the bus so that each device is active for only its assigned slot. Two modes of operation are common in industry, long frame and short frame. TSACs are available which provide long or short frame synchronization signals. The DDLC supports both operating modes and automatically switches between them on a frame-by-frame basis. Note: when switching between modes, one frame time is needed to synchronize operation. Motorola 6-4. MC145488. I_125. Pi. I. Frame sync. NN. SF, --:. Time slot numbers. I. 24. 2. 1. I. 2. I. 23. I. 24. 2. 1. I. 2. I. TX or RX 111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111 1111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111 111111111. Figure 6 to 7. PCM bus. 6.2.1 Mode selection. When the time slot mode is first selected, short frame operation is assumed. An 8-bit transfer is made. When the enable signal goes high. During the 3rd bit time, the enable signal is sampled, and if it is low, short frame operation is selected for the next frame. If the enable signal is high, long frame operation is selected. The serial interface samples the enable signal on every 8-bit transfer and adjusts its timing. For the next transfer, for best operation, the operating mode should be fixed to either long or short frame operation. The transmitter and receiver are independent of each other, so one may be in long frame and the other may be in short frame operation. When the time slot mode is first enabled, the transmit enable bit in the transmit control register should be 0. This forces the TXD pin to high impedance. After a 125 piece frame time, the serial interface block of the DDLC is synchronized to the time slot. The transmitter then can be enabled and will transmit on its proper time slot. 6.2.2 Long frame operation. In long frame operation, an enable signal is presented to the DDLC, which encloses the 8 bits of a time slot. The first transmitted data bit in a time slot is enabled on the rising edge of the TX enable or first TX clock rising edge, whichever is later. The next 7 bits are output on succeeding rising clock edges. The TX enable signal normally returns low between the 7th and 8th falling clock edges, but it may return low as early as the 5th rising clock edge. If it remains high after the 8th clock, the transmitter continues transmitting bits until the enable goes low. The receiver is similar, except that it samples the RX data pin on falling clock edges while RX enable is high. The long frame mode expects a continuous clock for proper operation. For non-standard applications, active time slots may be separated by as few as 4 clock pulses. Figure 6 to 8 describes typical long frame operation. Separate clocks may be provided to the transmitter and receiver for asynchronous applications. If a single transmit/receive clock is used, the TX and RX clock pins may simply be connected together. Similarly, if transmit and receive are on the same time slot, TX enable and RX enable are connected together. 6.2.3 Short frame operation. Short frame operation is similar to IDLB1 operation. A 1 clock wide sync signal is presented to the TX enable pin during the clock period immediately preceding the 8 bits of a time slot. The transmitter outputs its 8 bits on the 8 rising clock edges of the clock following the sync. The receiver samples the RX data pin on the 8 falling clock edges following the sync. Figure 6 to 9 describes the operation of short frame operation. As with long frame, active time slots may be separated by as few as 4 clock pulses. MC145488 Motorola 6 to 5 RxEnablej1111111111 RxEnablejL lax sync I underscore 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 RX clock. RX data. TX enable 11111111. Tsnable. N. TX sync I.J1 underscore 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 underscore. TX clock TX clock. TX data. Figure 6 to 8. Time slot operation long frame figure 6 to 9. Time slot operation short frame. 6.2.4 subrate multiplexing. The subrate multiplexing bit mask function of the IDL interface operates identically in the time slot mode. See section 6.1.2 for a complete discussion. Placing a 1 in a particular bit in the mask register causes the receiver to ignore that bit, and the transmitter transmits either a high impedance or 1 for that bit time, depending on the setting of the mask drive bit in the transmit control register. 6.2.5 Transparent operation. Transparent operation in the time slot mode is similar to operation in the IDL mode. Asynchronization. Signal is programmed into the bit mask register, which defines byte alignment through the receiver and transmitter. Because the transmitter and receiver share the bit mask register, byte alignment within transmit and receive time slots must be the same even though the time slots are not related to each other. See section 6.1.3. 6.3 Modem interface. For those applications that do not use a time slot type interface, the DDLC provides a modem style interface. In the modem mode, 7 pins transfer data and control information. There are transmit and receive clock inputs, TXCLK and RXCLK, transmit and receive data pins, TXD and RXD, and modem control lines, RTS, CTS, and CD. The transmit and receive clocks are independent of each other and may be asynchronous to the microprocessor system clock, MCLK. These clocks may have a frequency of up to MCLKI. It must be noted, however, that the data throughput of the DDLC is limited by the microprocessor bus bandwidth available to the DOL and the rate at which the MPU can service interrupts. See figure 6 to 10. Data bits from the TXD pins are presented on falling edges of the TXCLK, this is inverted from the time slot and IDL modes. Data bits on the RXD pins are sampled on the rising edges of the RXCLK, again, this is inverted. The modem control lines are used to control the flow of data. Request to send, RTS, is an active low output which indicates that the DDLC has data to transmit. Clear to send, CTS, is an input which indicates that the DDLC has permission to transmit. The CTS bit in the transmit status register indicates the current state of this pin. If CTS goes inactive, high, for more than one TXCLK bit time while a frame is being transmitted, the DDLC immediately aborts the frame and prepares to retransmit the frame. When CTS again goes active, carrier detect, CD, is an input which indicates that the data on the RXD pin is valid. The CD bit of the receive status register indicates the current state of this pin. Motorola 626 MC145488 Telephone or Packet Network. Modem 0. Modem 1. EIA 232. Transceiver TLCH0 1 plus LCHL EIA 422. Transceiver MC145488. DDLC. Figure 6 to 10. Modem application. Microprocessor. Bus. The bit mask feature is not available in the modem mode. Data is transmitted continuously, not in 8-bit clusters, so masking bits is not appropriate. 6.3.1 Transparent modem operation. The modem mode can operate with transparent data in a similar manner to the IDL and time slot modes. Unlike the other two modes, however, the user must provide a synchronization signal to indicate byte alignment of the serial data. The transmitter and receiver maintain the given alignment through the bit handlers and FIFOs to memory. The synchronization signal is a 1 clock-wide active low pulse. A byte boundary occurs 1.5 clocks following the falling edge of the signal. Figure 6 to 11 describes the operation of the receive byte sync. Transmitter operation is similar. Notice that the sync signal edges occur on rising clock edges, middle of a bit time, so that proper setup and hold times will be met when the signal is sampled on a falling clock edge. RxCLK RX0 byte 1 I byte N RxPsyncu U. Figure 6 to 11. Transparent modem operation. Synchronization signals on transmit should occur on 8-bit boundaries but is optional after the first pulse as the transmitter maintains byte sync in the absence of sync signals. Resynchronization occurs on every sync pulse, so if sync pulses occur every 8 bits, synchronization is maintained with the original alignment. For receive, sync pulses should also occur on 8-bit boundaries and are optional after the first pulse. The synchronization signal to the receiver resets an internal modulo 8 counter which generates a load signal to the FIFO. If synchronization pulses occur more frequently than every 8-bit times, the counter will never generate a load signal and data will not be transferred to the FIFO. 6.4 Serial Control Port, SCP. The DDLC has a serial control port which may be used to communicate with external devices through a serial mechanism. The SCP is a 4-wire full duplex communication system which exchanges 8-bit bursts. MC145488 Motorola 6 to 7 of data with SCP devices. The DDLC may be programmed to be an SCP master which generates the enable and clock signals OR.AN SCP slave which accepts clock pulses from an external master. The SCP is compatible with Motorola Serial Peripheral Interface, available on most single-chip MCUs, and National Semiconductors MicroWire Plus. Figure 6 to 12 describes a typical application of the IDL and SCP buses in an ISDN terminal. In this example, the SCP bus passes control information to the internal registers of the SIT transceiver and codec/filter to set operating modes and read status information, and the DDLC is an SCP master. In other applications, the DDLC may be an SCP slave. ISDN SIT bus MC145484 SIT transceiver SCP bus equals colon dash colon equals 1 IDL bus underscore dash 4 MC145488 DDLC. Figure 6 to 12. ISDN terminal application. 6.4.1 Serial Control Port Description. _pubis. The SCP module in the DDLC consists of a baud rate generator, a shift register, a control block, and several control bits. The shift register is parallel read/write and connects directly to the data bus when addressed. Data may be written or read at any time except when a transfer is in progress. If the register is written at this time, the write is ignored, and if the register is read, data reads 00 hex. Control and status. Bits may be read or written at any time. The control block generates an interrupt on the rising edge of slave select in the slave mode or generates 8 clock pulses in the master mode. The baud rate generator selects one of 4 clock rates derived from MCLK. The serial interface block multiplexes the SCP functions onto the modem control pins when the SCP is enabled. See Figure 6-13. Motorola 6-8. SCP-TX. Slave. Select. MSB. Control and Clock Gen. MPU Data Bus. 8-bit shift register. Control bits. MPU Data Bus. Baud rate. Generator. Figure 6-13. SCP Module Block Diagram. SCP-RX. MCLK. 2 timers. MC145488. The SCP module is enabled by setting the SCPE bit of the Channel 0 serial interface control register to T. The modem control pins of Channel 0 are forced into the STP function and override any other functions that may have been selected. The Channel 1 CD pin is controlled by the SCPE bit of Channel 1 serial interface control register and becomes a second SCP enable, SCP-N1, pin when this bit is set to 1. SCP-N0 or SCP-N1 must go low when the SCP clock is in its inactive state. For example, when the SCP clock is used in the normal mode, SCP enable must go low when the SCP clock input is low. When the SCP clock is used in the inverted mode, SCP enable must go low when the SCP clock input is high. 6.4.2 SCP Master Mode. SCP-N0 and SCP-N1 are actually general-purpose outputs which may be used to enable SCP slave devices. When low, the enable signals indicate that the slave has been selected and should expect a data burst. SCP-CLK is an output which provides the shift clock for the data. The clock is normally low until a burst of data is transmitted. Then the clock is active for 8 pulses. SCP-TX is an output which transmits data MSB first to the slave device. New data bits are presented on the rising edges of SCP-CLK. SCP RX is the input which accepts data from the slave devices. This pin is sampled on the falling edges of SCP-CLK. Note, the SCP-CLK is selectable as to its polarity. Normally, the transmitter outputs bits on rising edges and the receiver samples bits on falling edges. When the clock polarity is inverted, the transmitter outputs on falling edges and the receiver inputs on rising edges. Figure 6-14 shows the normal polarity case. SCPEN 0. ORLR. SCPEN 1I. SCP. CLK. SCP-TX. SCP-X. Figure 6-14. SCP pin functions master mode. When a message is to be sent to a slave device, the information is placed in the SCP-TX/RX register. Then enable 0 or enable 1 in the SCP status/control register are set to 1 depending on the application. This activates the selected enable pin to a logic low. The host then activates the transmit bit and the SCP controller generates 8 clock pulses on the SCP-CLK pin and shifts the data on the 8 rising edges. Data is shifted most significant bit first. The slave transmitter, at the same time, shifts its data, if any is ready, to the DDLC SCP-RX pin on the rising SCP-CLK edges. The DDLC samples the SCP-RX pin on the falling SCP-CLK edges and replaces the transmitted data with the received data in the TX/RX. Register on a bit-by-bit basis. After the 8 shifts have occurred, the transmit bit is cleared, indicating that the exchange was completed and the SCP complete interrupt is generated. The host then resets the enable 0 or enable 1 bit, which causes the enable pin to return to a logic high. Typically the user will poll the SCP IRQ bit to see when the 8-bit exchange is complete. The IRQ bit is a status bit which generates an interrupt if the SCP complete interrupt is enabled. The SCP and pins are directly controlled by the bits in the SCP control register. The pins change state within 1 MCLK after the end of the MPU bus cycle, which changed the bits. The SCP-TX bit causes the SCP state machine to start transmitting within 1 1/2 SCP clocks after the bus cycle, which changed the bit. Recall that this can be 24 MCLK periods if the +16 prescaler tap is selected. Note, the SCP register should not be written within 1 1/2 SCP clocks after the SCP complete interrupt is generated. This could be up to 24 MCLKs with the +16 prescaler selected. MC145488 Motorola 6-9. The user can select an appropriate baud rate for the application. The baud rate bits in the SCP status cell control register select a tap on a divider chain which generates the SCP CLK signal. See section 3.44. A listing of the divide ratios available. 6.4.3 SCP slave mode. When the SCP is in the slave mode, SCP N0 becomes an input, slave select. SCP N1 remains a general purpose output if it is enabled by setting the SCPE bit in the serial interface control register 1. Address 40 hex. SCP CLK also becomes an input. The SCP module now waits for the slave select pin to go low and accepts data until the rising edge of slave select. Data bits are input on the SCP RX pin. Any data in the TX/RX register is shifted out, MSB first on the SCP TX pin, on positive SCP CLK edges. Negative edges if the clock invert bit is set. When the rising edge of slave select is detected, the SCP complete interrupt is generated. In the slave mode, any clock frequency from DC to MCLK/2 is acceptable. The clock may be continuous, but is utilized internally only when slave select is low. Data is shifted into and out of a shift register simultaneously. If slave select is low for fewer than 8 clock pulses, data that was in the shift register before slave select went low will remain in the register and will be shifted by the number of clock pulses received while slave select was low. Data received will have shifted into the low order bit positions. If slave select remains low for more than 8 clock pulses, received data will be shifted out starting on the 9th clock pulse and will continue to shift until slave select goes high. Figure 6-15 describes a typical SCP slave exchange. In this case the clock invert bit is 0. The SCP-TX pin outputs the first data bit on the first rising clock edge following the falling edge of slave select. The SCP complete interrupt is generated on the rising edge of slave select. The slave select pin must transition to low while the SCP CLK is inactive, low while CI is 0 and high while CI is high. Motorola 6-10. Slave select dash R NNPUTIIL underscore 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 11. SCP CLK NNPUTI SCP-TX SCP-RX Figure 6-15 SCP pin function slave mode MC145488 Section 7. Applications. The DDLC was designed for ISDN systems, but it finds many non-ISDN applications. This section will describe two ISDN applications. A non-ISDN application such as an X.25 pad is similar in concept to the ISDN devices, but the physical interface is different. 7.1 ISDN Voice/Data Terminal Adapter. The DDLC and its companions, the MC145474 SID transceiver and the MC145554 codec/filter easily connect to build a powerful ISDN terminal with voice and data capability. This section will describe the design of a standalone 2B+D terminal adapter which provides an asynchronous EIA232 interface for an external dumb terminal. The terminal adapter, TA, performs packet assembly/disassembly, PAD, functions for the terminal and transports data packets on either B channel or the D channel. PCM voice is transported on the remaining B channel. This example assumes that 16K RAM and 64K ROM is sufficient to support firmware and buffering needs. Figure 7:1 is a block diagram of the TA, keypad and display. MC68HC05 MCU decoder DuArt2 FEIA232 dash terminal ISDN SID B interface transceiver L-DD_LC MPU bus MC68000 analog __ tones IDL bus 2 telephone handset codec filter 16K RAM 64K ROM. Figure 7:1 ISDN terminal adapter with voice and data block diagram. Terminal adapters may have many configurations. This example converts asynchronous EIA232 data into V.120 format for transport on either one B channel at 64 kbps or the D channel at 16 kbps. Firmware in the TA provides packet assembly/disassembly functions for the asynchronous data. Voice calls may be placed on the second B channel. Again, firmware handles call setup and teardown signaling with the network. A microcomputer is provided to control a keypad and display. These are used to place voice and data calls and to display local and network status messages. The microcomputer communicates with the MC68000 host through one of the asynchronous ports on the MC68681 DuArt. Call progress signals, such as dial tone and touch tone registered beeps, are generated in the microcomputer and passed to the telephone handset through the codec/filter. MC145488 Motorola 7:1. This basic design can be expanded to support more asynchronous channels by expanding RAM and ROM, if necessary, and by adding extra DuArts. V.120 software supports statistical multiplexing, which in turn leaves packets from multiple sources onto the ISDN B or D channels. 7.1.1 IDL and SCP interfaces. The data backbone of the system is the IDL bus. Figure 7:2 describes the interconnection between the SID transceiver, the DDLC, and the codec/filter. The IDL bus passes actual data which is transferred on the ISDN link to the network. The SCP bus passes status and control information between the MC145474 SID transceiver and the host processor using the SCP module in the DDLC. MC145474 SID transceiver SCP I 53 OREQ OGNTL. CH1. MC145488. OOLC. T68000. MPU system. CH0. MC145557. QEC/filter. Figure 7-2. IDL, SCP bus connections. Voice handset. On both IDL and SCP buses, master transmitters are connected to slave receivers and slave transmitters are connected to master receivers. The MC145474 SIT transceiver is the IDL master and the DDLC is the SCP master. Refer to Table 4-4 which defines pin names and data directions and cross-references them to the actual pin numbers on the DDLC. Refer to the MC145474 SIT transceiver and MC145554 codec. Filter data sheets for correct pin connections. All three chips simply connect together on the IDL bus and the DDLC and SIT transceiver connect together on the SCP bus. The codec/filter operates on IDLB1 channel and the DDLC will be programmed with software to communicate on IDLB2 and IDLD channels. 7.1.2 MPU/DMA interface. The DDLC was designed to fit into a 68,000 host system with minimal glue logic. For the high performance terminal adapter in this example, virtually all glue logic is contained in 2 PALs. Because the DDLC is the only bus master other than the 68,000, bus arbitration is handled directly by the 68,000. Interrupts from the DUART, DDLC, and SIT transceiver are directly connected into the 3 IPL inputs of the 68,000. The interrupt acknowledge, LAC, signal to the DDLC is also generated in one of the PALs. The RAM size is small, 16 KB, so static RAM was chosen for simplicity. Similarly, the ROM is small, so 232K x 8 EPROMs are used. Memory is arranged in even and odd byte address banks to be compatible with the DDLC and 68,000 memory structure. Motorola 7-2 MC145488. Figure 7-3 describes the memory map used in this example. 8 16KB pages are used. ROM occupies the lowest 4 pages. RAM is actually one 16KB page, but since full address decoding is not used, an alias page, beginning at 14,000, appears. The DDLC and DUART are not fully decoded, so they appear on many alias addresses within their respective 16K pages. As the DUART is an 8-bit peripheral, it occupies only the odd bank of its 16KB page. All accesses to the DUART are on odd addresses. LFFFF. Ward. OOLC. 17FFF. 13FFF. Off. ROM. 00000. Figure 7-3. 128KB memory map. The DDLC own pins are provided so that the page on which the buffer RAM resides can be accessed. In this example, the own pins are used to generate a chip select for the RAM which resides on the 5th page in the system. Expanding the ROM or RAM beyond this example is quite easy. Simply going to 32K byte pages doubles all available blocks without changing the address decoder block. The address pins are just connected to the next most significant address pins on the system bus. Other applications use the own pins to generate function codes and further expand the memory. Section 7.2 describes such a system. 7.1.2.1 Interrupt vectors. This design example has 3 interrupt generating devices, the MCL45474 SIT transceiver, the DUART, and the DDLC. The 68000 has 3 interrupt input pins which can be encoded to produce up to 7 interrupt priority levels. Level 7 is the highest priority and level 1 is the lowest. The DDLC IRQ pin is connected to IPL1 generating a level 2 interrupt and the SID transceiver. IRQ pin is connected to IPL0 generating a level 1 interrupt. Because the DuArt will be working at relatively high speeds, up to 19.2 kbps, its interrupt priority is set to level 4 by connecting its IRQ pin to IPL2. After the 68000 recognizes that an interrupt has been generated, it stacks selected internal registers then fetches a vector number from the interrupting device. The vector fetch cycle, known as an interrupt acknowledge cycle, is similar to a read cycle except that the LAC pin on the peripheral device is activated rather than the CS pin. The DDLC generates up to 27 interrupts and encodes them into 15 unique vectors. Several interrupt handlers may be built in software, each servicing specific interrupts. The DuArt also generates its own vectors in a similar manner to the DDLC, but this design uses the auto-vectoring technique of the 68000 to service the DuArt and the SID transceiver interrupts. Auto-vectoring operates as follows. When the 68000 fetches a vector from the interrupting device, if it detects VPA asserted in place of DAC, it terminates the cycle and vectors to the function addressed by the auto-vector area of the vector map for the current interrupt level. 7 auto-vectors are provided, 1 for each priority level. One of the PALs is programmed to generate VPA when a level 1 or level 4 LAC cycle is performed causing an auto-vector. The starting addresses of the interrupt handlers must be placed in their proper locations in the interrupt vector map during the TOS restart sequence. The programmer should not enable any interrupts in the system until all vectors have been placed in the vector map. MC145488 Motorola 723 7.1.2.2 DMA bus arbitration. The DDLC has a built-in DMA controller which connects to the 68000. Quite simply in this TA example, the 3 DMA arbitration pins, BR, BG, and GAC directly connect to their counterparts on the 68000. All 3 signals need pull-up resistors of about 50 kΩ. A more complex design with multiple MPU bus masters normally uses a bus arbitration module. 7.1.2.3 decoder PALs. Chip count of this terminal adapter is minimized by using 2 PALs, program Mabel array logic. This section describes the operations performed by the PALs and their design equations. Chip selects and control signals for RAM and ROM are generated in the address decoder PAL. DAC for RAM and ROM is generated in a second PAL. Recall that the DDLC and DuArt generate their own DAC signals. The address decoder PAL is a 20 LA device and the DAC generator is a 16 R4 device. Table 7-1 describes the input and output signals of the PALs, while Table 7-2 defines the design equations. Motorola 7-4. Table 7-1. System decoder PALs. Address decoder, 20 L8, DAC generator, 16 R4. Inputs outputs. As IROMCS ROM CS ID TACO. A 2 IRAM_CS RAM CS ID TACI. A 14 IDLC CS MCLK IRAM DAC. A 15 IDLC LAC QLQO, internal terms. A 16 IDUART CS02QL, internal terms. A 17 IWE enable. OWNO10E. OWNIIVPA. RW. DS. Table 7-2. PAL design equations. IDUART CS equals idlc cs equals idlc iack equals iromcs equals iramcs equals ivpa equals iwe equals ioe equals qo equals q1 equals 02 equals idtaco equals idtac1 equals iramdac equals ioe input equals clk input equals address decoder 20L8 IAS.A16.A15.A14 IAS-A16.A15/A14 IAS-A17A2 IAS/A16 IAS.A16/A15.0 IAS/A15.IOWNO IAS/A15.0 IAS-A17/A2 IDS/RW/S.A16/A15.0 IDS/RW/S/A15.IOWNO IDS/RW/S/A15.0 IDS/RW/S/A16/A15.0 IDS.RW/S/A15IOWNO IDS/RW/S/A15.0WNO DAC generator 16R4 IROM_CS clocked by MCLK IROM_CS.QO clocked by MCLK IROM_CS.QO.QL clocked by MCLK QO.QL/ROM_CS normal DAC Q1.02/ROM_CS delayed DAC IRAMCS IROMCS MCLK. Note, the three DAC signals are three state signals which are high impedance while their respective chip selects are inactive. MC145488. The address decoder operates on 16K byte pages allocating 4 pages to ROM and 1 page each to the DDLC, the DUART, and RAM. As full address decoding is not used, RAM appears at an alias page. Beginning at address 14,000 and the DUART and DDLC appear at many alias addresses in their respective pages. The lack cycle is detected, not by using the function codes, but by detecting the assertion of a 17. When the 68,000 does an interrupt vector fetch, it puts addresses between FO and FFFFFF on the bus. This is the only time in this design that the 68,000 accesses an address where A17 is asserted. So A17 makes a convenient interrupt fetch detector. When A2 is asserted during an interrupt fetch cycle, indicating a level 2 interrupt vector fetch, lack to the DDLC is asserted. When A2 is negated, VPA is asserted low, causing the 68,000 to vector to the level 1 or level 4 auto vector. DAC signals are generated for ROM and RAM. Normal and delayed DTACKs are provided for ROM, enabling the use of slow EPROMs if desired. Fast static RAM is assumed, so RAM_DAC is simply RAM_CS converted into an open drain signal. 7.1.3 User Interface, Microcomputer Keyboard/Display Controller. A microcomputer, configured as a smart peripheral, is a simple but powerful way to provide a user interface. Into the top. Typically a keypad and LCD display provide input means and feedback to the user. Ordinary telephones provide audio feedback, signaling tones, etc., to the user, so the microcomputer in this example also generates these tones. While the microcomputer is controlling the keyboard and display, It communicates with the 68,000 host to pass keypad inputs to the TA and status signals to the display. A simple protocol using the asynchronous port of the MC68HC05 and one of the two DuArt channels is an inexpensive and reliable W to provide two-way communication between the processors. To be user-friendly, an ISDN terminal adapter must be similar in operation to an ordinary telephone. Because it has several features not on ordinary telephones, it will have special function keys and a display of some sort. When the user wishes to place a call, the user places the TA in the off-hook state and dials the number just like an ordinary telephone. The MCU reports the hook switch status to the host to prepare the TA for an outgoing call. When the host acknowledges the status, the MCU reports keypad inputs to the host so call setup messages can be prepared for transmission to the network. Terminating a call is also similar to that of an ordinary phone. Voice and data calls are handled similarly. A simple message protocol should be implemented between the host and MCU, consisting of a status byte followed by data bytes. Optional error checking can be provided, but probably is not necessary. A typical speed for the data link would be 9600 baud with operation in a full duplex mode. Almost any message format may be used, but it must be simple enough so that it does not burden either the MCU or the host. The MCU should be the link master, so that if the 68,000 needs service, or has a message, it should request permission to transmit before continuing. A basic set of messages from the MCU to the host would consist of status information such as key X pushed, go ahead, and message acknowledged. Others may be implemented as needed. Messages from the host include display message XXX, enable tone YY, message acknowledged, and set test mode, among others. Details of how the message protocol is implemented is beyond the scope of this datasheet. Typically, the host processor in a system does not handle low-level tasks such as keyboard scanning and display driving. Using a microcomputer as a smart peripheral makes more sense from both the hardware and software aspects. The MCU has quite a bit of power which may be exploited by handling certain aspects of the TA state control in its firmware. Specific partitioning is up to the system designer. Using an asynchronous link between the host and MCU makes good use of available hardware. The DuArt has a second channel which would not normally be used, and the MCU has an asynchronous communication module on chip. Separation of functions between the host, which is controlling the pad functions, and the MCU which is controlling the keyboard and display is clean. Only when a key is pressed. MC145488 Motorola 725. Or when a new message is to be displayed is there any communication between the 68,000 and MCU. This leaves the host free to handle the pad functions both for signaling and data transmission with interruptions only during state changes requested by the user or by the network. 7.1.4 Real-time operating system. A small real-time operating system coordinates the pad functions with real-time inputs from the micro-computer. The operating system is capable of controlling several instances of Layer 2, LAPD, and Layer 3, each logically independent from one another, even though they may use the same physical ROM code. Each process has its own environment which distinguishes it from other similar processes. The low-level device drivers operate in an interrupt environment and communicate with their host processes through mailbox structures. Requests from the outside world, user or network, are handled by the operating system. Appropriate processes are spawned or terminated as required. Figure 7-4 describes the interaction of the Operating system with the processes, their environments, and the device drivers. External. Processes. Environment. O. Device. Driver. O. Environment. Device. Driver. 1. Process. O. Process. Device. Driver. Figure 7-4. Real-time multitasking operating system. The operating system keeps track of all processes. For example, if a voice call is in progress and a data call is requested, the operating system will spawn new logical instances of layer 1, 2, and 3 processes to control the data call on the B channel. When the data call is terminated, the instances that were spawned are terminated. The voice call is independent and ignorant of the data call. The operating system keeps track of and controls the priority of each process and adjusts it as needed. Recall that network signaling messages have higher priority than packet messages. Figure 7-5 is a high-level view of the software/hardware interface. The operating system is not shown, as the individual processes and device drivers are not aware of its presence. From the process's point of view, it serves as a post office which passes messages between layers and from layers to device drivers. Requests from the outside are processed through the management entity. Motorola 7-6 MC145488. Management. Hardware/SDNWARE. Interface. SIT. SCVR. Data. Terminal. User. Keypad and display. ISDN SIT. Interface. Figure 7-5. Terminal adapter software/hardware model. 7.1.5 Summary. This section has described a conceptual design for a standalone ISDN terminal adapter. It is intended only to provide suggestions as to how a design might be done. The PAL equations are examples which are based on proven 68,000 designs. The software which resides in ROM is simple to describe but complex to write. No attempt has been made to describe the complexities of LAPD or Layer 3 software. The next section will go into some detail regarding Layer 2 software along with the low-level device drivers. Notice that the Layer 1 device driver logically connects to the SID transceiver even though it physically communicates via the DDLC's SCP block. 7.2 ISDN terminal card for the Macintosh SE. The Macintosh SE combined with an ISDN terminal card provides a powerful desktop communication tool. This section describes the design of an ISDN terminal which has the capability of transferring data at 64 kbps over an ISDN B channel while a voice call may be made on the second B channel. Call set up and tear down is handled on the D channel. The card uses the Macintosh's 68,000 CPU and system memory. Application software resides on disk and is loaded into memory when the application is started. The following discussion assumes that the reader is familiar with the Macintosh environment. The Macintosh is a powerful, elegant computer with a complex software package. Once the operating system and ROM toolbox are understood, the Macintosh is a programmer's dream. It is easy to build powerful, robust applications which have the Mac look. MC145488 Motorola 7-7. In many ways the standalone terminal adapter described in the previous section is similar to the Macintosh SE Ta. This section will provide detailed descriptions of the hardware and software. Figure 7-6 is a block diagram of the terminal card hardware. TX MC145474. SCP bus SCP. ISDN. SID bus SID. RX transceiver CH0. CF, MC145488 Macintosh SE equals. CDDDLC expansion port. 52. Telephone MC145554. CH1. Handset codec /FLLTER. Figure 7-6. Macintosh SE ISDN terminal card. Hardware block diagram. 7.2.1 Terminal card hardware description. This section describes the hardware of the terminal card. Brief digressions into 3 low-level software. Routines are included to clarify the hardware/software relationship. 7.2.1.1 The Macintosh SE expansion bus. The Macintosh SE is the first Macintosh computer, which provides an expansion slot so peripheral devices may be added to the system. Connection to the motherboard is via a single 96-pin VME type connector. Pin functions are unique to the Macintosh SE and are in no way compatible with the VME bus. For a detailed description of the expansion slot, consult Designing Cards and Drivers for the Macintosh/I and Macintosh SE, Addison Wesley Publishing Company. 1987. This book is referred to as DC&D throughout the discussion. 7.2.1.2 Data, Address, and Control Buses. Basically, the expansion slot provides all MC68000 bus signals plus a few extras which are used by the custom circuitry in the Macintosh. For the most part, the DDLC is directly compatible with the signals provided. The data bus of the DDLC is directly connected to the data bus of the expansion port. No data transceivers are necessary. The address bus in the Macintosh is 23 bits wide. Address decoders inside the Macintosh utilize all 23 lines to select specific devices or RAM areas. Since the DDLC provides 16 address lines, address expansion is required. A 64 KB block of RAM is used by the DDLC's DMA controller to hold data that is ready to transmit or that has just been received. An LS374 octal latch is used as an address expansion register, which is enabled onto the address bus during DMA cycles when the DDLC owns the bus. The DDL's buffer alloc routine allocates buffer space from the operating system and loads the upper byte of the buffer's base address into the 374, see figures 7-7 and 7-8. When a DMA cycle is executed, the outputs of the 374 are enabled by the own pins onto the upper byte of the address bus, providing effectively 23 address lines. Motorola 7-8 MC145488 1. Type pound of the complete DDLC register structure. 1. Type def short int integer. Type def unsigned bit underscore field. 1 star. Individual register unions. Asterisk 1. Type def union. Integer SYSCNTR. Struit. Bit field. Bit field test. Bit underscore field DTACKN. Bit underscore field wait. Bit field reset. Bit underscore field BW. SYS control. Sys control. Type def union. Integer vector. Struct. Bit field. Bit field vec user. Bit underscore field vec number. RNSTR underscore stat. Master status. Type def union. Integer int n. Struct. Bit underscore field SCPC. Bit field CDI. Bit field CDO. Bit underscore field RXLIDL. bit underscore field RXOIDL, bit underscore field RXB over, bit field TXF unr, bit field RXF over, bit field TXLFC, bit field TXOFC, bit underscore field TXLDMAC, bit underscore field TXODMAC, bit underscore field RXLDMAC, bit field RXODMAC, bit underscore field address air, bit underscore field bus air, int underscore enable, IRQE, MC145488, slash asterisk system control register asterisk slash 8, 1 asterisk 8F, dummy bits asterisk 1. 3 1 asterisk 5 to 7, factory test modes asterisk 1. 1 1 asterisk 4, DAC enable asterisk 1. 2 1 asterisk 2 to 3, wait state select asterisk 1. 1 1 asterisk 1, software reset asterisk I. 1 1 asterisk 0, bus width, status, asterisk 1. 1 asterisk master status register, vector. 8, 1 asterisk 8F, dummy bits asterisk 1. 4, 1 asterisk 4 to 7, user programmable bits asterisk 1. 4, 1 asterisk 0 to 3, vector number asterisk 1. 1 asterisk interrupt enable register asterisk 1. 1, 1 asterisk F, SCP interrupt enable asterisk 1. 1, 1 asterisk E, CDI interrupt enable asterisk 1. 1 1 asterisk D, CDO interrupt enable asterisk 1. 1, 1 asterisk E, CH1 idle interrupt enable asterisk 1. 1, 1 asterisk B, CH0 idle interrupt enable asterisk 1. Asterisk 1. 1, 1 asterisk A, receive buffer overrun int enable. 1, 1 asterisk 9, transmit FIFO underrun int enable. 1, 1 asterisk 8, receive FIFO overrun int enable asterisk 1. 1 1 asterisk 7, CHTX frame complete int enable. 1 1 asterisk 6, CHTX frame complete int enable. 1 1 asterisk S, CHTX DMA complete int enable asterisk 1. 1, 1 asterisk 4, CHTX DMA complete int enable asterisk 1. 1, 1 asterisk 3, CHRX DMA complete int enable asterisk 1. 1, 1 asterisk 2, CHRX DMA complete int enable asterisk 1. 1, 1 asterisk 1, address error interrupt enable asterisk 1. 1 1 asterisk A, bus error interrupt enable asterisk 1. Figure 7 to 7. DDLC type def IC language. Asterisk 1. Asterisk 1. Asterisk 1. Asterisk 1. Motorola. 7 to 9. Motorola. 7 to 10. Type def union. Integer scpreg. Struct. Bit field. Bit underscore field. Bit underscore field CI. Bit field BR. Bit underscore field N1. Bit underscore field ENO. Bit field TXN. Bit underscore field TXRX. Scpreg. SCP. Type def union. Integer timer. Struct. Slash asterisk. Bit underscore field. Bit underscore field TIRQ. Bit underscore field WDE. Bit underscore field 10. Bit underscore field count. Timer. Timer. 1. 1. 1. 2. 1. 1. 1. S. 5. 1. 1. 1. S. 1 asterisk SCP status L control register asterisk 1. 1 asterisk F, SCP complete asterisk 1. 1 asterisk E, /master select *1. 1 *d, SCP clock invert *1. 1 *bc, SCP baud rate select *1. 1 *a, SCP enable 1 *1. 1 *9, SCP enable 0 *1. 1 *s, SCP transmit enable *1. 1 0 to 7, SCP TX/RX register *1. / timer register */ 1 *bf, dummy bits *1. 1 *a, timer interrupt status bit. 1 *9, watchdog enable, chan 0 only, *1. 1 *s, timer enable *1. 1 7 to 0, S-bit timer register *1. Structure of the channel status / control and buffer descriptor registers. *1. Type def struct. Union. Integer ser cont. Struct. Bitfield. Bitfield SCPE. Bitfield tol. Bitfield loop. Bitfield TRSP. Bitfield mode. Bitfield mask. Serial control. Ser control. Union. Integer tx3. Struct. Bitfield. Bitfield 01. Bitfield fa. Bitfield MD. Bitfield FCE. Bitfield ITF. Bitfield BR. Bit_field TE. T.X control. TX cont. 1. 1. 1. 1. 1. 3. 8. 9. 1. 1. 1. 1. 1. 1. 1. 1 * channel status / control registers *1. 1 *f, dummy bit *1. 1 *e, SCP enable *1. 1 *d, transmit on loop *1. 1 *c, loop back *1. 1 *b, transparent operation *1. 1 *sa, mode bits *1. 1 0 to 7, bit mask register *1. / transmit control register // 7f, dummy bits // 6, data invert */ 1 5, force abort *1. 1 4, mask drive *1. 1 3, force CRC error */. 1 2, interframe time fill *1. 1 1, buffer ready *1. 1 0, transmit enable */. Figure 7 to 7. DDLC type def, C language, continued. MC145488. MC145488. Union I * receive control register *I. Integer RxCNTR. Struct. Bitfield, 9, 1 7f, dummy bits *I. Bitfield, D1, I * 6, data invert *1. Bitfield, ABS1, 1 5, address byte select *I. Bit_field ACE1, I * 4, address compare enable *I. Bitfield, RCE1, I * 3, receive on CRC error *I. Bit_field BBR1, I * 2, buffer ready *1. Bit_field bar1, I * 1, buffer ready *I. Bitfield 1 rupee, I * 0, receiver enable *1. RX_control. RX cont. Union I * transmit status register *1. Integer tx status. Struct. Bit underscore field 10, I asterisk 6f, dummy bits asterisk I. Bit field fun 1 I asterisk 5, FIFO under run asterisk I. Bit field, TFC1, I asterisk 4, transmit frame complete asterisk I. Bit underscore field CTS1, I asterisk 3, CTS status asterisk I. Bit field B1, 1 asterisk 2, bus error asterisk 1. Bit field, AE1, 1 asterisk 1, address error asterisk I. Bit underscore field TDC1, I asterisk 0, transmit DMA complete asterisk I. TX underscore stat. TX stat. Union I asterisk receive status register asterisk I. Integer RX status. Struct. Bit field, CD1, I asterisk F, CD pin status asterisk I. Bit field, RI1, 1 asterisk E, receiver link idle asterisk I. Bit underscore field CE1, I asterisk D, CRC error asterisk I. Bit field, DIRC1, I asterisk C, CD interrupt status asterisk 1. Bit underscore field FO1, I asterisk B, FIFO overrun asterisk I. Bit underscore field RC3, I asterisk 8A, residue count asterisk I. Bit field 2, I asterisk 6 to 7, dummy bits asterisk I. Bit underscore field B1, I asterisk 5, bus error asterisk I. Bit field AE1, I asterisk 4, address error asterisk 1. Bit field BBD1, 1 asterisk 3, buffer B overrun asterisk 1. Bit field BLED1, I asterisk 2, buffer A overrun asterisk 1. Bit underscore field RBC1 I asterisk 1, buffer B complete asterisk I. Bit underscore field RAC1, I asterisk 0, buffer A complete asterisk I. RX underscore status. RX stat. Struct 1 asterisk address compare registers asterisk 1. Char add comp 1, 1 asterisk 8f, compare address 1 asterisk 1. Char add compo, I asterisk 0 to 7, compare address 0 asterisk 1. Add CMP. Union I asterisk wildcard register asterisk 1. Integer wild. Struct. Bit underscore field 8, I asterisk 8f, Duruni bits asterisk I. Bit underscore field wildcard 8, I asterisk 0 to 7, address wildcard bits asterisk 1. Wild bits. Wild bits. Figure 7 to 7. DDLC type def, C language, continued. Motorola. 7 to 11. Motorola. 7 to 12. Slash asterisk. Union. Integer CRC air. Struct. Bit underscore field. Bit underscore field CRC error. Cris errors. CRC error C. Integer TXFR len. Integer TX base. Integer TX byte CNT. Integer RX buff len. Integer RXA base. Integer RXA byte CNT. Integer RXB base. Integer RXB byte CNT. CH underscore regs. Slash asterisk CRC error count asterisk slash. 8, slash asterisk 8f, dummy bits asterisk slash. 8, slash asterisk 0 to 7, CRC error count asterisk slash. Slash asterisk transmit frame length asterisk slash. Slash asterisk transmit buffer base address asterisk slash. Slash asterisk transmit byte count asterisk slash. Slash asterisk receive buffer length asterisk slash. Slash asterisk receive buffer A base address asterisk slash. Slash asterisk receive buffer A byte count asterisk slash. Slash asterisk receive buffer B base address asterisk slash. Slash asterisk receive buffer B byte count asterisk slash. Type def of the complete DDLC register structure. Asterisk slash. Type def struct. Syscontrol system. Master status mstat. IRQE interrupt. Integer select 16. Slash asterisk. Integer unused underscore space 04. SCP. Timer timeout 2. Integer unused underscore space L5. chregs 2. DDLC. Slash asterisk system control register asterisk slash. Slash asterisk master status register asterisk slash. Slash asterisk interrupt enable register asterisk slash. Slash asterisk dummy register for 16-bit bus asterisk slash. Slash asterisk unused space asterisk slash. Slash asterisk SCP register asterisk slash. Slash asterisk timer registers asterisk slash. Slash asterisk unused space asterisk slash. Slash asterisk channel status slash control registers asterisk slash. Definition of global dole pointer. Asterisk slash. DDLC asterisk DDLC underscore PTR. Figure 7-7. DDLC type def, C language, continued. MC145488. Hashtag define address exp. Hashtag define address mask. Ox 00528000L. Oxofool. Slash asterisk. Asterisk slash. DDL's buffer alloc allocates non-relocatable memory that resides completely on a single 64K byte page. The requested size must be a global constant void, asterisk address exp should contain the address of the address expansion register. Typically, this value will be 5280000H or 52C000. Calling syntax, void asterisk DDL's buffer alloc, unsigned long buffer size. Functions called internally. Return value, if success. If failure. Mlalloc, relalloc. Pointer to allocated buffer. Null. Void asterisk DDL's buffer alloc, buffer size. Unsigned long buffer size. MC145488. Int asterisk address exp void asterisk big underscore buffer. Unsigned long int extra page. Unsigned long int first underscore page. Address exp vo asterisk, address exp. Slash asterisk pointer to address exp register asterisk slash. Slash asterisk pointer to original requested buffer asterisk slash. Slash asterisk temporary data asterisk slash. Slash asterisk temporary data asterisk slash. If, buffer size, long, ox 000100000, return void asterisk, null. Slash asterisk allocate twice as much as requested asterisk slash. If big underscore buffer, void asterisk, mlalloc, buffer size L, void asterisk, null. Return, big underscore buffer, slash asterisk allocation failure return null asterisk slash. Extra page unsigned long, big underscore buffer plus buffer size, and address mask. First page, unsigned long, big underscore buffer and address mask. If, extra page first page. Long int length. Slash asterisk requested buffer overlaps 64K page boundary, use the higher page asterisk slash. Address exp int, extra page 16, slash load address expansion register asterisk slash. Length extra page, unsigned long, big underscore buffer plus buffer size. Slash asterisk deallocate unused space above requested buffer asterisk slash. If, relalloc, big underscore buffer, length, void asterisk, null. Return void, null, slash reallocation failure, return null asterisk slash. Return void asterisk, extra underscore page. Else. / requested buffer fits on a single 64K page */ address expreg, int, first page 16, / load address expansion register */ if, relalloc, big _ buffer size, void *, null. Return void, null, / reallocation failure, return null */. Return, big _ buffer. Figure 7-8. DDLS buffer allocal, procedure IC language. Motorola. 7-13. Since the own pins are driven high or low during a DMA cycle, they cannot be simply connected together. To control 1374, diodes are used to wire or them together. One of the own pins is active when the DDLC is the bus master and is executing a DMA cycle. At all other times, the address expansion register is held off of the address bus in a high impedance state. Both channels share the same 64K byte buffer area in this design example. If the two channels need separate pages, two address expansion registers can be provided, each controlled by its own pin. See Figure 7-9. DDLS buffer alloc should be appropriately modified so that it can load page addresses into two separate 374 registers. This scheme can be expanded so that each receiver and transmitter has its own buffer page by using the R/W pin to further decode the own pins. The Macintosh control bus has a few special signals which are not used directly by the 68000. ext.dtk disables the Macintosh's internal DAC generator, allowing an external device to generate its own DAC. The chip select line to the DDLC is connected to ext.dtk, so the DDLC's internal DAC generator may be used, DCND 13-10. Timing of the Macintosh bus is slightly different from the 68000. In particular, as of an external bus master, the DDLC must not change around the rising edge of the Macintosh's S3 state. DCND 13-14. Since the DDLC is not synchronized to the Macintosh bus and its S signal changes on a rising edge, the MCLK to the DDLC is derived from the C8M signal and inverted. 7.2.1.3 INTERRUPTS. The DDLC provides several interrupt vectors to the host processor. The Macintosh cannot, however, use these vectors directly. Instead, the auto vector capability of the 68000 is used, DCND 13-16. A gate array in the Macintosh generates a VPA signal to the 68000 whenever an interrupt vector fetch is made, which initiates auto vector operation. The processor fetches an address located in the auto vector area and jumps to that location. There are 7 auto vector locations in the system. All 27 interrupts generated by the DDLC are grouped into the level 5 auto vector location 0074H. Similarly, interrupts generated by the MC145488 SID transceiver are assigned to the level 3 auto vector location 006CHL. The Macintosh system uses level 2, and level 4 interrupts for its own uses. Level 1, the lowest priority. When a level 5 interrupt is detected, the interrupt handler in the terminal card software package looks at the master status register in the DDLC and jumps to the appropriate routine based on the value in the register. When a level 3 interrupt is generated, a special routine accesses the SID transceiver through the SCP in the DDLC. Interrupt handlers will be discussed in greater detail in section 7.2.2.2.5. 7.2.1.4 PAL device. A 16L8 PAL is used to generate chip select signals to the DDLC and 374 address. Expansion register. The base address of the DDLC is 5200000H and the address of the address expansion register is 528,001H. 5200000H was chosen as the base address because it is in an area that does not have RAM and is not used for Apple factory testing, DC and D13 to 16. The PAL also generates an inverted MCLK for the DDLC. When the card is installed in the second wave expanse chassis, available from second wave, Austin, Texas, 512-343-9661, the inverted clock is not used and MCLK is connected directly to the C8M signal of the chassis. The PAL is programmed to provide a chip select for a second address expansion register even though it is not used in this example. The design equations for the PAL are /5200000H equals /A23.A22/A21A20/A19/A18/A17/A15/A14/as /52800 equals /A23.A22/A20/A19/A18/A17/A15 /A14/as/LDS /52COL equals /A23.A22 /A21.A20/A19/A18.A17.A15.A14/as/LDS /MCLK equals /C8M 7.2.1.5 serial buses. Two serial buses connect the SID transceiver, DDLC, and codec/filter. The IDL bus transports data while the SCP bus transports control information. The following paragraphs describe the operation of the two buses. Motorola 7-14 MC145488 Macintosh SE expansion bus connector ISDN 4-wire SID interface 1 II -11 interface and TXP1I voice circuitry 1 protection 110L bus R underscore asterisk underscore 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 I underscore OL underscore B underscore U underscore S underscore underscore T dash 4 G all bus ha ETI network F ITXN14 IIISCP bus MC145541 1 SCP bus IT, LO dash underscore underscore dash 1 SFT bus 1411 1 transceiver 1 MC14544741 general purpose output L underscore 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 dash JTFNTI interface and RXPI protection or 1 dot dash dash network RXN control OGNT dot dash dash I underscore 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 BI underscore underscore I plus 5V dash plus 5V as I6 47 50 53 54 57 5B 4 44 45 4B 49 55 56 59 60 1 Data bus JL do CLC.14 01 02 dash dash slash 0 underscore 3 underscore R04 underscore dash colon 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 JCLB 05 dash R colon colon dot underscore dot IC1S slash 0 6 underscore 07 DB 09 V010 R dash equals dash roll dot CL underscore 012 R 013 CZ7 014 R 015. R UC 29. Plus 5V plus 5VC. C. 34 underscore. Dash dash. AC. Note 1 Burp. 47K. Optional. 01526 015071 LB 0719 1823. R dash dash R dash J430WNL. R dash dash R dot 0-0-420WNO. 01425 01406 117 0716 1N. 10606R. 520000H underscore. 52COOLH underscore. 52BOOLH underscore. Notes. Dash LB. Dash 17. R16. Ampal 16 LB. Chip select. Generator. 19. 14 IDS. 13 as. A23. 9. B. 7. 6. 5. 4A17. R011. 2 BCS. IPL 2012. RIP underscore L0T. RL equals dash asterisk 3I6IRQ. RB equals colon dot GA colon C K underscore R dash 1 underscore 0 underscore 3 underscore 4 dash 1. GAC. GB40 BG. Comma dash underscore 39. VOTAC 37. R dash 1 OTAC. RUO, S underscore dash colon, 3 dash equals. VRLDC.S underscore equals C3 colon JL los. VRAS equals dash underscore dash equals 3 dash equals I0 S. RRIW underscore Z, 7R slash W. V. R underscore 029 MCLK. Reset 33 underscore. VR plus dash. 35. Dash. RST. MC1454BB. Dual data link. Controller. Base address equals $520,000. 3. 2. 1 R. VSS. 2. B. L. ONMO colon T in. C. 16B 67 66 65 64 63 62 61. Joule. 12 FTRA. 15 CBM dash. No 2. Address bus. O underscore NMCTN. Control bus. 01324 013 05 14 05 051 dot 5 underscore dot dash underscore dash A2. 012 1 2 dot 3 colon point 012 /104 equals comma 1 underscore equals 1304 41 colon 2 T1 colon 0820. 22011003 IB MC145488 011F colon dot IRL 0303R 9 equals comma underscore colon slash 010201902 I70202 R6 comma I underscore A underscore B 09190901140101 R5 1 underscore A 17 db1b db do 13 do 00 r2 equals dash comma dot dash underscore a underscore 6 0717 0710 ECLK1 0616 06 input 100 res equals 2t minus 0.2 L underscore I 0515 0552 C001 H 0414 04 0313 0307 LB 0707 19 823 slash 0212 02 backslash 0.0 dot 6 underscore 706061 dash underscore 6t underscore ta underscore 22 slash 0111011 dash equals 0 colon 5 underscore colon 0.1 dash 140505 r c colon 5t underscore ra colon 21j do 10 underscore dash comma 0 I 0 dot 0.4 underscore CI 304041 dash 12 T underscore TA underscore 20 slash 0 dot 3 underscore B103 MC14 HC374 Q3 R9 equals dash plus A underscore 9 slash VSSN 911 1 plus JB 02 dash underscore comma dash 710202 T6 equals dash plus AB slash 01 dash underscore 4 underscore 101011 dash 4 equals dash plus A 17 0 underscore 3 dash 100 R2 dash plus Al 6 input address equals L70E underscore colon CLRKC 52B001H111 1 If only one address expansion register is used, the anodes of the diodes can be connected together effectively wire O-ring OWNO and OWNL together onto the output enable pin of the 374. If two 374s are used, the diodes may be removed and the ON pins connected directly to the 374 output enable pins. The pull-up pins must still be used as the ON pins are high impedance while not in DMA. 2 Joule is a clock selector for the DDLC. The PAL is programmed to be an inverter from pin 15 to pin 12. When this board is installed directly into a Macintosh SE, the MCLK should be inverted from the CBM signal on. The expansion connector. If a second wave expanse chassis is used, MCLK should not be inverted. MC145488 JL A.4 slash A dot colon 2 equals dash A 3 underscore A6 A 4 A.7 RA5 equals dash A 6 A 7 dash A B underscore A 9 A.12 Al 0 R A13 all RU underscore A14 A 12 dash A.15 A6 4 dash R underscore 5 underscore A 16 dash A 19 R A 20 RU A23 A 21 R A.25 A.26 Address bus JL slash CBC M underscore RIPO IPLLB.19 IPL2 B.20 GAC.4 C.3 BG dash equals dash IC5 OTAC colon R slash R dash dot colon dot IW underscore as IDSCB. UDS. Equals R equals dash dash dash. Reset dash, C.12. EXTOTK. B26. V. B13 to 17, C13. B.3Z. GNOR. Control bus. Figure 7 to 9. Macintosh SEISDN. Terminal card, MPU section. Motorola. 7-1517-16. 7.2.1.5.1 IDL bus. The IDL bus is a 4-wire serial bus which transports serial data between the DDLC, SID transceiver, and codec/filter. This bus is described in detail in section 6.1. Since the SID transceiver is the IDL master, its TX pin is connected to the RX pins of the DDLC and codec/filter. Likewise, the SID transceiver's RX pin is connected to the other device's TX pins. The sync pins of the devices and CLK pins are connected to their respective mates. Recall that the DDLC has two independent IDL interfaces. Since they are on the same bus, they are simply connected together. Of course, the two channels must not be programmed to operate on the same IDL time slots at the same time. The codec/filter operates on the IDL B1 channel, so the DDLC is programmed to use the other B channel and the D channel. The SID transceiver has the capability to switch B channels internally, so the DDLE and codec/filter can access either B channel on the ISDN SID bus. 7.2.1.5.2 SCP bus. The Macintosh's 68000 communicates with the MC145484 SID transceiver's internal registers through the DDLC's SCP port. Operation of the SCP from the DDLC's point of view is described in detail in section 6.4. Figures 7 to 10 and 7 to 11 describe 2C routines which communicate to the SID transceiver. ST-read-write is a routine which accepts the data direction, read or write, the SID transceiver register address, and the data to be written. SCP_transfer actually performs the data exchange with the SID transceiver. Transceiver nibble registers need a 1-byte access, direction, address, and data, on a write, are all in 1 byte. Byte registers need 2 accesses where the first 8-bit exchange passes the direction and address to the transceiver and the second exchange passes the data. For more details on the operation of the SID transceiver, consult the MC145484 datasheet. 1 star. *ST-read-write. *ST-read-write is a low-level device driver for communication. With the MC145484 SID transceiver. Asterisk. 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 Calling syntax: int st-read-write, int dir, int address, int data. Int dir, data direction 1 equals read, 0 equals write. Int address, address of SID transceiver register to be accessed. Int data, data to be written. Don't on a read. Functions called internally, SCP_transfer. Return value, data read from SID transceiver. *1. Int st-read-write, int direction, int address, int data. Char data _byte equals 0, 1 * temporary storage of transmitted data *1. If direction, data _byte equals char, aux80. If address equals aux0070r. Data _byte 1 equals char, address and aux007f. SCP_transfer, data_byte. Data_byte equals, char, data. Else. Data_byte 1 equals, char, address 4. Data_byte 1 equals, char, data and aux of. Return, SCP_transfer, data_byte. 1 asterisk if read, set the direction bit */. 1 asterisk byte register access to address *1. 1 asterisk 70H to 7FH, mask unused bits, *1. 1 asterisk first 8-bit exchange. *1. 1 asterisk, send the address *1. 1 asterisk now prepare the data. *1. 1 asterisk, for the second exchange *1. 1 asterisk nibble register access */. 1 asterisk address 0 to 6H *1. 1 asterisk set the transmitted data. *1. 1 asterisk begin the 8-bit exchange. *1. 1 asterisk, and return the result *1. Figure 7 to 10. ST read write, procedure IC language. MC145488 Motorola. 7 to 17. / asterisk. Asterisk SCP_transfer. Asterisk. Asterisk SCP_transfer prepares the DDLC for communication. Asterisk with the MC145474 SID transceiver and performs the transfer. Asterisk. Asterisk calling syntax, int SCP_transfer, int data. Asterisk int data, address or data to be transferred to SID transceiver. Asterisk. Asterisk this function expects a global pointer to the DDLC register structure. Asterisk extern DDLC asterisk DDLC_PTR. Asterisk. Asterisk functions called internally, none. Return value, data read from SID transceiver. Asterisk for write cycles this is unknown data. Asterisk 1. Hashtag define on equals 1. Hashtag define off equals 0. Int SCP_transfer, char data. Extern DDLC_PTR, / pointer to DDLC register structure */ DDLC_PTR-scp.scpreg.txrx equals data. DDLC_PTR-scp.scpreg.eno equals on. DDLC_PTR-scp.scpreg.txn equals on. While DDLC_PTR-scp.scpreg.txn. DDLC_PTR-scp.scpreg.eno equals off. Return, DDLC_PTR-scp.scpreg. / load the data into the DDLC */. / set the eno bit */. / enable the SCP transmitter */. / wait for the exchange. *// to complete *// turn off eno bit *// return the data, for write cycles *// this is unknown data, */. Figure 7 to 11. SCP transfer, procedure, C language. SCP_transfer, does not use the interrupt capability of the SCP module. In most cases when the DDLC is the SCP master, polling the TX bit may be more efficient. In other applications where the DDLC is an SCP slave, the SCPC interrupt is probably the most efficient way of detecting that an asynchronous SCP exchange occurred. 7.2.1.6 SID transceiver and line interface blocks. The MC145474 SID transceiver connects directly into the system through the SCP and IDL buses. Figure 7 to 12 describes the connections. The IRQ signal is assigned to interrupt level 3 by wire O-ring IPL0 and IPL1 through diodes. DREQ and DGNT are connected to DDLC channel 1. DREQ and DGNT pins, RTS and CTS, and the SCP and IDL buses are connected. The ISET resistor is selected to be 33K, which sets the transmit current to be compatible with 1 transformers. A 15.36 MHz crystal is connected to generate the master clock for the SID interface. This clock generates the timing for the IDL bus and is asynchronous to the Macintosh's master clock. The TE/NT pin is connected to +5V, selecting the TE mode of operation. Figure 7 to 13 describes the interface and protection blocks which protect the SID transceiver from high-level transient signals that exist on the twisted pairs of the SID bus. The terminating resistor on the receive pair may or may not be needed, depending on the installation. 7.2.1.7 Codec/Phi LTERB lock. The MC145584 is a general-purpose codec/filter which converts analog voice signals into digital data that is transmitted over the SID bus B channels. It communicates with the SID transceiver via the IDL bus on the B1 channel. Clock signals for the codec/filters 8 and DA are provided by the IDL-CLK. The SID transceiver is programmed to generate a 2.048 MHz IDL-CLK. Motorola 7 to 18. MC145488. MC145488. TXP. TXN. RXP. RXN. Control bus R-L I 2115 NI TXP SCP cell I 14 CLK 20 SCP CLK TXN 12 RX SCP TX I SCP RX 13 TX I1 J equals ISETI 33K8 sync IDL sync I 3RX9 CLK IDL CLK P11TX IDL TX 210RXI RXN IDL RX IPL0165 IROD grant II IPIT Drioist 7I Reset 22 Reset TE/NT 4 XTLEXTLI 19 10M 18I 15.36 MHz I-01 30PF J 30PF SCP bus IDL bus DANT DREO TLNT Figure 7 to 12 Macintosh SE ISDN terminal card SID transceiver section ISDN SID bus transmit pair 20V Varistore 11.1:1 VDD NVL.FV/RTXP Figure 7 to 13 ISDN transmit pair interface and protection Motorola 7 to 19 Figure 7 to 14 shows the connection of the codec/filter to the IDL bus and the analog circuitry for the handset. R1 and R2 set the gain of the signal from the microphone. R5 sets the bias current through the microphone. R4 sets the attenuation for the received signal which is applied to the speaker. R3 sets the side tone, feedback from mouth to ear. Resistor values shown are selected for a typical telephone handset. With a carbon microphone, if an electret microphone is used, R1, R2, and R5 will change values to compensate for the different bias and gain characteristics of that microphone. Bypass capacitors C2 and C3 should be laid out close to the codec/filter chip. Placement of the ground paths around the codec/filter are critical to achieving the best possible analog performance. 7.2.2 Terminal Card Software. The following section describes the software package of the ISDN terminal card. Figure 7 to 15 is an overview of the software. 7.2.2.1 Software Functional Description. The general structure of the DDLC demo software is shown in Figure 7 to 15. The following functional blocks may be identified. Transmit and receive are the highest level routines which control the sequence of events required for proper transmission or reception of files. Data link layer, that implements a HDLC data link protocol, with a sliding window, numbered, data flow control and go back and automatic retransmission error recovery. Two primitives are included in this functional block, DL_data_request and DL_data indication. The first is called by the application whenever a packet containing data from a file needs to be transmitted. The procedure checks the state of the transmission window, and determines whether the packet may be accepted by the data link layer. The second procedure is called by the application to determine if a received data packet is available for processing. If it is the case, and before returning control to the application, the DL_data_ indication procedure sends an acknowledge message to the peer entity at the other end of the data link with an acknowledge number corresponding to the received frame. Physical layer provides a reliable data path between the upper data link layer and the hardware interface. Two primitives are implemented within this block, ph_data_request and ph_data_ indication. The first is executed whenever the upper data link layer requests that a packet be given to the DDLC for later transmission. The second is called by the same entity to determine whether or not a frame has been received that requires further processing. Transmission queue and a reception queue, which are used to exchange data between the application and the DDLC. When a packet of data is ready to be given to the DDLC, to be later transmitted as a frame, it is placed in the transmission queue, from where the appropriate handler will access it and give it to the DDLC to be transmitted. When a data frame is received, it is placed in the reception queue by the interrupt handler, so that it may be accessed by the application. Hardware interface is responsible for handling the hardware present on the card, mainly the DDLC itself. Within this block, the interrupt handler processes all of the interrupts originated from the DDLC as part of its normal operation: transmit frame complete interrupt, frame received interrupt, etc. Additional hardware drivers are required to initialize the DDLC, enable/disable its interrupts, and perform other maintenance functions. Management entity, that provides for additional services required to link all the functional blocks of the application. 7.2.2.2 Description of the individual blocks. What follows is a discussion of the issues concerning the implementation of the functional blocks of the software. Motorola 7-20 MC145488 MC145488 Dash MC145554 FSR Sync 12 FSX RX11 DX TX DR 1.bk 10 bclkx clk mclkx mclkr/pdn 13 tsx blckr/clsil voice circuitry and handset vfxi plus 16 vfxl 15 14 gsx vfro 4 vcc gnda vbb 0.1 pf dash 5v vdd dash equals 0.1 pf plus 5v L underscore 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 dash dot j IDL bus figure 7 to 14 Macintosh SEISDN terminal card codec/filter section management entity transmit J receive I 1 data link layer underscore L underscore underscore DL data rujust J IDL underscore data underscore annoycation J physical layer L dash IPPHH underscore Redaltia underscore RRECEULUEESSTT2 LRPH dash underscore DATA underscore L dot in CATL on 1 transmission Q hardware I drivers hardware interface reception Q 1 I interrupt I handler figure 7 to 15 terminal card software block diagram Motorola 7 to 21 7.2.2.2.1 Transmit procedure. The transmit functional block of the DDLE demo software is actually composed of three main procedures: transmission, transmit, and transmit_packet. The sequence of actions implemented by these procedures is as follows. Transmission: the transmission procedure is the first one to be executed, right after the transmit button is selected from the main window. It calls a procedure from the management entity to install the terminal card, and after that, displays the Macintosh standard file package so that the user may select which file is to be transmitted. The procedure then opens both data and resource forks of the file, and sends a numbered frame containing both the file type and file creator of the file to the data link layer. This finder-related information is required by the peer station to be able to create a file with the same characteristics as the one whose data is to be received. It must be emphasized that this first message is numbered. Indeed, the transmission procedure will provide the data link layer with a data packet that will be processed exactly as if it were a file data packet. This way, the data link layer will retransmit this first setup frame until the proper acknowledge is received. Having done this, the transmission procedure is ready to start sending the file. To do this, it executes successive calls to the transmit procedure, requesting transmission of the data fork and resource fork of the file, respectively. Transmit: this procedure controls the transmission of a file fork, data or resource. It receives two input parameters: the DDLE channel through which the data is to be sent, the file reference number of the file fork to be transmitted. The procedure first determines the length of the file. If it is longer than 32 KB, a 32 KB memory block is requested from the operating system, and the transmission of the file will proceed in blocks of 32 KB each. Otherwise, the application requests a memory block long enough to load the file fork into memory. The transmit procedure initializes a status window, which displays the following information: the name of the file being transmitted, whether its data fork or resource fork is being transmitted, and how much, in percentage, of the file has been transmitted. Then it interleaves calls to the transmit_packet procedure with calls to a management entity procedure to update the information contained in the status window. The user has the option of suspending the transmission of a file at any time. Transmit_packet, this procedure receives three input parameters: the DDLE channel through which the data is to be sent, a pointer to the buffer containing the data packet to be transmitted, the length, in bytes, of the packet to be transmitted. The procedure transfers the data intended for transmission, which is in the memory buffer the file was read to, along with a packet header, to another memory buffer, and passes it to the data link layer for further processing. The sequence of actions involved in the transmission of a file is schematically described in Figure 7-16. 7.2.2.2.2 Reception Procedure. The reception functional block of the DDLE demo software is actually composed of two main procedures, reception and receive. The sequence of actions implemented by these procedures is the following. Reception. This procedure first displays the Macintosh standard file interface to request the user to input a name to be given to the file, whose data is to be received. After this, it waits for a preliminary frame. Motorola 7-22 MC145488. Get name of file to transmit. Figure 7-16. Transmit procedure. File data in memory to be received. Recall that the program will wait until either the proper frame is received or the user clicks the quit button. The latter will cause the program to return to the main window. This preliminary frame contains the file type and creator of the file that is to store the data to be received. After the preliminary frame has been received, the reception procedure initializes a status window, similar to the one displayed during the transmission sequence, which displays the following information: the name of the file being received, whether its data fork or resource fork is being received, and how much, in percentage, of the file has been received. Then, it executes consecutive calls to the procedure receive. To process the reception of both the data and the resource forks of a file, it implicitly assumes that the data fork is sent first, and then returns to the main window. Receive. This procedure is called to control the reception of a file fork, either data or resource. It receives two input parameters: the file reference number of the file fork to be received, the length of the file to be received, in bytes. The procedure requests a 32 KB buffer of memory to store the incoming file, and successively checks the data link layer, by issuing calls to the procedure DL_data_indication, to see if any data packets are available for processing. In doing so, it interleaves calls to a management entity procedure to update the information contained in the status window. The user has the option of suspending the reception of a file at any time, and updates the information contained in the status window. The sequence of actions involved in the reception of a file is schematically described in Figure 7-17. Get name of file to receive. Figure 7-17. Reception procedure. MC145488 Motorola 7-23. 7.2.2.2.3 Data link layer. From a procedural point of view, this is the most important part of the software. The data link layer provides a reliable interface between the application's data transfer needs and the available physical resources. Furthermore, it provides with flow control and error recovery so that A. Potentially faulty, physical link becomes an error-free physical link. It is made up of two main procedures. DL_data_request, this procedure is called by the application whenever a data packet needs to be sent through the link. It receives three input parameters: the DDLC channel through which the data is to be sent, the pointer to the memory buffer that contains the data packet, the length, in bytes, of the data packet to be sent. Before trying to process a data packet, the data link first checks to see if any pending acknowledges have been received. If so, it updates the transmission window, and then checks the state of the transmission window. If the window is exhausted, i.e., the maximum number of frames is pending to receive acknowledge, it returns control to the application, with a value that indicates that the message couldn't be processed. Otherwise, the data packet is first copied in an internal storage area of the data link, along with a timestamp indicating the moment of acceptance of the packet, and then the packet is duplicated to a buffer in the memory area of the DDLC, with a data link header inserted into it. Finally, the data packet is passed to the physical layer, for actual transmission by the DDLC. Data_LLNK, indication, this procedure is called by the application to check for data frames received by the DDLC, requiring to be processed. It receives two input parameters: the DDLC channel whose reception status needs to be checked, a pointer to a data structure used to pass information regarding frames received to the application. It accesses the physical layer to determine if there are any received frames in the reception queue. If so, the physical layer passes the first enqueued frame to the data link layer, which in turn passes it to the application. As it may be deduced, whether on transmission or reception of a file, the application allocates the data link software a minimum processor time so data packets can be transmitted/received as soon as possible. In absence of a real-time operating system, this is the best way to allocate a minimum of CPU time to the communication functions of the application. 7.2.2.2.4 Physical Layer. This functional entity is responsible for handling the data structures used as exchange between the application and the DDLC, i.e., the transmission and reception queues. As is the case of the data link layer, it is made up of two main procedures. PH_data_request, this procedure is called by the data link layer to enqueue a data packet that is to be transmitted by the DDLC. Two input parameters are needed: the DDLC channel through which the data is to be sent, a pointer to the transmit descriptor of the data packet. Since this procedure needs to access the transmission queue, it requires that the CPU interrupts be disabled, to provide for mutual exclusion with the interrupt handler. After disabling the interrupts, it checks the queue. If it's empty, it means that no packet is in the process of being transmitted. It also means that the interrupt handler will not be able to service this particular packet. This last issue will be understood when the interrupt handler is explained in detail later on, so its transmission must be triggered with an auxiliary driver. If, on the other hand, the transmission queue has at least one element, it means that a Motorola 7-24 MC145488 packet is in the process of being transmitted, and a transmit complete interrupt will be signaled later on. That will cause the interrupt handler to service other packets in the queue. In this case, the procedure simply enqueues the packet descriptor in the transmission queue, and enables the interrupts back. PH_data_indication, this procedure is called by the data link to check for data packets being received from the physical link. For the same reason as in the previous procedure, This must be executed with the interrupts disabled. It accesses the reception queue, which is also accessed by the interrupt handler. 2. Input parameters are passed. The DDLC channel that needs to be checked for reception. A pointer to a data structure used to pass information regarding frames received to the data link layer. If the procedure finds that a data packet has been enqueued in the reception queue, it is removed and information about it is copied in a message that is passed to the data link layer, a pointer to the storage area that contains the data, and the length in bytes of the data. This last value excludes the 2 bytes corresponding to the CRC. Recall that, in receiving frames, the DDLC does transfer the CRC to memory, but includes the data link header of the frame. Finally, it removes the data packet descriptor from the queue, enables the interrupts, and returns a value that indicates that a valid data packet is being passed to the data link layer. If no data packet is found in the reception queue, it re-enables the interrupts, and notifies it to the data link layer. 7.2.2.2.5 Hardware Interface. As pointed out before, the hardware interface is made up of a set of hardware drivers, and the interrupt handler. Interrupt handler. The interrupt handler is the part of the code that processes the interrupts generated by the DDLC as part of its normal operation. Prior to start execution, the interrupt handler saves all the CPU registers in the stack, and then executes a utility call, setup A5, that forces register A5 of the 68,000 to be loaded with the application's A5 register. This is relevant because any compiler that generates code to execute in the Macintosh is expected to generate global addresses relative to register A5. Thus, by executing the utility call, it is ensured that the interrupt handler will be able to address the global variables of the application. Due to the hardware design of the Macintosh, any device interrupting the CPU is forced to do it through a so-called auto-vectored interrupt. Because of this, the only way to differentiate between different interrupting sources within the DDLC is by reading its master status register. This is the first thing done by the interrupt handler after saving registers and setting register A5. The actions taken by the interrupt handler after this point depend on the actual interrupt source. They are identical for both DDLC channels. Bit handler fault interrupts and system fault interrupts are dealt with by resetting the corresponding bit and resuming the DDLC operation. In some special debug routines, these interrupts are serviced differently. Time zero interrupts cause a tick counter to be incremented. This counter is used as timeout and timestamp clock by the data link layer. Timer 1 is not used in the application. Bit handler normal operation interrupts are handled according to whether they are transmission or reception interrupts. Transmission interrupts, all related bits in the transmit status register are cleared, and the transmission queue is checked to see if any more data packets need to be transmitted. If so, the DMA transmit base address register is loaded with the offset of the memory buffer containing the data packet, and the buffer ready bit in the transmit control register is set, so that the DDLC will start transmission again. MC145488 Motorola 7-25. Reception interrupts. In this case, the receive status register is read to determine whether buffer A orb is filled with data. Once this is done, it requests the buffer descriptor corresponding to the data buffer in which the data has b.in stored. Then, the interrupt handler accesses the free, unused receive buffer of the descriptor, loads it in the corresponding receive base address register, and sets the buffer A ready or buffer B ready bit in the receive control register, so that another Received frame may be loaded in that buffer. 7.2.2.2.6 Hardware drivers. This is a set of routines that provide access to the hardware of the DDLC. Demo board. These routines reset the DDLC. Enable/disable interrupts from the DDLC. Enable the individual interrupt sources of the DDLC. Initialize the receive buffer registers of the DDLC. Control the SID transceiver through the serial control port of the DDLC. 7.2.2.3 Implementation issues. 2 implementation issues of the DDLC demo software will be described in some detail. These are the memory buffer management, the flow control and error recovery functions of the data link layer. 7.2.2.3.1 Memory buffer management. One of the most important actions in servicing the DDLC is to supply it with buffers to be used during transmission or reception of frames. The way the DDLC drivers interact with the rest of the application is more or less a classical message passing problem. Packets that are to be sent must be encoded in some output data structure so that the DDLC drivers will see them, whereas packets that have been received must be encoded in an input data structure so that the application will see them. In this kind of message exchange problem, it is generally agreed that it is better to deal with buffer descriptors rather than the buffers themselves. A buffer descriptor usually contains a minimal of information required to completely specify a buffer in memory. Figure 7-18 depicts the information in a buffer descriptor. In particular, descriptors are particularly well suited for queue management. Figure 7-19. Descriptor queues can be either single-linked, an element contains only a reference to the next element in the queue, or double-linked, an element contains references to both the previous and the next element in the queue. Since operations in the exchange structures of the software occur at either the beginning of the queue, when deleting the descriptor of a received frame, or the end, when appending the descriptor of a frame to be transmitted, it is only necessary to implement a single linked queue structure. When the application is first called to run, either for transmission or reception of a file, it creates a small pool of descriptors, each one having assigned a memory buffer. 2 obvious questions to be asked at this time are, why is it necessary to create pool of descriptors? And why is each descriptor assigned to a memory buffer? We will deal with these questions one at a time. With the memory allocation facilities of an operating system, it is sometimes possible to avoid such things as pools, since free memory may be allocated and deallocated at runtime. However, the Macintosh does not allow calls to the memory manager from an interrupt handler. But from the last section, it is clear that the interrupt handler needs to request a free memory buffer to give it to the DDLC after a frame is received, otherwise the DDLC runs out of buffers to store incoming frames, and the receiver circuitry is disabled. The solution in this case is to create a memory management entity that is part of the application itself, and supply it with enough LMATs to satisfy the worst-case requirements of the application. This Motorola 7-26 M worst case number is affected by the window size of both the data link and the number of DDLE channels that may be active at any given time. So the application creates 2 small pools, one for transmit frame descriptors and one for receive frame descriptors. These pools are actually arrays of structures, the structures being the descriptors themselves, addressed in a circular fashion, figure 7-20. After the last element of the pool is used, the first element of the pool becomes the next to be used descriptor. By Making sure that the size of the pools is greater than the maximum number of elements that may be withstanding at any given time. No active descriptor can be mistaken as a free descriptor. With respect to the linking of a buffer to a descriptor, there is a savings in processing time, since the other solution would be to actually have two pools, one for buffer descriptors and one for the buffers themselves. But that would be worthless, especially when one considers that descriptors are consumed at the same rate as the buffers are. There is, though, an additional complexity introduced here, since when a frame is received, its corresponding descriptor must be accessed with the descriptor data structure shown in figure 7-20. The only way to do it is to use the buffer offset as an index to the array that implements the descriptor pool. For small pools, this solution is both simple and fast, but for a larger number of descriptors, additional features must be considered, i.e., a double link between a descriptor and a buffer. Another alternative might be a hash table to store the pointers to the descriptors, and use the buffer offset as an input to some hashing function. 7.2.2.3.2 Flow control and error recovery in the data link layer. As suggested by the layered hierarchy of the ISO model for an open systems interconnection, the data link layer should provide for a reliable logical link between peer processes in the network. Two important issues involved here are flow pointer to next descriptor, memory buffer length, pointer to memory buffer. Figure 7-18. Buffer descriptor. Descriptor number 1, descriptor number 2, descriptor number 3, descriptor in T. Field 1. Field 2. Field 3. 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 Figure 7-19. Linked list of descriptors. Dash. Underscore 13. Figure 7-20. Circular queue of descriptors. MC145488 Motorola. 7-27. Control and error recovery. The first has to do with how can the data link entity controls the amount of data being sent by a peer process. The second refers to the means by which the same data link entity can react to non-permanent errors present in the link. A window flow control scheme is used to limit the number of frames that a data link entity may send without waiting for acknowledgement from its peer process. It means that the data link entity may send a consecutive number of frames equal to the window size, which is usually a multiple of 2, say 2n. In this software, the window size is 8, minus 1. When the total number of frames waiting for acknowledge equals the maximum allowed, the window is said to be exhausted, and the sending side of the link is forced to wait for acknowledge frames. Thus, the receiving side controls the flow of frames from the sending side by withholding the acknowledge of frames received. Normally, nothing prohibits the receiving station from acknowledging various frames at a time. For instance, the receiving station could wait for its peer to send as many frames as possible, and then acknowledge them all with a single acknowledge frame. Nonetheless, in this software, frames are acknowledged as soon as they are received, so the sending station is constantly updating its transmission window. The information required to implement the flow control in the link is contained as a header that is appended to the frame prior to its transmission, figure 7-21. Of all the fields available in the data link header, the only ones used by this software package are the N, S, in the information mode, and the N, R, and the function fields in the supervisory mode, other. Fields are set, but they are never checked, so they are not functionally active. At any given time, an error may take place in a frame being sent that will cause it to be discarded by the receiving station. Obviously, this frame will not be acknowledged, and after a certain time, the sending station realizes that there was an error related to that frame. An error recovery procedure must be initiated, so as to ensure that all frames intended for transmission are received correctly. The way it has been implemented here is through a go-back and automatic retransmission error control procedure. Whenever the data link entity receives a packet to be transmitted, it is duplicated in a local storage area, and a timestamp is associated with it. That way, the data link knows how much time all the transmitted frames have been in the data link. If this time ever exceeds a maximum timeout, this will always occur to the oldest packet in the data link. All the packets stored are retransmitted, and their corresponding timestamps are updated. 7.2.2.4 Summary. This section described in some detail the inner workings of the software associated with the ISDN terminal card for the Macintosh SE. It attempted only to provide direction to future ISDN programmers. The development tool that this data sheet describes is compatible with the ISDN SIT interface from a hardware point of view. The software is in concept similar to what real ISDN software would be like. However, multiple logical links were not considered as they add quite a bit more complexity. Motorola 7-28 SAPI ICR TEL NIR IPIFI NICI Data link header for information frames. SAPI ICR TEL NIR IPIFI Function I. Data link header for supervisory frames. Figure 7-21. Data link headers. EAO EAL 0 EAO EAL 0 MC145488 Section 8 Electrical Specifications 8.1 Maximum Ratings. Rating symbol min-max unit. Supply voltage VDD-0.3 plus 7.0 V. Input voltage yin-0.3 plus 7.0 V. Operating temperature range Ta 0 plus 70 DC. Storage temperature TSTQ-55 plus 150 DC. 8.2 Thermal characteristics. Characteristic. Thermal resistance, still ARL. Asterisk estimated. 8.3 DC electrical characteristics. Rating symbol. Input high voltage VIH. Input low voltage VIL. Input leakage current at 5.5 V lin. High impedance input current at 2.4/0.4 V 1 Hz. Output high voltage, low equals -400 AIVOH. Output low voltage, LOL equals 5.0 mV. Power dissipation PD. Capacitance CIN. Asterisk C section 8.4. MC145488. Min. 2.0. -0.3. 2.4. Asterisk. Max unit. VDDV. 0.8 V. 10A. 10A. V. 0.5 V. MW. 20 PF. Motorola. 8:1. Plus 5.0 V. Test point plus dash dash. TLIIT. 6K. Equals. Figure 8:1. Test load. 8.4 Power considerations. Maximum power dissipation calculations. MPU power consumption PMPU, max, equals 2.5 MW/MHz. Serial power consumption serial, max, equals 2.0 MW/100 kbps. Examples. MCLK equals 8 MHz and aggregate serial data flow equals 256 kbps. Total power dissipations 25.2 MW. MCLK equals 16 MHz and aggregate serial data flow equals 4.096 Mbps. Total power dissipation S122 MW. Motorola 822 740 MM07000 or equivalent. MC145488 8.5 MPU/DMA timing characteristics, 68,000 mode, Ta equals OOCT070C, VU equals 5.0 V plus or minus 10%. Reference. Characteristic min-max unit notes. Number 1. Asynchronous setup time 20, ns1,2. 2. Address valid before CS active 0, ns. 3. R/W, write, before UDS, los active 20, ns. 4. R/W, read, before UDS, los active 20, ns. 5. Data strobe pulse width, write cycle, 20, ns. 6. Data setup time, write, 20, ns. 7. DAC active after MCLK high 035 ns3. 8. DAC active after CS active 1/2 1 plus 35 ns MCLK. 9. Data valid, read, after data strobe active, access time, 80 ns5. 10. DAC active before data valid, read, 35 ns. 11. CS active after data strobe inactive, hold time, 0, ns7. 12. Address valid after MCLK high, hold time, 20, ns4. 13. R/W valid after data strobe inactive, hold time, 0, ns. 14. Data valid after data strobe inactive, write hold time, 0, ns. 15. Data valid after data strobe inactive, read hold time, 2050 ns. 15. A data high impedance after data strobe inactive 025 ns. 16. Chip select inactive to chip select active 1, MCLK. 17. DAC active after chip select inactive, hold time, 030 ns6. 18. DAC high impedance after chip select inactive, 50 ns. 19. Signal active delay 055 ns. 20. Signal inactive delay 055 ns. 21. Signal high impedance delay 060 ns. 22. GAC inactive after MCLK low 030 ns6. 23. GAC high impedance delay, 50 ns. 24. Address valid after MCLK low 055 ns. 25. Address valid before as active 0, ns. 26. Data valid after MCLK high 055 ns. 27. Data valid before UDS, los active 0, ns. 28. Address valid after as inactive, hold time, 20, ns. 29. Address high impedance delay 025 ns. 30. Data, write, after UDS, los inactive, hold time, 20, ns. 31. Data, write, high impedance delay, 25 ns. 32. Data, read, valid before MCLK low, setup time, 20, ns. 33. Data, read, valid after UDS, los inactive, hold time, 0, ns. 34. DAC valid after MCLK high, hold time, 20, ns. 35. BUR valid after MCLK low, hold time, 20, ns. 37 CS and lack inactive after address error sample point 20, NS8. Notes. 1 MPU mode. This is the time that a signal must be valid before a falling MCLK for the access sequence to begin on this MCLK cycle. 2 DMA mode. BG must be active, GAC, and AS must be inactive for 2 successive MCLK edges before a DMA sequence begins on this MCLK cycle. 3. This is for synchronous applications. 4. The address is latched on the rising MCLK edge following the falling edge at which CS was detected low. 5. Both CS, and LOS or UDS, must be active before data is output. 6. This signal may not reach VOH before going high impedance. 7. The bus cycle is terminated when CS goes high. The rising edge of CS may precede the rising edges UDS or LOS. 8. If either of these signals is active when sampled, an address error interrupt is generated. MC145488 Motorola 8-3 Motorola 8-4 MCLK Address RNI Data Figure 8 to 2.68000 MPU write timing. Figure 8 to 3.68000 MPU read timing. MC145488 80 81 82 83 84 AODR+ RNI data dash 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 underscore 4 dash DCK dash 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 underscore 4 dash 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 underscore plus dash input registered input figure 8 to 4 68,000 DMA arbitration and write timing MC146488 8586 Motorola 8-5 80 81 82 83 84 colon dash equals C dash at BR dash dash plus dash 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 RJ address dash 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 1 R/W data dash LNPUT dash dash plus dash high DCK dash 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 underscore plus dash input Motorola 8-6 at figure 8-5 68,000 DMA arbitration and read timing 8586 MC146488 8.6 MCLK timing characteristics reference characteristic number 38 MCLK rise time 39 MCLK fall time 40 MCLK width high 41 MCLK width low 42 MCLK period notes 9. A 50% duty cycle signal should be provided. 10. The DDLC is a static device. Any clock frequency from 2 to 16.67 MHz may be provided. 42R Figure 8-6 MCLK timing diagram MC146488 Min max 15 30 60 Unit notes NS NS9 NS10 Motorola 8-7 8.7 Serial interface modem mode timing characteristics reference characteristic min-max unit notes number 43 RxCLK TXCLK rise time 15 NS 44 RxCLK TXCLK fall time 15 NS 45 RxCLK TXCLK width high 60, NS11. 46 RXCLK, TXCLK width low 60, NS11. 47 RXCLK, TXCLK period 120, NS12. 48 RX data setup time 20, NS. 49 RX data hold time 20, NS. 50 BSYNC low setup time 20, NS. 51 BSYNC high setup time 20, NS. 52 TX data high delay time 30, NS. 53 TX data low delay time 30, NS. Notes. 11 The TXCLK and RXCLK signals should be nominally 50% duty cycle. The width of either phase must be greater than 1 MCLK period. 12 TXCLK and RXCLK may be any frequency up to MCLK/2. Motorola 828. TXGLK, TXD, TXBSYNG. Figure 8-7. Serial interface, modem mode, timing diagram. MC145488. 8.8 Serial control port timing characteristics, TA equals OOC to 70 OC, VDD equals 5.0 V plus or minus 10%. Reference. Characteristic min-max. Number. 54 Delay from internal SCP-TXN to first SCP-CLK edge 1-1/2 2. 55 SCP-CLK period, master model MCLK/2 MCLK/16. 56 Delay from end of MPU bus cycle to SCP-N, 1 or 21 edge, 75. 57 Delay from SCP-CLK to SCP-TX 050. 58 SCP-RX setup time 35. 59 SCP-RX hold time 20. 60 Time from last SCP clock edge to next TXN 1-1/2. 61 Slave select active before rising SCP-CLK edge 50. 62 SCP-CLK high time, slave mode, 30. 63 SCP-CLK low time, slave mode, 30. 63 SCP-CLK period, slave mode, 60. 63B Slave select inactive before SCP-CLK rising edge 50. Notes, 13. Internal SCP-TXN is the end of the bus cycle when SCP-TX is set high. 14 This also applies when the SCP-CLK is inverted with the CI bit. 15 Delay is measured from the end of the MPU bus cycle when SCP-N 0 or 1 is set or cleared. 16 If the SCP module is re-enabled within this time, erratic behavior will result. 17 The SCP-CLK in slave mode should be nominally 50% duty cycle. SCP-CLK output, _+____, J. SCP-N, 0 or 1. Output. SCP-TXN. Internal signal. SCP-TX. Output, _______, SCP-RX. Input, _______, J. SCP-CLK. Input. Slave select. Input. SGP-TX. Output, ______, MC145488. SCP-RX. Input, _____, Figure 8-8. SCP Master Mode. Figure 8-9. SCP Slave Mode. Unit Notes. SCP-CLKS 13,14. NS15. NS14. 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 SCP-CLKS 16. NS. NS17. NS17. NS. NS. Motorola. 8 to 9. 8.9 IDL timing characteristics, Ta equals OOC to 70 degrees Celsius, VU equals 5.0 V plus or minus 10%. Reference. Characteristic min-max unit notes. Number. 64 IDL sync active before IDL CLK falling edge, setup time, 25, ns. 65 IDL sync active after IDL CLK falling edge, hold time, 25, ns. 66 IDL sync inactive before 4th IDL CLK 25, ns. 07 IDL CLK period MCLK/2, MCLK. 68 IDL CLK width high 60, ns 18. 69 IDL CLK width low 60, ns 18. 70 IDL TX active delay 30, ns. 71 IDL TX time to high impedance 25, ns. 72 IDL RX valid before IDL CLK falling edge, setup time, 25, ns. 73 IDL RX valid after IDL CLK falling edge, hold time, 25, ns. 74 time between successive IDL syncs 24, IDL CLK. Note. 18 each phase must be greater than 1 MCLK period. IDL CLK should be nominally 50% duty cycle. 8.10 Serial interface timing characteristics, long and short frame modes. Ta equals OOCT 070 degree C VU equals 5.0 V plus or minus 10%. Reference. Characteristic. Number. 75 TX or RX enable active after TX or RX clock falling edge, long frame. Operation. 76 TX or RX enable active before TX or RX clock falling edge, long frame. Operation. 77 TX or RX enable active after 4th TX or RX clock rising edge, long frame. Operation. 78 time between successive TX or RX enables. 79 TX data valid after TX enable active. 80 TX data valid after TX clock rising edge. 81 TX data high impedance after 9th TX clock rising edge. 82 TX data high impedance after TX clock rising edge, subrate multiplexing. Operation. B3 TX data valid after TX clock rising edge, subrate multiplexing operation. 84 TX data high impedance after TX enable low. 85 TX or RX clock high time. 86 TX or RX clock low time. 87 TX or RX clock period. 88 RX data valid before RX clock falling edge, setup time. 89 RX data valid after RX clock falling edge, hold time. 90 TX or RX enable active before TX or RX clock falling edge, short frame. Operation, setup time. 91 TX or RX enable active after TX or RX clock falling edge, short frame. Operation, hold time. 92 TX or RX enable inactive before 4th TX or RX clock rising edge, short frame operation. Notes. 19 TX data becomes valid after TX clock rising edge or TX enable high, whichever is later. 20 data bits continue to be output after the 8th TX clock as long as TX enable is high. 21 This applies when TX enable returns low before the 8th bit time. 22 Each phase must be greater than 1 MCLK period. A 50% duty cycle should be provided. 23 The maximum serial interface clock frequency can be no more than MCLK/2. Motorola. 8 to 10. Min-max unit notes. 25 ns. 25 ns. 25, NS. 12, CLK. 30, NS 19. 30, NS. 25, NS 20. 25, NS. 30, NS. 25, NS 21. 60, NS 22. 60, NS 22. 120, NS 23. 25, NS. 25, NS. 25, NS. 25, NS. 25, NS. MC145488. S. I. S. LJ. 000. IDLTX, J. IDLRX. IDLTX. With subr TE. Multiplexing. W-FL. Registered. Registered. 1. Underscore underscore underscore. Dash dash, underscore it. H at. B23. Underscore 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 underscore. Figure 8 to 10. IDL timing. Dash dash 78 dash dash. TXN. TXCLK. TXD, I. RXN. RXCLK. RXD. Motorola. 8 to 12. TXD. Figure 8 to 11. Time slot mode timing long frame operation. MC146488. Dash dash 78R dash 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 dash. TXN. TXELK. TXD, J. Figure 8 to 12. Time slot mode timing short frame operation. MC145488 Motorola. 8 to 13. 8.11 MPU/DMA timing characteristics, 80186 mode, TA equals OOCTO70C, VU equals 5.0 V plus or minus 10%. Reference. Characteristic min-max. Number. 93, CS valid before road or WR active 30. 94 address, BHE valid before RD or WR active 30. 95 data valid after road active, read access time, 80. 96 RD pulse width 80. 97 WR pulse width 20. 98 ES valid after RD or WR inactive 0. 99 address, BHE valid after CS active 0. 100 data valid after road inactive, read hold time, 2050. 101 data high impedance after RD inactive, 75. 102 data valid before WR inactive, write setup time, 20. 103 data valid after WR inactive, write hold time, 0. 104 HREQ active delay, 55. 105 asynchronous setup time 20. 106 address valid after MCLK low 055. 107 address valid before road or WR active 0. 108 data valid after MCLK high 055. 109 signal active delay 055. 110 ROI active before T3 rising edge, ROI setup time, 20. 111 ROI active after T3 rising edge, ROI hold time, 20. 112 signal inactive delay time 055. 113 signal high impedance delay time 025. 114 address valid after road or WR inactive, address hold time, 20. 115 address high impedance delay time 025. 116 data valid after WR inactive, write data hold time, 20. 117 data high impedance delay time, 25. 118 data valid before road inactive, read data setup time, 20. 119 data valid after road inactive, read data hold time, 0. Note: 24 This is the time required for a signal to be valid before the MCLK edge if it is to be detected on this cycle. Motorola 8 to 14. Unit notes: NS 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 NS24 NS 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 MC145488. Address, BHE. T plus dash dash, 96, dash dash dash. Data. Figure 8 to 13. MPU read timing, 80186 model. Address, BHE. Dash dash dash, 97, dash dash. Data underscore 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 underscore. C. At FJ dash F dash dash at underscore 3 underscore underscore. Figure 8 to 14. MPU write timing, 80186 model. MC146488 Motorola. 8 to 15. T112 13 14. MCLK. M. R dash 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 1 dash 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 plus dash R dash 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 plus dash dash plus dash V. RIW. Address high. De 1A dash 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 plus dash 109. T. Own underscore. Motorola. 8 to 16. Figure 8 to 15. DMA write timing, 80186 mode. MC146488. T1 T2 T3 T4. MCLK. HREO. Underscore 104. Dash 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 plus dash dash plus dash 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 plus dash yen. Dash plus dash. RRW. AOOR plus 4I. OATA plus dash dash. 109. T. Own underscore. Figure 8 to 16. DMA read timing, 80186 mode. MC146488 Motorola. 8 to 17. Motorola. 8 to 18. MC145488. 9.1 pin assignment. MC146488. IDL Sync 1. 10 LCLK1. CTS1. RTS1. RXO1. TXO1. CDL. VSS. VU. SCPEN. CDO. TXO0. RXO0. RTS0. CTS0. 10 LCLK0. 10 LSync0. Section 9. Mechanical data. 68 lead. PLCC. Top view. 26015. 25014. 24013. 23012. 22011. 21 VSS. 20010, 1909, 1808, 1707, 1606, 1505, 1404, 1303, 1202, 1101, 00, Motorola, 9 to 1, 9.2 package dimensions. Motorola, 9 to 2, ly break/-0, fn suffix, K719-02, B1, 101-810-0071 registered ITIN CLJP CLJIL, MCLJI. U plus or minus 01810.007 registered ITIN CLJPLG LCLJ McLG. Note 1. GL. Plus AR plus RN %100071 registered ITIL CLJ McLG NCLJ ICLG viewed D. H-RRR1. 10.1810.0071 registered. Millimeters inches. Dim min max A 25.02 25.270.9850.995. B 25.02 25.270.9850.995. C 4.204.570.1650.160. E 2.292.790.0900.110. F 0.330.480.0130.019. G 1.27 BSC 0.050 BSC. H 0.660.810.026.032. J 0.510.020. K 0.64 to 0.025. R 24.13 24.280.950 U 24.13 24.280.950 V 1.07 1.21 W 1.07 1.20.0.048. X 1.07 1.40.0.040.056. Y 0.50 to 0.020. Z 210 210. GL 23.12 23.62 KL 1.02 to 0.040. ZI 210 210. Detail S. Notes. 1. Due to space limitation, case 779-02 shall be represented by a general, smaller, case outline drawing rather than showing all 68 leads. 2. Datums L, M, N and P, determined. Where top of lead shoulder exit plastic. Body at mold parting line. 3. Dim GL, true position to be measured at. Datum T seating plane. 4. Dim rand you do not include mold protrusion. Allowable mold protrusion. IS 0.25, 0.0101 per side. 5. Dimensioning and tolerancing per ANSI. Y 14.5 m, 1982. 6. Controlling dimension, inch. MC145488. Literature Distribution Centers. USA, Motorola LI Territory Distribution, P.O. Box 20912, Phoenix, Arizona 85036. Europe, Motorola Limited, European Literature Center, 8810 ERS Drive, Blakelands, Milton Keynes, MK145 BP, England. As IA Pacific, Motorola Semiconductors HK Limited, P.O. Box 80300, Changshawan Post Off ICE, Kowloon, Hong Kong. Japan, An-Ipan Motorola Limited, 321 Mi Namiyazabu, Mi Natoku, Tokyo 106 Japan. _@ Motorola 1/23449 PRIN TED IN USA 10/8 IMP Arial Lit HOC 676888 L5000